Okay, good morning, everyone. I'm blinded here. As announced, we do punctually Berkeley time, 10 past. So welcome. This morning today we have two more exciting sessions and one more keynote. And we start with a session which is chaired by Kirsten Persson, who you saw yesterday already, so I will only spend 1 minute saying who she is. She works both at Berkeley in material science and at LBNL, where she heads both the materials project and the, what's this thing called? The molecular foundry, sorry. I just blanked. Okay, with that, it's your session.
Thanks, Christian. Okay, I think we really have a treat for you today. We have 4 people speaking this morning who are really on the forefront of doing AI and ML together with materials and molecular design and simulations. So the first speaker, it's my honor to introduce Professor Connor Coley. He is the class of 1957 career development professor and assistant professor at MIT in the Department of Chemical Engineering and the Department of Electrical Engineering and Computer Science. He has a lot of awards. I'm just going to mention a few. He's the recipient of the CNN Talented 12 Award, the Forbes magazine's 30 Under 30 for healthcare, Technology Review's 35 Innovators Under 35, an NSF Career, the ACS Computational OpenEye Outstanding Junior Faculty Award. I think the more awards you have on these awards, the better. The Bayer Early Excellence Award in Science, and the 3M NTFA, and the Schmidt Early Career Fellow, and the 2023 Samsung AI Researcher of the Year. So, Connor, we are very excited to have you here, and we look forward to hearing about accelerated molecular design, synthesis, and analysis.
Excellent. Thanks very much for the introduction, for the chance to be here and share some of our work with you today. It's really a terrific symposium and a fantastic lineup of speakers, and it's very fun to be among them this morning to kick things off. So I work mostly at the interface of AI and chemistry. I think a lot about small organic molecules and the many roles that AI can play in accelerating the discovery process. So chemical space, I think it's fair to say, is enormous. People like to put numbers to it, and for small organic molecules, that number is about 10 to the 60, 10 to the 80. It's astronomical, it's virtually infinite. And so when we think about trying to navigate this very large chemical space and find new molecules and materials with extraordinary properties, we should be thinking about the ways that we can accelerate this process and use computation to help us do things more efficiently and more robustly. Now, it doesn't really matter if we're trying to discover a new molecule itself or if we're trying to discover a new reaction or manufacturing process or even trying to identify unknown structures, right? There's a role to play for AI. Now, I like to sort of comment that, sometimes we can get away with off-the-shelf techniques that we import from computer science, right, using sort of algorithms and models off the shelf designed for natural language or for images. But molecules are kind of funny as data structures, right? Molecules are not inherently text or not inherently images. They're these sort of weird three-dimensional floppy things that move around in time and space, and so sometimes we need to be a little bit more careful about how we represent them to computers and how we then use them in our learning algorithms. Now, small organic molecules are, as the upper right sort of hopefully conveys, a very versatile design modality. Admittedly, I think mostly about them in the context of therapeutic discovery, but we use them across disciplines. We use them in materials. We use them in dye-sensitized solar cells. We use them in organic electronics. We use them as ligands and catalysts themselves, especially polymers, linkers in reticular materials, working fluids to replace halogenated things in refrigerants and fire suppressants. There's sort of an endless list of the ways that we use small molecules to support sort of our modern life. Now, sort of against my better judgments, today I'm going to try to tell you about 4 short vignettes. We'll see if it works. I'll stay on time, I promise. Just to try to convey really the breadth and richness of opportunities that we have to bring in new computational workflows and sometimes old computational workflows to accelerate the scientific process. Now, where I'd like us to start is with this sort of highly idealized structure-property relationship. So this is a cartoon surface. You can imagine that it's conveying that as we change molecular structure, sort of as the x and y axis maybe, we'll have different molecular fitness levels. And that could be things relating to electronic properties. It could be stability. It could be any number of things that we're trying to optimize when we're trying to pursue a new molecule. Now, traditionally, and quite often, what we'll do is we will go through this process of virtual screening. We will take this sort of imaginary landscape that we don't necessarily know, and we'll list out molecules and we'll try to evaluate them. That might be in experiments, might be a simulation, right? This relates back very much to what Christine talked about with sort of these large virtual screening campaigns that one can do with computational chemistry. And so in this sort of paradigm of virtual screening, we're often finding ourselves increasingly looking at large chemical spaces, very large chemical spaces. Now, in a different context, in the context of structure-based drug design, right, these virtual libraries that we're screening are now numbering in the hundreds of millions and billions. So it's quite common at this point to take a protein of interest, let's say, and to take a list of billions of molecular structures and to try to run really crude, but not free, simulations to understand the affinity between that protein of interest and our candidate small molecule ligands. Okay. Now, when we do these virtual screening campaigns, even though we have this massive search space, right, the hope is that we're going to narrow things down to a very small list of high-performing molecules. And what that means is that the vast majority of calculations or experiments end up being to some extent wasted, right? They don't directly contribute to our ability to find the very, very best structures. Now, instead of running 100 million sort of simulations here exhaustively, what we can do is very simply adapt the framework of model-guided Bayesian optimization to say, let's just put a model in the middle. What that lets us do in this context is evaluate or simulate a small number of molecules and use a trained machine learning model to predict the performance of the remainder, and then use that to steer us and point us in the direction of more promising chemical space and steer us away from less promising candidates. So it's a very simple framework, and Bayesian optimization has been around for quite some time. But in practice, it's actually quite effective and yet still not as widely used as it could be. Right? So in this sort of plot, we're showing that compared to this sort of random baseline of just exhaustive screening everything, if we use a surrogate model, just insert it into this workflow, we can find the vast majority of the best molecules with orders of magnitude fewer simulations. And so that lets us save on computes, maybe save on experiments, or it lets us just search a chemical space that's 40 times bigger. And maybe that larger chemical space will have even better solutions. Now, one of the sort of really nice things about sort of working from the more, workflow and algorithmic side is that quite often the things that we do are generalizable, right? So this is structure-based drug design. We're not here to talk about structure-based drug design. But virtual screening takes place in a number of different ways. And if we look back at, for example, the Harvard Clean Energy Project, there was a very large virtual screening campaign conducted to find organic molecules with an optimized HOMO-LUMO gap. And this required TD-DFT, time-dependent density functional theory calculations, which took a few CPU hours per structure, and they did this for about 2.5 million structures. So were we to have applied the same framework of model-guided optimization, we could have found, again, the vast majority of the best-performing molecules, in this case with about 1/25th, let's say, of the simulations. And so this very simple technique of just inserting a surrogate model into the picture, right, lets us have these massive savings of cost. And this becomes especially important when our design spaces open up and become intractable to evaluate exhaustively. And so recently, in collaboration with a colleague in material science, Rafa Gomez-Bombarelli, we've been looking at zeolites as very interesting porous crystalline materials of interest. They have some parallels to MOFs and COFs, as we've heard about. But one thing about zeolites is in the synthesis of these sort of inorganic frameworks, there's a special aspect of the synthesis conditions which tends to be this incorporation of what's known as an organic structure directing agent. This is a small organic molecule. This is a small organic molecule that templates the pores that are being formed and hopefully makes it kinetically favorable to achieve a particular crystalline material. Now, why does this matter? Well, there are hundreds of thousands of known hypothetically known thermodynamically stable zeolite frameworks. But we've only experimentally verified a couple of hundred of those. So there's this vast design space that we think will have useful applications in gas separation, in industrial catalysis. But researchers have only been able to make a couple of hundred out of the hundreds of thousands that are predicted to exist and be stable. Now, organic structure-directing agents number in the hundreds of thousands or millions as well, and so we're left with this massive space of sort of synthesis design options, and it's intractable to pursue experimentally, it's intractable to even simulate exhaustively, and so now we're using this sort of model-guided optimization framework to help us navigate this space and hopefully let us access these new zeolite materials. So virtual screening, right, is really ubiquitous, and again, it's across applications in human health, across applications in material science, climate sustainability. But of course, you can't go too long these days without talking about not just screening, but generative design and inverse design. Now, the reason why generative design is so alluring for molecular discovery, materials discovery, is because in principle, if we have some understanding of the relationship between a molecular structure and its property, we hope or we feel like we should be able to invert that in some manner so that we can directly identify, okay, what are the molecular structures predicted to exist at the maxima of the surface? And so the hope is that we can use generative techniques to be creative, to invent new molecules that aren't in our lists, even of billions of structures, and find better and better properties than we had before. And so since about 2016, 2017, generative techniques in chemistry have really picked up. They work in a number of different ways, and they're applied to a number of different problems. Again, we see a lot of visibility in the pharmaceutical industry in trying to apply these to the invention of new drug molecules, or at least drug candidates. So here this is a model that's operating sort of atom by atom and inventing this structure that's predicted to be a protein degrader. Not experimentally verified, but at least structurally looks like a very reasonable suggestion. And we also design these in sort of three-dimensional spaces, so maybe coming back to that application to templating zeolite porous frameworks. We can develop conditional models such that if we have a target molecular shape like the one shown in the blue mesh, we can ask our models to propose a molecular structure that can at least approximately achieve that shape. It's not perfect, but it's a start. There's really sort of a number of different ways that we can try to tackle this generative task. But the problem, and this has already been alluded to quite a bit yesterday, is that synthesis becomes a barrier for most of what we do, regardless of if we're using generative design or not. Now, especially when we're using generative design, we can end up with recommendations from our models that syntactically look like valid structures, but sort of semantically or to a chemist might not be so reasonable. Okay, so when we use generative design, sometimes we get molecules that look like sort of the smaller ones up there that are synthetically tractable. We could give that to a chemist. They could try to make it and test its performance experimentally. But sometimes our models like to give us weird structures, right? Structures that are not reasonable for a variety of reasons. But one of those reasons is that they're not synthetically tractable. We should be able to look at these structures and know this is a bad recommendation because there's no chance that you can make that and test that. It just doesn't make sense to a chemist. So synthesis becomes this interesting now problem that emerges. And to make molecules, we have to have a plan, or should have a plan. So synthesis planning is this idea that we can take a molecule that we'd like to make. In this case, this is palbociclib in the bottom right corner. And we want to devise a recipe, right? We want to specify what are the series of reaction steps that connect us to commercially available starting materials. So what are the steps that take us from the things in red, the reaction conditions in blue, and intermediates in yellow, all the way through to our final product of interest. And so when faced with some of these structures, right, we can ask ourselves, okay, well, how do we make them, right? We can imagine developing programs, and we do develop programs to try to recommend these kinds of synthetic pathways. But there's an alternate approach that we can take. When I talk about generative design, right, we sometimes take for granted that we can use models and computers to propose new molecular structures. But it's important to be more specific about how it is we are proposing those structures. Like, what are we truly asking a model to do if we say we're using deep learning to invent new molecules? We have to pose a task in terms that it can understand. Now, one way of posing that task is as a sequence generation task. So there are these line notations that we can use for molecular structures. So we could say that to propose a molecule is to propose a string. That's OK. We could treat them as graphs, as we often do in molecular machine learning. We could say to propose a molecule is to propose a graph, or in 3D space, a point cloud, something in 3 dimensions. But when you do this, you then are faced with this difficulty of chemical synthesis. And so instead, something that we've been sort of working on and advocating for over the past several years is to do this design actually in the space of experiments, in the space of synthesis. So what I mean by that is, instead of designing a molecular structure as this sort of amalgamation of atoms or letters or 3-dimensional Cartesian coordinate associated atoms, we can generate molecular structures as a synthetic tree. And so now we're saying to propose a molecule is to propose the recipe by which that molecule is made. So this is trying to align the way that our generative algorithms think about chemistry with the way that our experimental chemists have to think about chemistry. Now, to sort of maybe draw an analogy, potentially an unnecessary analogy, right? I liken this to trying to design a very custom cake. So I could design a cake by specifying its, texture, color, shape, flavor, right? All these sort of parameters, and say this is the cake that I want. But then if I do that, I have to go to an expert baker, and I say, can you find some way of achieving this combination of properties? Can you make this cake a reality? And it might take, an expert baker willing to take custom orders to do that. But if instead I just write down the recipe and I say, this is how you make the cake that I want, then a lot of people can follow a recipe, right? We don't necessarily need to be that inventive or have that much expertise to carry it out. And we can even start to think about the use of robotics, of course, to carry things out for us as well. And that's essentially what we're doing here, is we're designing the recipe by which we're making the structures. We're not directly designing the structures themselves. That's a byproduct. And so, what this looks like is we train some neural agents. It's basically a set of policy networks, and what it does is it learns how to take some target molecule of interest and select commercially available starting materials, select reaction transformations, and stitch those together in a tree. And so from a learning perspective, this looks like a tree generation task operating in this high-dimensional discrete action space. And so this has some fun sort of machine learning novelty. We heard about from David that you need those elements of methodological novelty to get computer scientists excited. So this has those. But also, by virtue of generating this synthetic tree, right, we get the recipe and the molecule at the same time. It's sort of a 2-for-1. Now, once we've sort of trained this on known molecules and known recipes, we can then wrap it with some optimization routine, so we can tweak this input, this conditional code. That will lead to different choices throughout that policy. It'll lead to a different synthetic route, a different molecule, and different properties. So the whole thing can be wrapped in something like a genetic algorithm or model-free optimization. So as a consequence of doing this, we end up getting molecular structures that are quite small and simple. This is a proxy optimization objective that's related to biological activity. But increasingly, what we're doing is trying to apply this to a broader range of applications, including things from fragrances to, in this case, CO2 capture agents. So this is a very general purpose technology, right? It's a model designed to generate new molecular structures and their synthetic routes in one go. And so you can say that any application for which a small organic molecule might be the solution is amenable to this kind of model. So synthesis is really essential in the discovery stage because it lets us take these ideas and bring them into the lab more quickly. But synthesis itself, right, as the title says, also offers opportunities to pivot to more sustainable practices. So we and others have been developing programs for performing retrosynthetic analysis and planning synthetic processes for many years. Sometimes, if we're lucky, when we query these programs with a molecule of interest, we'll get sort of this great big network out, where every one of these little branches might give us a different idea on how to make a structure. So, sometimes we get 0 results, sometimes we get 1, sometimes we get hundreds or thousands of pathways to choose from. And when that does happen, we then have the luxury of defining criteria for choosing what makes the best process to produce a molecule of interest. Now, thankfully, there's been a lot of work trying to formalize some principles of green chemistry from the green chemistry community. There are simple notions and calculable properties like the atom economy, which is essentially just if you look at the structure of your final product compared to the structure of all of your reactants, how many atoms have you lost going from the latter to the former. The number of steps often correlates with the environmental impacts of a process. There are all sorts of solvent greenness scores, usually qualitative, that we can use to say, we like water, we like ethanol, we don't like chlorinated solvents. So we can use this to rank and triage between these many possible routes. And then there's also more complex notions in the bottom right here, showing process mass intensity, which is sometimes defined as the mass of everything that goes into a process compared to your pure product. Sometimes it's the mass of waste compared to your pure product. And this essentially is the sort of aggregate efficiency of a full manufacturing process. And this ratio turns out to be, it's very close to 1 for the petrochemical industry. We've really optimized squeezing every last drop out of a process. In pharma, it's often 25, 50, 100, right? Hugely impactful in terms of the amount of waste that's generated. And so we can try to use this as a criterion to select better, greener pathways. There's also good opportunities to bring in new synthetic strategies into the toolkit that we're using to make molecules, whether it's in the lab scale or at the manufacturing scale. So this is an example just of a route that has been proposed by one of our programs that combines, in these orange boxes, these sort of traditional chemical steps with an enzymatic step as the very last one. And so this gives us an opportunity to sometimes replace or augment manufacturing routes and processes that have been designed only with traditional chemistry in mind, these use of rare earth metal catalysts, maybe use of chiral purifications. There's a number of different sort of reasons why you might not want to pursue the sort of known chemical routes to this particular molecule. But by bringing together not just traditional chemistry, but by sort of incorporating enzymatic chemistry and using biological enzymes to carry out transformations, we can find conditions that can be run at much milder states, ambient temperatures, usually aqueous solvents, much more benign processes can be carried out here. And actually, I should probably emphasize that one of the reasons why AI sort of matters in this case more than you might think is because the expertise of using traditional synthetic steps and using enzymatic steps don't always overlap, right? In especially pharmaceutical industries, are sort of completely different teams that think about how we can use enzymes to make molecules and using traditional metal catalysts to make molecules. And so by having a program that sort of brings them together, even if that program is not better than the best synthetic chemist or better than the best enzymatic chemist, you can at least bring the two fields together and make them aware of opportunities to incorporate each other's toolkits. And so this is sort of one of the ways that we can make sure that we're providing value just by getting people to think about the concepts of green chemistry and enzymatic chemistry when they normally would not. So there's other opportunities from taking inspiration from biology, not just using biological enzymes to serve as catalysts, but also use molecules from biology, whether that's sort of metabolites from bacteria or agricultural waste products, as feedstocks for the processes that we carry out. So there's a really extraordinary list of weird, fun molecular structures that are present in biomass, some of them in very low abundances, some of them in high abundances. But these kinds of structures also give us an opportunity to pivot away from the petrochemical-dominated sort of feedstocks that we tend to use. Right? Almost everything that we make tends to be derived from petrochemicals at some level, right? Even the medicines that we take are mostly derived from petroleum indirectly. And so we, long-term, need some sort of path to avoid that and trying to bring in feedstocks now and starting materials that can be sourced from sustainable places like agricultural waste is one of the ways that we're also thinking about this transition to greener manufacturing. And it's sort of a fun consequence of the really combinatorial nature of chemistry that relatively small numbers of building blocks that we can derive and know how to purify and work with can lead to large numbers of new molecular structures. And so we're also doing, not just the sort of synthesis planning, which is done as a backwards process, but forward planning, which is done as an enumerative process, to say, okay, given these sort of sets of renewable feedstocks that I have access to, and given these enzymes I have access to, what are the thousands or millions or billions of molecules that I think I can make? So now we can define these sort of sustainable chemical spaces to complement the traditional sort of lists of molecules that chemical vendors give us. Now, the very last vignette I want to share is sort of pivoting gears, but it's fun. It's something we've been working on sort of most recently, and that's in the world of analytical chemistry. Now, analytical chemistry tends to be overlooked when we think about AI for science. Might not seem as flashy, but it really is quite essential as well. In analytical chemistry, we can think about the role of small organic molecules in mediating interactions. A lot of those interactions are in human health. We can think about primary metabolites like cholesterol, right, being implicated and correlated with many different disease indications. Small organic molecules are what give some plants their psychoactive properties. But sometimes the interactions with the environment in these small organic molecules are very much not so benign. And I want to focus for a second on this story box on the bottom right corner, which was reported in a science paper, I think back in 2020. So this molecule, 6-ppd quinone, is a molecule that was not previously known before this paper reported on it. What was known and what was observed was simply the die-off of coho salmon populations in Washington. So for many years, they observed that the population of salmon was declining. They weren't laying eggs at the same sort of rate that they were previously. They did not know what was going on. And so eventually, through sort of painstaking analytical chemistry effort, they tracked it down to this particular molecule that was present in the water. And so 6-ppd quinone is an oxidative degradation product of 6-ppd. They react with ozone in the atmosphere. And 6-ppd is a preservative that's added to tires. And so as tires go on the roads, flake off small particles of rubber, those eventually slowly react, leach into the water, and in this case, inhibit the ability of salmon to produce eggs. And the concentration of 6-ppd quinone that is relevant is 1 part per trillion. Right, CO2, we think of it as dilute, or some of us think of it as dilute, right? That's, a few hundred parts per million. This is 1 part per trillion. And so that sort of speaks in some ways to the sensitivity of the analytical instruments that we sometimes need to use just to figure out what's going on in the environment around us. These sort of really, really trace environmental contaminants. And so, our ability to identify those structures, right, also has to operate at this very small scale. And so we often use techniques like mass spectrometry to take a sample of interest and acquire these mass spectra, and they look like sort of fragmentation patterns, little blips in these plots. And the goal is to take those sort of unknown molecules and try to elucidate what the structures are. Because when you measure a sample out in the wild, you're not told this is the structure. You're given this sort of characteristic fingerprints, and you're then tasked with finding out what the structure is. And we usually pursue this by sort of comparing what we measured to things in reference databases. It's a simple match using like a cosine similarity. But our reference databases of known molecular structures and their known fragmentation patterns are very small. And they don't contain things like 6-ppd quinone that we sort of need to identify and elucidate. And so we can think about ways of augmenting these reference libraries by simulating what these spectra might look like for new compounds. And to sort of cut a longer story short, what we do is we sort of take inspiration from what physically happens in our spectrometers and this key step of collision-induced dissociation where we bombard a charged precursor with sort of high energy and it fragments into these sort of physical things that we then detect. We can train models that are mimicking the physical fragmentation process and learning how molecules are likely to fragment and then how those fragments are likely to manifest in our spectrometer. We can train this on experimental data, but again, using domain expertise, this sort of domain-inspired or application-inspired work to reflect the physical process in what we do. And so we are able to take new molecules, predict how they might fragment. Because we've sort of grounded the prediction in this physical process, it's inherently interpretable. Right? We don't have to worry about explainability as a separate task. It's sort of built into the model. And of course, what actually matters is not just making sort of images that compare predicted spectra to known spectra, but it's how does this affect our ability to elucidate new unknown molecules? So that's what this sort of plot on the right summarizes. Obviously, there's a lot more quantitative detail that I'm not going over. But this plot sort of reflects our ability to identify what is the unknown molecular structure present in a sample. And the purple trace, which is us, can be compared to other, even machine learning approaches, transformers, all sorts of different network architectures that don't think about the domain of chemistry. And we can sort of measure, like, this is beneficial, right? Actually thinking about what is happening at a physical level helps us here. And so we do have some interest in sort of human health, obviously, and biomarkers and working with clinicians. But we're also collaborating on understanding degradation products and the face of pesticides in the environment in particular. And trying to think about, well, if we know how molecules are likely to degrade and persist in the environment, we can now engineer new materials with their sort of environmental fate in mind from the beginning. And so that's how we're sort of trying to slot this into the overall framework for sustainable materials development. Okay. So I am over time, but I managed to get through at least most of these 4 stories, and really they're meant to showcase, again, the breadth of opportunities and how we can use AI in molecular materials discovery, whether it's just exploring very large design spaces to designing new molecules with synthesis in mind, having that synthesis use enzymatic chemistry, renewable feedstocks, or trying to identify unknown pollutants and contaminants in the environment, right? There's a huge breadth of opportunities to work with, and a really nice fluidity between applications in human health and sustainability. Again, most of the work that I do typically involves human health and applications to drug discovery, but equally, all of these algorithms apply to challenges in sustainability as well. And so I think there's interesting ways of sort of crossing application spaces with these shared methods. So with that, I'll thank you again for the invitation to be here today. Looking forward to sort of questions and discussion, and I'll just close by thanking my terrific research group.
Wonderful. Do we have any questions for Connor? Yes.
Fantastic talk. Thank you so much. So I have a question about the exact sort of way that you're framing the objective function. Yeah. Well, it's not a technical question, actually. Mm-hmm. It's because from my perspective as an outsider, a computer scientist, I would assume that it's not the existence of a green synthesis pathway that is the important thing. It's what people are actually going to use in practice. Yeah. How do you account for that? Because the best from a green perspective is not necessarily what people are going to do. How do you optimize for maybe what is most cost effective being as green as possible? Or maybe even discounting certain molecules that don't have a good green pathway at all, rather than just finding the greenest pathway that exists there.
Yeah, absolutely. So everything is multi-objective. Everything's a multi-objective optimization in life and in science, of course. So the sort of sustainability of the pathway is certainly one of the elements. And when it comes down to it, right, a lot of companies will optimize for cost of goods manufactured, and that will be really the bottom line. And so to some extent, the role of these tools and techniques is at least to provide the information to make informed decisions, right? We're still leaving it up to expert process chemists to understand the trade-offs and what's workable or not from a financial perspective. But having that information available and showing them that perhaps there are these cost-competitive routes that are more green is a path forward. Now, estimating costs, building in those complexities is another hour-long talk. It's a very complicated process, and we're only scratching the surface of being able to do so quantitatively. But at the very least, we can try to provide support for that kind of decision-making and elucidate what those trade-offs are. But it's a great question.
So I have a question on your analytic chemistry
Yeah.
approach, which is, the way I understand it is that you have a set of molecules you actually, let's say, have a spectrum for.
Yeah.
And then you have a much larger set of molecules, which could be the culprit. And now you're trying to find which one of those. But you might actually want, it almost looks to me as if you could just do the inverse problem. You could sort of, or can you is the question. So can you say, oh, here's the spectrum. This is how the structure must look like.
Yeah. Yeah.
Or is that too difficult?
So this is sort of a retrieval formulation of the problem, where we want to compare to known reference spectra, and we can say, well, let's simulate the reference spectra to augment our databases. But what about just going directly, right? Solving this f of x at the top, take a spectrum and propose a molecular structure. We can do that. We've built and published models to do that. That task, that formulation, right, is almost like you've one shot to get it right. You take the spectrum, you make the prediction, and so there's less of an opportunity for the models to have some sort of refinement step. So actually, we're in some sense we're not exactly doing this process of retrieval in practice. What we're doing is we're creating these sort of optimization consistency loops to say, if we can take a structure and predict its spectrum, then we can still iteratively optimize on that hypothetical structure for this sort of de novo generation type setting, and look for the structure that is most consistent with what we've observed. So there's like a few different angles to tackle the same problem. Empirically, we do find that going directly from spectrum to structure is a little bit less robust. This one, but it's a valid approach for sure.
We're a little short on time, so we're going to thank Connor, but we'll bring him back for the panel. So thank you so much. And our next speaker, I'm so excited to introduce Aditi Krishnapriyan. She is an assistant professor here at UC Berkeley, where she is a member of the steering committee at the Berkeley AI Research, BEAR, and the AI Plus Science Group in Electrical Engineering and Computer Science, EECS, and the theory group of chemical engineering. She was a DOE computational science graduate fellow at Stanford, and I'm happy that she saw the light and came over here, where she became the Luis Alvarez Fellow in Computing Sciences at LBNL. And we're very excited to hear her talk, and it's going to come anytime soon, on machine learning methods for improving molecular simulations. It's going to happen anytime. I had to try different ports on my Mac. One port didn't work, the other one did. If it's the use
HDMI.
Oh.
I think we're great. Yeah.
Yay.
Perfect. Great. 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 Great, I'm really excited to be here with a lot of really great discussions and great speakers. And I'll be talking today a lot about this intersection between machine learning and the domain sciences, and how I think these two things are very synergistic in a few different ways. And I think molecular simulations is actually a fascinating area that really brings these two fields together on both sides. So I think this is not going to be new to this audience. Modeling spatial and temporal behavior over time is really going to be one of the key aspects of unlocking a lot of insights that we have, whether it's for catalysis or materials design or designing better materials for batteries. When we go to the drug discovery level, we look at molecular simulations, we look at proteins and how these evolve over time. And really the crux of all of these applications comes down to, can we actually unlock and model the spatial and temporal behavior of these systems of interest? And when we look at these types of systems, some really interesting things start to happen at longer and longer timescales. So for example, if you're looking at some type of diffusion process in a material, if we can simulate the system for a really long time, we can compute nice properties about the system, like the diffusivity. This also happens in the drug discovery domain. When we look at proteins and the way that proteins fold, this is going to unlock a lot of insights on, say, the catalytic activity or the bioactivity of these systems. And one of the things that's really crucial here is that we want to do these simulations for really, really long time steps, just so that we can see this type of behavior emerge and that we can calculate the properties of interest. It's also interesting to do this with large-scale simulations, because the larger we can go, the more atoms we can have in our system, the more realistic we can simulate the behavior of these problems. So how do molecular simulations work more broadly? So we've talked a lot about potential energy surfaces in previous talks, and molecular simulations essentially operate very similarly. So you might have some molecule of interest. This is going to be something that lies on a very complicated potential energy surface, like some very high-dimensional surface that we care about. And maybe we have some type of function to estimate this potential energy. And we could use something really cheap, like some type of very quick force field that fits the parameters. But if we want to really do really accurate computations, often this ends up being some type of quantum mechanical simulation. And this can start to get very expensive, which is obviously where we start to have some alarm bells go off about maybe this is where we can actually see some acceleration opportunities. So after we go ahead and have some function to estimate the potential energy surface, and we query this and we get some energy out, we can go ahead and get forces on this type of system. And then we can use some of the classical tools that we have for numerical integration to go ahead and integrate the system forward over time. And if we do this repeatedly and repeatedly, we get some type of simulation over time. We can run this out for many, many time steps. And I think something that's quite interesting about this whole thing is that it's typically a stochastic process. So there is some idea of statistical uncertainty. There is some idea that we're actually drawing samples from some type of distribution. So one of the reasons I think this is a really interesting area is, so one, I think for a lot of the chemists, the material scientists, the physicists here, you know that this is a really impactful area because simulating these systems for long time scales at these realistic sizes could make a huge difference in many, many types of applications. But I think this is also a really interesting problem from an ML point of view for a number of different reasons. One of those reasons is that we do want to simulate these systems at these different length scales. And so this opens up a natural question of what are the best ML methods we can use to accelerate this process. Of course, because these are systems we want to simulate at large scales, this requires computing forces and doing numerical integration on every atom. And this is going to also get quite expensive. And there's also this component of the fact that this is some type of stochastic process. And so there's a component of physical consistency to think about, the fact that this is very similar to looking at the thermodynamics and respecting the thermodynamics of these systems. And I think this latter point is actually quite interesting from a few different ways. As some of you may know, a lot of the history of modern machine learning, there was definitely a kernel of inspiration from these very types of molecular simulations and the general statistical physics community. And so I think these are actually some things that sometimes end up going both ways between communities. So let's come back to what this molecular simulation would look like. So we have our full setup here, the full cycle of how we would simulate these systems over time. And now let's think about what are the common ML aspects that we start to bring in for these molecular simulations. And one of the most common aspects here, this is just the general overview of where the field is to use some type of ML model to estimate the potential energy surface here. And this is something that's typically very slow, takes a while to query, and so potentially a natural way to speed up this whole cycle is can we actually get a pretty good estimation, a much faster estimation of this complex potential energy surface. We can query that instead, and now when we run this for millions of time steps, this is going to expedite the whole process. You could also potentially think about actually trying to use machine learning to speed up the actual numerical integration process itself. This is a bit less common, but is, I think, starting to become a more active area. Okay, so when we think about ML aspects for molecular simulations, there's a few key aspects that come into play here. Of course, data sets are going to be really, really important. There's also this idea of neural network architectures, and I think that is also something that's evolving in terms of how much focus we should pay and what aspects of these architectures we should pay attention to. And then I think there's also this idea of training procedures. So how do we train these models? What are the loss functions that we use? And how do we get the most out of different sources of data that we might have? And I think, as we've seen in other fields of ML repeatedly, different types of training procedures can end up making a huge difference in the final outcome of what we'd like to predict. So starting with these data sets, our systems typically look something like this. We might have a molecule or a material. It's some type of atomic structure defined by these XYZ coordinates. And hopefully n is a really large number. That would be ideal. And we typically have some labels associated with these atomic structures. So one example of a label would be the energy of this whole molecule. Another could be the forces that are on each atom. There are also other properties that we could compute about these systems, but energies and forces tend to be the most common. And one point is that these are usually computed from density functional theorem, which is a type of quantum mechanical simulation that I know has been discussed in many previous talks. And the reason I want to point that out, though, is because this is still a simulation-based method, and this is computing information about one modality of data, specifically these quantum mechanical simulations. But I think we also maybe want to think about broader modalities of data as well. And there's also this question of, this is a simulation, how do we actually bring this back to the full cycle of what we might do in a lab or what we might see with experiment? So coming to this point of neural network architectures, so these are colloquially known as neural network interatomic potentials because they're an approach to actually estimate that potential energy surface. And it's become pretty common in the field now to actually represent these systems as some type of graph. There's also a whole line of work and interest in this idea of, does it make sense to encode certain types of symmetries into these models, into your feature representations? So essentially your feature representations would now be geometric tensors. And I think this is a pretty open area in the field now about to what extent do we need these types of symmetries? To what extent are they actually going to be useful for certain types of downstream tasks? If they're useful, what's the best way to encode them? And how do we also grapple with this trade-off between efficiency and potential accuracy in terms of training these models with this higher level of complexity? And so I think philosophically this is actually an area where I think it could be very fruitful to think about general strategies or operations for designing neural networks that go beyond a very, very specific type of architecture. So putting this together and coming to this point of training procedures, and how do we actually typically train these models? The most common way that we would try to estimate this type of potential energy surface is we have some quantum mechanical data set. Maybe it's typically labeled with energy and forces. We can go ahead and feed that into a neural network, any type of neural network architecture. And then we output the predicted energies and the forces, and we're going to take a loss function on these energies and forces. And this is going to represent the full problem setting that we're trying to estimate. And if we want to go ahead and train this model, we can do the standard procedure that we would to train neural networks. So we train this with backpropagation. We differentiate this loss back through the network and update all of the weights of the neural network accordingly. And so this could broadly be thought of as a supervised learning procedure that we're using to estimate the potential energy surface. And our goal is that this is ideally going to be accurate enough that it's going to give us a pretty good and accurate and efficient depiction of the landscape that we want to model. So putting this full procedure together with all of these different components, a typical procedure that you might do, and I think this would be like the most common procedure that you might employ to solve these problems, is that you start by training the neural network with atomic structures mapped to energies and forces. So this would be the standard supervised learning setting. Then after you train this model, maybe you have some type of test set that you'd like to evaluate this performance on, and you go ahead and compare that energy and forces error on this separate test set. And hopefully that error is sufficiently low, and if it is sufficiently low, you can go ahead and run whatever type of simulation you want with your model. So you could run a molecular dynamics simulation with that trained neural network. And so this full cycle would look something like this, where the neural network is estimating the potential energy function, and that's what you're using to simulate this system over time. So this is a pretty standard procedure to follow, but I think when we come into ML land, there's a few things and a few caveats we have to think about that sometimes don't immediately pop up when looking at this from an outside framework. And this is namely this idea that the training objective is not necessarily always in sync with what we would like and what we would like to see. So if we go through this procedure, we train the model, we check the error, make sure it's sufficiently low, and then we run MD simulations. Sometimes you can see some weird things happen with that simulation that you run, where even when the energy is low, even when you have a reasonable time step, you're seeing some really unphysical things happen with your neural network. Here's another example of what that looks like. I think this one is a little more fun, actually, where if you wait for it, you get a very unphysical bond stretching going on. And these instabilities are obviously super problematic from the neural network point of view. So we can't simulate these systems for long time scales if you run into these instabilities. But I think the other big concern is that this means that we don't necessarily have a lack of reliable simulations. So if I showed, say, a chemist in the audience this type of simulation, would you really want to use these neural networks to study your systems? And so diving in a little bit deeper into the failure modes of these neural network potentials, we see that over time you start with stable structures and you become repeatedly unstable as you go further and further along in time. And of course, this is problematic for all of these reasons like reliability. And because of the fact that we run these simulations for long time periods, we want to compute properties of interest from those simulations. And that becomes challenging if we can't trust the simulations. And they're leading to these instabilities. And these failure modes can actually manifest in a lot of different ways and depend sometimes on the systems that you look at. So sometimes we actually see that with molecules, a failure mode that might come up is you have this really unphysical bond stretching or bond coordination that doesn't make sense, and you've essentially landed in a spot that's unphysically not plausible. Sometimes with other types of systems like condensed phase systems or materials, we see these instabilities propagate a little bit differently in that you might have a more local instability. So you might have two atoms that run into each other and fall on top of each other, and that blows up the energy, and then that leads to a failed simulation downstream. And if we come back to this potential energy surface view of what this might look like, I think essentially what we see here from an ML point of view is this very classic distribution shift problem, where we've trained our model on as much of the potential energy surface as we can. But when we go out and simulate it, it's very plausible that there are certain types of regimes that are out of distribution, and we don't know what to do when we get to those points. And this could manifest in a few different ways. So you could have some type of true potential energy surface like shown in blue here. And maybe there's some hole in that potential energy surface. And if you fall into that region, that's game over, and now the simulation is just too unphysical to continue onwards. So there's a few different ways this can manifest where maybe the right trajectory is going up a potential energy well, and you've veered off into a completely different domain. And this is really coming up because we could try to look at the whole potential energy surface, but this is so complicated, so difficult to capture, that it's almost, depending on the system, it's very likely you'll fall into regimes that you haven't really seen before. And I think this comes up to this really big point about why AI and science is hard, because machine learning is really a problem that we try to do really well on in-distribution problems. And ML is great for doing well on these in-distribution problems. But when we actually look at the scientific problems that we care about, these end up being things that we care about that are more on the out-of-distribution side. And this manifests in a lot of different ways across a lot of different fields. So, okay, in this case, this wasn't so good. We had these failure modes here. Is there something that we can do to actually fix some of these failure modes? And I think this is an area where it could be worth thinking about different types of data modalities. So the first thing that we can immediately think about is let's get more data. And I think this is great. We should always think about getting more data, and more quantum mechanical data will definitely help. The flip side of that is it might require quite a lot of data, and that takes a while to compute, but also it may still not be enough, because this is a very specific style of data trained on quantum mechanical simulations and energies and forces, and that could be quite different from what we actually see when we go and do an experiment or when we actually run these simulations out. So it may not necessarily be the complete data source that we're looking for. And so I think going forward, and this is one of my general philosophies, is thinking about what are the general training procedures that we can use in machine learning to capture more information about these systems and not encounter some of the failure modes that you see here. And I think one very natural way to go is actually thinking about why not actually use the simulation itself? Why not actually run the simulation out and see if we can actually come up with new ways to include that within the training procedure? So let's come back to this molecular simulation. We go ahead and simulate the system over time. And over time, we can compute properties of interest about the system that we care about once we simulate this sufficiently long. So if we want to take learning signal from the molecular simulation itself, we can take this whole procedure, wrap it up together, and this is essentially what we're actually going to end up using. So we're actually going to run this molecular simulation for many time steps, and this is actually the learning signal that we care about now. So going beyond purely force and energy matching on the potential energy surface, this is giving us more information about what happens when we actually simulate out and see other parts of our phase space. So if you run this many times, at each time step, you query the neural network and you run the numerical integrator. And you can compute system observables about the system over time. And these could vary. There's many, many types of observables you could compute. Something that relates the interatomic distances between your atoms, something that tells you something about the transport coefficients of your system. And so what about actually training to these system observables in addition to what we do with quantum mechanics? So the bonus here is that you get multimodal data. You see different parts of your phase space. And the nice thing is that you can actually get this from experiment too. So now we can actually think about bridging that theory to experiment gap. So let's put this together in a new problem formulation. So let's assume that this is equilibrium MD. And one thing that we actually know on the domain side about doing these samples is that we're sampling our new structures from a Boltzmann distribution. So when we run these systems over time, it's essentially the fact that the probability of our system appearing in a certain state is proportional to this value here in terms of your Hamiltonian and your partition function. And again, this is actually another place where there's some nice connections to broader machine learning because of some of the formulations we use to sample distributions can be thought of in a very similar light. So let's formulate this learning problem as follows. So this is a stochastic problem. And so what we're going to do is the neural network is going to learn to maximize the expected reward, in this case, whatever observables we want to get over time. And this is going to be done under some type of Boltzmann distribution that we're sampling from. And so this is essentially the learning procedure that we're going to do now. The one caveat with this type of procedure is that if you want to train the neural network to these types of observables, you need to be able to estimate the gradient of this training procedure so that you can update your neural network weights. And so this requires actually differentiating that final step, that expected reward, with respect to the parameters of the neural network. And this is actually where I think some interesting ML things come into play. Because one approach you could do is direct differentiation. So you differentiate this loss, you do backpropagation through that whole molecular dynamics trajectory. But there's actually a lot of issues that come up here because the MD simulation required many calls of the neural network, many calls of this numerical integrator. And so if you're trying to actually do backpropagation through this whole trajectory, this ends up being too memory intensive, super computationally expensive, even just for a few steps. And so this is an immediate bottleneck, even though we know and we have a pretty good intuition that using information from time trajectories is going to give us more information for the neural network to process and update better to tackle some of these harder problems out of distribution. But one actually key approach here, and this is, I think, something where we can really take some of our domain insights and use that to devise new ML methods. This insight here is that the individual sampling steps don't matter because we're just sampling from a distribution because this is a stochastic process. So it doesn't matter necessarily how we got to that point. It matters that we ended up at a point where we could compute those observables. And so because those gradient steps are actually independent of sampling, we can formulate this problem using implicit differentiation. So we can actually derive this using implicit function theorem and derive a new way to actually train the model using just the state that we ended up at. So putting that all together, it means that then when we train to these observables, we can train the neural network with this type of implicit approach. And the key insight is that we're separating the forward pass of the neural network with the backward pass of the neural network. And this ends up being a really powerful approach for all sorts of physics-based simulations. So after we went ahead and formulated it this way, you can actually derive something that we call a Boltzmann estimator to train the neural network and get gradients. And you can actually formulate this for global instabilities. And this is actually something that you can derive in other ways too, like from thermodynamic perturbation theory or from policy gradient and reinforcement learning. This specific formulation that we derived with implicit function theorem also means that you can go ahead and formulate it for local instabilities as well. So these are the types of instabilities that might be more common in materials or in certain types of catalysis systems or condensed phase systems. So this whole training procedure now actually follows very nicely from how we were doing things before. So here, we're still doing a step of this pre-training on these simulations. So we still train our model with energies and forces of atomic structures. But now we actually go ahead and do this additional procedure, which we call stable training for stability-aware Boltzmann estimators. So sometimes it's nice that the actual method maps on very nicely to a nice acronym. And in this case, what we're doing essentially after we pre-train this neural network, so this can be any neural network. Again, I think this is a case where the architecture can be totally agnostic. Maybe we make a better architecture and we can still use that within this framework. And the idea here is that we go ahead and find all of these unstable regimes that, that we get after simulation that fall into these areas that we know aren't physical. And we go ahead and roll back those simulations, and we then train this model to system observables that we know hold true after many, many time steps. And by doing that, we can actually correct a lot of these instabilities, and it doesn't take that many cycles of this type of training to really correct a lot of the problems that we were seeing from before. So what does that look like in the context of actually simulating these systems? So this is an example of simulating a molecule where we train it on 1,000, 10,000, and 50,000 structures. And we also train it on 1,000 structures and apply our stable training procedure on top of that. So one thing that you see here is that when you train on 50K structures, the stable simulation time is on the x-axis. You do get more stable when you use 50K quantum mechanical data compared to just 1K. But if you use this training procedure on top of that, you get significantly more stable compared to that 50K option. And now you're actually really pushing these simulations out much further in time. And so I think this is one example that I like to just illustrate that sometimes thinking about new data modalities can make a huge difference in actually understanding and simulating our systems more reliably. And this is just another example of what this looks like, where the y-axis is the number of unstable trajectories, and we push that y-axis down because we're able to actually simulate more trajectories for longer time periods. One nice thing about being able to simulate these systems much longer is that you can compute more accurate transport properties. So in this case, we compute a diffusivity coefficient that ends up being closer to the true one because we actually are able to go and simulate this further and reduce some of the statistical error that you might otherwise see. And finally, one thing that was also interesting was that this type of training improves the accuracy of system observables that the neural network never saw. So in this case, we have a radial distribution function here, and the black line is the reference, and the regular training procedure is in blue, and then our stable training procedure is in orange. And so we see that even though the neural network never saw this during training, because it was able to at least get some signal about other modalities, it's able to improve upon this type of metric as well. So I think finally, I think this idea of ML training procedures using simulations can potentially be very powerful in a few different ways. And I think one of those reasons is because we have these really nice reliability guarantees on accuracy and convergence that we get from these numerical simulations. And it may also enable training with different types of information. And so while I talked specifically about molecular simulations, we found that these types of iterative solvers and neural networks, training them together in an end-to-end differentiable manner, makes a big difference for other types of spatiotemporal modeling problems. For example, this is a case of solving Navier-Stokes equations in fluid dynamics. And we've also done some work on actually trying to scale these procedures. So one potential thing is that are these procedures a little bit on the slower side, but we can actually come and use tools from other areas of ML, so we can actually formulate these types of hybrid training methods using mixture of experts, which is really the thing that's made a lot of the large language models work really well now by distributing the computing load across different types of experts. And we can use that same type of procedure here to scale up some of these methods as well. So in summary, I think one of the things I really wanted to discuss, because I think this is really where I see the future of the field going, is thinking more about what are the general training strategies that we can use for ML methods in the scientific domain. So what are strategies that we can use on top of a lot of general approaches or a lot of general architectures that are not necessarily going to be very specifically tailored, but move towards this idea that we're going to try to tackle a set of problems with a suite of tools. And on that note, how can we take advantage of all the modalities of information that we have? And so this comes into play when we think about bridging what we train on with what we care about. It comes into play when we think about bridging this theory-experiment gap. And I think it comes into play just because we do see a lot of data scarcity in the problems that we look at. I think that's rapidly changing, and we should always be looking forward to how to design methods, given that we're going to have an abundance of data in the future. But at the same time, I think thinking about different modalities of data comes into play because some areas are going to have less data than others. And then finally, I think this idea of comprehensive evaluation metrics is also important to both detect the failure modes of neural networks that wouldn't be immediately apparent from current evaluation metrics, but also just thinking more about reliability in downstream applications. If I could give you evaluation metrics that you trust a lot more, hopefully you're much more likely to think about the idea of using neural networks, because this is something that scientists put a really big premium on, this idea of reliability. So I'd like to thank the great students that I get to work with, and I'll go ahead and come back to this summary slide, and happy to take any questions.
Very exciting. Do we have questions for Aditi? Yes.
Hi. Yeah, thanks. That was a great talk. I feel like in particularly language modeling and other image domains now, people working on these large systems take a lot of consideration for things like data quality, deduplication. It seems like it's a little less clear in kind of quantum mechanical simulations what that actually means. And I was wondering if you had any thoughts on kind of generally data quality versus quantity. And, yeah.
Yeah, so I think this actually manifests differently in some ways in the scientific domain, because in vision and in language, a lot of the tasks are actually classification tasks. In our case, sometimes these are regression tasks where we want to output a value for an energy, for example. And that means that when we run this at different levels of theory, we might be getting a different number out. And I think that does play some role in that if your level of theory is better, hopefully your ML model is also better. I think there is that trade-off, probably a Pareto front of trade-offs, though, of generating more data that's less accurate versus less data that's more accurate. And probably the right answer, like most things, is that it's somewhere in between.
Maybe I'll add to that, too. I think one of the pathological things that Aditi sort of pointed out is that when we train on data that tends to be sort of close to an equilibrium. So we have these trajectories for nice little molecules that are not too uncomfortable. So we never see these horribly elongated bonds or whatever. They're not part of our training data because we don't start with those weird things. So the machine learning model never knows that should be really high in energy. That you shouldn't be able to stretch that bond that much. So having a more I would say, consciously built database or data sets that sort of actually incorporates those points. And I wasn't quite sure, is that what your Boltzmann distribution does?
So one thing actually with our approach is that we do this just based on the data that we have. So it's purely static. It's a fine-tuning approach that you can add after you train a model. So that's one of the nice benefits, that there's a pretty cheap cost associated with it because there's no extra data generation. At the same time, I think it's super important if we can do additional sampling to get a more thorough database, and then maybe that means that there's less of a need, or there's fewer cycles of this type of fine-tuning that we have to do on top of that.
Yeah, knowing basically where your system can't go, and sample that a little bit more consciously than rather just staying close to your equilibrium.
Right.
Cool, sorry.
So a question also along the same line. A very nice talk, by the way. Can one recast the stable training procedure as a regularization, either of the architecture or the training based on physical constraints, such as, atoms cannot lie on top of each other and bond cannot be stretched out too much?
Yeah, that's a great question. So I think you could think of it in that way if you were also doing this training in conjunction with the QM training. In this case, we formulate it as more of a fine-tuning procedure where you do the quantum mechanical training and then you apply this on top of that. But I think those two things, it might be interesting to do them both in conjunction. We initially actually converged all of our potentials using quantum mechanical training and then only applied this on top of that to also just see what is the benefit that we get purely from this training procedure.
Okay, so we're gonna again move. We will have Aditi back for the panel. We have a coffee break now for 20 minutes, and please everybody be back here by 10:40 when we're gonna start again. Let's thank Aditi again. So I'm just going to use my It's absolutely my pleasure to introduce Larry Zitnik. He is the research director on the fundamental AI research team at Meta. He focuses on scientific applications of AI and machine learning. For example, the discovery of new catalysts. Maybe we'll hear about that. All right, excellent. Previously, his research in computer vision covered many areas, such as accelerating acquisitions of MRIs through the FAST MRI project, and developing data sets to benchmark object detection and visual language tasks. And before, does it work now? Okay, now it works. Before joining FAIR, he was a principal researcher at Microsoft Research, and he comes to us with a degree in robotics from Carnegie Mellon University. So we're really excited that people come from all kinds of directions, because that's how we're going to make progress in this interdisciplinary regime of AI, ML, domain sciences, and applications. So Larry, take it away.
Thank you. Thank you for having me. So I'm hoping today, as already mentioned, to kind of give you a perspective of this space from a machine learning viewpoint. And what it's like for somebody like myself with a machine learning background to come into this space and kind of see what it's like and what it feels like to work in this space. So one of the big motivators to explore this area is climate change. It's one of the things I think is top of mind for many of us here. It's something that I know is top of mind for my children. You know, it's something that we need to address. So first, the good news. When you look at renewable energy generation, it's been increasing year after year in a very, fairly dramatic rate. And this is really promising. It's awesome that this is happening. It's great to see this is going along. But there's a problem. Even if we increase the amount of renewable energy that we're producing, we're still going to have an issue. So let's just look at an average day in California. And this is the demand of electricity for a day in California. Now, if we look at the amount of solar and wind generation at the same time, you get this. So let's pretend. What if we just took the amount of solar energy and wind energy and we just 3x'd it? Created 3 times more solar panels, 3 times more wind generation. What would happen? You would get this. There's an obvious problem. Yeah, well, maybe not batteries, but batteries are part of the solution. But in any case, there's too much energy when the sun's shining, and there's no energy at night, when we all want to fill up our cars and do all the other things we want to do. So how can we store renewable energy? How can we address this problem? Well, one of them is we could do batteries, and that's good for some applications, that's good for some scenarios. But there's other ways of doing this as well that could scale to grid-size applications. One of them is to use renewable energy and electrolysis to break water apart, to generate hydrogen and oxygen. You basically let the oxygen go up into the air, you keep the hydrogen, and later on you use the hydrogen in a fuel cell to generate electricity. You can have more complex processes where you take the hydrogen that you just generated, you combine it with CO2, hopefully from the air, use methanation, to then create methanol, or natural gas, essentially. You can then burn that natural gas to create electricity. You can store the CO2 that you get from burning that natural gas, put it back in the cycle, and repeat, 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 and we could have energy that is carbon neutral. Now, all of these processes, they seem fairly complex. There's a lot of chemistry involved, but there's one thing that's important to understand, which is that in this, there's a bunch of different chemistry problems. Electrolysis, how do we break apart water? Methanation, how do we combine CO2 and hydrogen to create methane? Fuel cells, how do we use hydrogen to then create electricity? All of these are kind of chemical reactions. Or CO2, how do we pull CO2 out of smokestacks or out of the air? These are all kind of chemical problems. And these, when you look at it from a machine learning perspective, sometimes I think people look at these as, if you're outside of chemistry, if you're outside of these things, it feels like niche. But in reality, these are the big problems that we have today. And many times I think this is a bigger problem than, generating new images or videos or having really great chatbots that we can communicate with. These are the problems that we need to address. These are the problems we need to solve. All right. So let's just look at one of these problems in particular and talk about let's dive in a little bit and see what the actual problem is and how can we address it with machine learning. So first, let's talk about catalysts, because I just mentioned there's a lot of chemical reactions, and the way that we make chemical reactions efficient is to use something called a catalyst. And that's a material used to speed up the reaction rate without being consumed in the process. And you can see catalysts in many different applications, but one of the ones that's fairly popular is you can have like a car, which is a fuel cell car. Within it, it has this fuel cell, and on the fuel cell, there's a cathode and anode, and on the cathode, there is a catalyst which drives a chemical reaction. All right? So this chemical reaction is going to be an oxygen molecule plus 4 hydrogen or protons. And we have a catalyst here, let's say a platinum catalyst. And we have our oxygen molecule. And as it floats around, it's going to come in contact with that platinum surface. And what happens is that weakens the bond between the 2 oxygen atoms. And because that bond is weakened, because it's in contact with that platinum catalyst, is when 2 hydrogen come into play, they can more easily pull away one of those oxygen atoms to create a water molecule. And when 2 more hydrogen come into play, it's much easier to pull off that final oxygen atom off the platinum surface. So what you've done is you've just taken a chemical process using this catalyst, and you have to apply a lot less energy to make it happen. All right. Now the trick with a catalyst is it needs to be just right. If you have a catalyst which attracts that molecule too strongly, that molecule will just sit on the catalyst surface, and your reaction is going to grind to a halt. If you have another catalyst which doesn't attract the molecule strongly enough, it's not going to have any effect at all. So your chemical reaction is going to run at the same rate as if you didn't use a catalyst at all. So what you need is a catalyst which is just right, which attracts that molecule not too strong, not too weak. The problem is for many chemical reactions, the ones that we really care about, like fuel cells, green hydrogen generation, etc., the catalysts are expensive. They're platinum, iridium, etc. And if we really want to have a green energy economy, we need to find better catalysts. Which then raises a question. How do we find new catalysts? So how do we screen them? Well, how do we screen these computationally is as follows. We can take an absorbate, which is that molecule in the chemical reaction of interest. We put it on top of a catalyst. We then relax the atom positions. We basically compute the forces on the atoms, like Aditi was talking about earlier. We then update the atom positions, repeat this until we get to a local energy minimum. And that local energy minimum, we can then use that to say, okay, is it pulling that absorbate strongly enough onto the catalyst surface, and use that to approximate the reaction rate that this catalyst would have, to kind of predict the trends of what we would expect. Now, this is great because we can computationally, using computers, model a catalyst. The problem is that a single relaxation, what I just mentioned, takes about a day of compute using DFT. So density functional theory is great because it can model things with relatively decent accuracy, but computationally it's very, very expensive. And as you heard in the previous 2 talks, same as this application, there are billions of possibilities. So there's just no way to kind of screen through all these materials using this approach. Which raises a question. Can we take that computation, which used to take days, and can we get it down to a second? Can we make it a lot faster? And this is where ML comes in. Instead of using density functional theory, can we use ML to approximate it? And this is why we started the Open Catalyst project. This is a collaboration between CMU, Meta, and the University of Toronto. Now, being a good machine learning researcher, you want to study a new problem. What's the first thing you want to do? You got to get data. I love making data sets. It's like my passion in life. It's creating data sets. So the first thing we did is we wanted to create the Open Catalyst 20 and Open Catalyst 22 data sets. And the key thing here is the computational chemistry community was doing an awesome job showing that machine learning potentials work really well on specific materials. But the open question was, can we train a machine learning potential that can work across a wide range of materials so we don't have to keep retraining models and collecting new data? And in order to train that model, what do you need? You need lots of data. Not just a little data, you need a lot of data. So what we did is this data set has 140 million training examples. That means 140 million DFT calls, which took about 500 million hours of compute to estimate. So if you're wondering what Facebook servers are doing when they're not serving up cat videos, this is what they're doing. They're running atomic simulations. They're running DFT, which is awesome. We have a really great software engineering team that figured out how to run DFT on the Facebook servers and do that all efficiently, and that's been really great. The data set, again, we want to expedite research in this community. We want to enable everybody to be working on this space. So one of the things that was really important to us was to make sure that we could not only create this data set, but we could release it so others could use it. So this data set is released for both commercial and non-commercial uses. You can basically do whatever you want with it. And then, again, the data set's fairly large, so we created separate splits so that way if you are a graduate student and you want to publish papers on it, you can train models on the 2 million data set. It only takes a few days to train a model. It hopefully is a little bit more accessible to the academic community, so that way we can see more people publishing on this. All right, so what is the data? What actually is the problem? It's super simple. What you have is the input is a bunch of 3D atom positions and their atomic numbers. Easy inputs. And the outputs is what Aditi was mentioning earlier, which is the energy of the overall system and the atom forces for each atom. So really simple inputs and outputs. You don't need to be a chemist to understand this. I think it's something that the machine learning community can easily grasp. And then to model this, we generally use graph neural networks where each node equals an atom, and then each edge corresponds to neighboring atoms. And then all we want to do is figure out a neural network which, given a certain node embedding, which is like the embedding for each atom, and then pass messages between the different atoms to update their embeddings to then estimate the energy and forces that I mentioned earlier. In some ways, this might even look like a really simple problem. Because if you want to attract machine learning people to a new domain, there has to be something novel, something interesting to study in that problem. You can't just take known approaches and just slap it into this new problem and it just works. That's not interesting. You're not going to publish in NeurIPS, ICML, iClear doing that, right? So,
but the beauty doesn't work.
Yeah, but luckily, just plug and chug doesn't work. And that's what I want to talk about. Why is this problem actually interesting if you're a machine learning researcher? Why is this something that you actually want to dive into and work on? Just from the pure machine learning concept, not because you want to help with climate change and that sort of thing, but because you want to do interesting research. Well, one of the interesting aspects of this space is something called equivariance. It's a mathematical property, which means that if the input is transformed, the output should be similarly transformed. So to illustrate this, let's talk about translation equivariance. And I have actually a computer vision background, so I'll use a computer vision example here. So let's say you have a segmenter, you have an image here, and you have a function which segments out that dog. If you translate that image, you run the same function, you translate that back, you should get the same answer as what you did in the first place. So if you have this property, it's translation equivariant. And the reason why would you want equivariance in computer vision? Yeah, it's a mathematical property, it should hold, but what is the real reason you want to do this? The real reason is because you don't have to train a dog detector or segmenter for that box, another one for that box, another one for that box, another one for that box. You want to have a single segmenter, a single set of weights that works across anywhere in the image. So you're not learning things that are redundant. And it makes your neural networks much more efficient. That's why CNNs are so popular, and that's why people use them so much. And the way that CNNs work is you basically break your image up into a grid, you compute a function there, and a compute a function there, compute a function there, and you get a response map. And this response map obviously will translate when you translate your image. It's a really nice, eloquent solution to solve this problem. So how does this translate to atoms? How does this translate to our problem? Well, instead of translation equivariance, what we really care is about rotation equivariance. And what we mean by that is we have a set of atoms. We have some function, let's say, that computes the forces on those atoms. If we rotate those atoms, use the same function, compute the forces, rotate them back, we want to get exactly the same answer. And again, this seems like a really obvious mathematical property, but putting this into a network which actually has this property is much more complex. Because it places very strong constraints on the type of networks, nonlinearities, etc. that you have in your neural network. And when we're studying atoms, as we know, a lot of angular information, etc. is really important. So if you have a CO2 molecule like that, you might think a water molecule looks like this, but as many of you probably know, it looks like this. So studying kind of this angular information is important for this problem space. So in our image, we had a representation where we had an image, and we have a bunch of planar channels encoding that information. Now for a bunch of atoms, what type of embedding? How do we want to, what's our internal representation of the network? what we care about is the relative orientation of all these atoms, right? So instead of having planar channels, what we want is instead, we want to have spherical channels. So you can imagine a function on a sphere encoding information about what other things exist relative to that atom in different angles. So how do we represent those spherical channels? Well, if you're coming from a computer vision background like myself, the obvious answer is a discretized grid on a sphere, like a lat long. Like, that's the first thing I thought of, first thing we tried. But this has all sorts of issues, because if you rotate it, then you have to resample it, and it's just computationally not very efficient. It's not a great solution. But instead, you could use something called spherical harmonics, where you have a bunch of coefficients, you have a bunch of basis functions, and your basis functions look like that. And this creates a really nice way of looking at it, but it's also something that's very different from how the machine learning community generally looks at embeddings. Usually it is a discretization over a grid, or over tokens, or over words. It's not thinking about it as like continuous basis functions on some domain like this. So it opens up kind of a new way of thinking about how to apply your neural networks. And these spherical functions are really cool, like spherical harmonics. So you can take a bunch of coefficients, and you can use that to basically approximate any function on a sphere. But what's really, really cool about them is you can take those coefficients, you can multiply it by something called a Wigner D matrix, and then what can you do? By multiplying it by the Wigner D matrix, you can rotate that spherical function any way you want, perfectly, losslessly. It's a really cool mathematical property. And by basically allowing you to kind of rotate those spherical harmonics and then reorient your feature space, it allows you to do all sorts of very interesting and kind of fun things from a machine learning perspective. At this point, I would typically go into a lot more mathematical detail on how this is done and how you can do this really efficiently, but I don't have time to do that today, so I'm not going to go into that. Check out some of the papers. We'll probably put some videos up later. There's actually other videos online if you're curious to hear more about the mathematics behind this. All right. Another property that's really interesting is the conservation of energy. So this means that the total energy of an isolated system should remain constant. So when we compute our forces in our models, we could initialize our neural network, we could do the message passing with the graph neural network, and then we could compute our energy. And then you could compute the forces as a derivative of the energy with respect to the atom positions, which essentially corresponds to backpropping your gradients all the way back through the neural network. And this is a great way to do it, but it has a problem, which is doing that backprop is computationally very expensive. It takes twice the amount of memory, and just due to, if you use AMP or other ways, basically becomes numerically unstable for many scenarios and many different neural networks, just because the gradients don't behave very well. And for this reason, at least in our team, we haven't been using this approach as much as we would like because of these reasons, because you can't train as big of models, and numerically it's a little less stable. So instead, what we've been doing is we initialize a neural network, we do message passing, and then we compute the energy and the forces separately. What's awesome about this is computationally it's a lot less, and it's much more stable. So we end up using this a lot. But there's a problem, which is that this does not ensure that you're going to be energy conserving. So to give you a sense for energy conserving, what we mean by this is, let's say we have a two-body system, two atoms. If you look at the potential energy between them, the potential energy is going to change as those two atoms move, get closer to each other. So we think the energy here is actually changing, but it's not, because in a closed system, those two atoms, as they move closer together, are going to increase their velocity. And that kinetic energy is going to offset the increase in kinetic energy is going to offset the decrease in the potential energy, and the overall system is going to keep the same amount of energy. But when you compute that kinetic energy, that's your forces, right? That's going to say how much should you increase your velocity. And if you get that wrong, the kinetic energy is not going to offset the potential energy differences, and you're going to end up with a system that's not stable or not precise. Another way to look at this is that if we have a potential energy surface like this, which is actually many, many dimensions, but here it's just shown in two, is that if you integrate the forces as you go around, and you have the same starting and ending point, the forces should integrate to zero. And this is actually something that's really tricky to think. If you compute the forces as a derivative of the energy, you get this all for free. It's nice and easy. But if you want to come up with another way of doing this, it is pretty hard. pretty complex. And this is something I think is like an active area of research, and I think something that's really interesting to kind of explore and try to figure out ways of maybe approximating this or doing this without having to do the full gradient-based approach. All right. So that's a couple of reasons mathematically why this is a really interesting problem. And again, I think it's an interesting thing from a PhD kind of academic perspective. But let's take a step back and let's look at results in action. We've been training a lot of models on this. We've been applying it. Where are we now? So if you go to the Open Catalyst dataset and the website, you'll see that we have a nice leaderboard. You can kind of track all the results. And let's look at force mean absolute error, force MAE. So at the very beginning of this project, in 2019 or 18, we had a couple of the early models here with higher errors. And then the next generation of models, we saw the errors progressively getting better, and then kept getting better and better, where the ESCN and Equiformer V2 are these equivariant models that I was talking about before that use spherical harmonics, et cetera. And we've been seeing better and better accuracies. Now, one thing you might be thinking, though, is it looks like it's kind of going like this and it's kind of flattening out, right? So are we like hitting diminishing returns? Like, what does that mean? So a little bit on that in a little bit, but just to show you what it looks like when you use these forces, this is really interesting. See the ESCN, which is the machine learning potential, we have DFT, the ground, which we call the ground truth, and you can see that even in this fairly complex relaxation, we're getting very similar results. Like obviously they're going down at different rates, different optimization steps, and the DFT calculation here would have taken days, and the ML1 is going to be done in seconds. And you notice here the energy conserving, not quite right, because the energy goes up. It should always go down. But it still works pretty well. So when you do a relaxation and you want to find where the molecule exists on the atom surface, you don't want to just do a single relaxation and say, okay, when you relax from there, you go here. You actually want to do this multiple times, and then you want to find out which is a global minimum. Because if you have a molecule on top of like floating above a catalyst, it's going to naturally want to go to the point where the energy is a minimum, right? So you've got to find where is that global energy minimum on that catalyst surface. And this is computationally even more expensive. So one way you can approximate this, you can do 100 ml relaxations, find the one or a small set that have the lowest energy, and then you just do a single point DFT calculation at that low energy state to kind of refine your energy estimate. And if you do things in this way, using ML and DFT, you can do this whole process 700 or 1,000 times faster than if you just use DFT alone. So that's a huge improvement. Now the question is, it's faster, but is it accurate? It doesn't make any sense to be faster if you're not accurate, right? So let's look at the success. So success means that you get the same answer within 100 millieVs, which is a pretty small delta. And then on the x-axis, what I'm going to show you is a force MAE from the slide I showed you before. So the early models had very low success. Like, they weren't really useful for this application. The next generation of models, they did slightly better. But you're still not seeing that much. If it only works 40% or 20% of the time, it's not going to be that practically useful. Now, if you remember the next generation of models, the force errors got a little bit better, right? It wasn't a huge amount, but they got a little bit better. So what happens? Well, the next set of models, that little bit of improvement in the forces led to really big improvements in success. So as we improve these forces more and more, when we apply them to real applications and start using them for relaxations, we haven't been studying MD as much as others. We're hoping to see that these get better. All right. So, and we put this out as a data set as well. All right. So just to give you a sense for screening a new material, if we actually use this process, each material has a different surface you need to consider for the catalyst. It can be that surface, that surface, that surface, that surface, that surface, that surface, and there's basically 90 different possibilities. Many reactions you want to have multiple absorbates. Each absorbate, you want to consider all these different placements, which means that how many relaxations you need? 90 times 5 times 100 equals 45,000 relaxations. If you did this with DFT, you're talking 120 years to do a single material. Using this combined approach, you can do it in days. And this allowed us to basically brute force calculate these properties across many different materials for basically every known material for certain applications. And this wouldn't be like, this doesn't matter. unless it actually is predictive of what we see experimentally. So we're working really closely with the University of Toronto to do high throughput testing to then generate a data set of experimental results that go along with our computational data as well. And hopefully this will be coming out in a little bit. All right, so simulating entire reactions. So right now we've been talking about these fairly simplistic systems, but we could have much more complex things where we have errors in the, or like defects in the catalyst. We could have multiple absorbates. You can have sorbents, that sort of thing. Much more complex reactions. So real reactions are a lot more complex. And also, when we think about time frames, reactions in nature happen very quickly. DFC simulations are really slow. ML simulations are a lot faster, but there's still a big gap here in between. So one of the things that we want to look at is, when we think about chemical reactions, before we were talking about absorption energies, but what if we look at transition energies, which is, if you go back to this illustration, let's go here, is you have your activation energy here, which is how much energy do you need to have to rip apart that oxygen molecule? I'm going to skip over that. But in any case, we have just because I'm going to run out of time, we've applied the ML models that we trained on OC20. We didn't update them at all. We just used the vanilla model, and we applied it to estimating transition energies, where we have a starting state, a final state, and what you want to do is find the saddle point, which is a transition energy. And we used something called NEBs, or nudged elastic bands, and we used ML models instead of DFT, and we've been getting really good success. And that's been awesome because we can show that the models generalize across many different applications, or many different types of materials, but also across many different applications. And we don't have any NEB calculations in the training data set. So it's really interesting to see that it generalized to this application as well. And here's some examples of the ML ones. They're pretty cool looking, but for time, I won't show them all. And there's a lot more areas that our team's been looking at. Direct air capture is one of them. I don't have time to talk about that today. And other things you can use these models for, like batteries, proteins, drug discovery, I think others have talked about today in enough length. And the way that I look at this is like these ML models hopefully are offering us like a new microscope into this problem, another way of looking at it that hopefully enables us to get a better understanding of what's actually happening at the atomic level by expediting these calculations, and hopefully we can experiment a lot more. And with that, I want to thank the team. And thank you for the time. Really appreciate it.
Great. I'm sure we have lots of questions. Sorry.
Thank you so much for the nice talk. So the part I'm wondering is if we really look at the OC20 leaderboard, and what we see is that there are multiple submissions of the very similar models, right? We'll see multiple leaderboard results for GemNet, multiple leaderboard results for BIDMaP, and what people have been arguing over and over are these performance increase from these architectural changes. But what I'm really seeing is even for the same model, we can have a very different performance. So I'm wondering what factor that contributes a lot to this performance difference. Do we really need a lot of architectural changes, or maybe it's just a way to how to train the model better?
That's a good question. So when you mean performance, you mean accuracy improvements?
Mm-hmm.
Okay. Yeah, there's a lot of different ways of, like GemNet, for instance, is an invariant model. It looks at it specifically encodes like the angular information between the atoms. You have ESEN, Equiformer, which look at the spherical harmonic representations. There's a lot of different ways of approaching this problem, and because it is, like, we've only been, like, this is like a relatively new problem. It hasn't been studied for 20 years. Like the last 5 years, 6 years, we've really been looking into it. So I think there's still a lot of room of exploring different model architectures. I do think that a lot of the advancements are due to novelties in the model architectures. It's not just training with more data or factors. Because one of the big challenges we have is, like, say you want a property like equivariance. That places constraints on the nonlinearities and like the model architectures and that sort of thing. So I think it takes a lot of creativity to figure out how can you get a model that is equivariant or close to equivariant that also is as expressive as possible. And that's one of the things that I really like about the OC20 data set, is that it's large enough that like it's pushing the community towards thinking about how can we make the models as expressive as possible so that we can represent all of the data. You know, otherwise, if you have a really small amount of training data, it's too easy to overfit, and you naturally want to develop models which are architecturally much smaller and not as expressive, so that way they don't overfit. But this is, like, I think one of the first kind of data sets and problems where it's kind of the opposite, where we need more and more expressive models. And I think that's why you'll see models like OC or GemNet OC, Equiformer, et cetera, which can be expanded, which can have a lot of parameters, because you need to have that in order to model these kind of larger data sets and more complex problems.
Just to add the question, I think the other part that I'm maybe not quite sure about is I do see a lot of variance of the performance coming from the same model name, and what is the cause of that?
Do you have a particular model that you're interested in?
For example, there are like 4 to 5 GemNets performance shown.
Yeah, there's different GemNets on the leaderboard. A lot of them are just different sizes. So there was the original GemNet, and then there's GemNet OC. So GemNet OC has a bunch of kind of model tweaks to it, which made it specific, like to make it work well specifically for OC20, hence the GemNet OC nomenclature. And then several of the GemNet models are different model sizes. So you can vary the number of layers, you can increase the width of the models, et cetera. And some of the thinking here is, yeah, we can go to bigger and bigger models, but at some point you're getting diminishing returns because if you can't run that model on a single GPU, like not many people are going to be using it, or if you're doing things like relaxation or MD with it, computationally it's going to take a lot longer. So at some point you want to have like the best model you can get with the most accuracy, but you want it to be computationally reasonable. So we're always kind of looking at that trade-off when we're building these models. We don't want to just, you know, blindly make the numbers lower and lower and make the models really big and to the point where the models get as slow as DFT, you know, in the worst case. So,
Thank you.
One more question.
Mostly like a clarification question.
Yep.
When you talk about like the same models for transition state estimation, what I was wondering is it that you took the same model architecture in a new data set, or you took the basically pre-trained model and you fine-tune it in a small data set? So it was more like a foundation model, like fine-tuning approach?
Yeah, so what we did, and I want to give credit to Brooke Wander, who is on that. She's a CMU PhD student right now who's leading this project. Hopefully this paper will come out in the next month-ish, so hopefully it'll come out shortly so you can read all about it there. We did not retrain the model. So we took a model which is literally, it's on the webpage. You can download the model right now, and you can just apply it to NEBS, and it will work. It did work in our experiments. What we did do was we did create a validation testing data set. So we have, as part of that paper, we're going to be releasing a data set of roughly 1,000 different NEB calculations using DFT. And we use that to demonstrate that the ones using just machine learning are getting approximately what you would get if you did full DFT on these calculations as well. So as far as like new data sets, it's just for testing and val. The models themselves we didn't even retrain them. It's like literally the ones taken off the website.
That's pretty cool. I'll ask later.
Yeah.
I know we are trying to.
Thanks, everybody. Let's thank Larry so much again. Right, so the last speaker of our morning session is Professor Carla Gomez. Carla is the Ronald C. and Antonia Nielsen Professor of Computing and Information Science, the director of the Institute for Computational Sustainability at Cornell University, and the co-director of the Cornell University AI for Science Institute. And she comes with a PhD from Edinburgh, so she's international. She has a lot of awards. I'm going to try to sort of boil this down to, and if I miss anything, let me know. The most influential Cornell professor by Merrill Presidential Scholar 2020. She's also the recipient of the Association for Advancement of Artificial Intelligence, AAAI, Feigenbaum Prize in 2021. She is the 2022 ACM AAAI Alan Newell Awardee, and she is the fellow of a number of societies, AAAI, ACM, and AAAS. And we are so excited to have you here, Carla.
Thank you so much for the invitation. And I'm super excited to be here. This is amazing and really, really fantastic. And today I am a computer scientist, and in fact I was just talking to Jennifer Chase about how I've been doing this for a while, for over 15 years. I started working and nurturing this field of computational sustainability, and when nobody was really working on this, and but as the previous speaker highlighted, these are really the critical challenges that we want to address. And so computational sustainability really aims to harness the power of AI and computational methods for sustainable development. And I want to emphasize that sustainable development really encompasses balancing environmental, economic, and societal needs. So this really, the idea is we want to, benefit the humanity. And you may have seen this several times. Recently, 2015, the Sustainable Development Goals were put forward, ranging from no poverty, no hunger, health, education, and the protection of our planet. So, and I take this opportunity, as I mentioned before, this was a time nobody was doing this, so, but, NSF believed in us, and they really allowed us to create the Institute for Computational Sustainability to nurture and, identify the core research areas, and both from computation and sustainability perspective. And we then got another major NSF expedition to nurture this CompSusNet. And of course, I want to thank my students because they are the real bees here. Today, what I want to do is to give you some examples of our research, ranging from AI to combat the rapid decline in biodiversity, which is, like climate change, reduction of biodiversity is really a severe problem. But I also want to talk about, and yes, I'm part of this amazing session on AI to accelerate materials discovery for renewable energy. And if time permits, I would like to tell you a little bit about how AI can play a key role in terms of strategic planning to reduce adverse impacts of the Amazon, the real Amazon basin hydropower expansion on people and nature. In fact, you see here this amazing river, and right now there are already 200 dams, and over 400 have been proposed. And yeah, dams generate energy, but they can have very adverse impacts, like fragment the river, which really affects fish migration, transportation, sediment production, etc. But they can lead to also deforestation, displacement of populations, and including greenhouse gas emissions, because they flood huge areas that leads to the decomposition of organic matter with the release of methane. And what's the key question here? Well, how can we do this plan? And I love the line that Connor had, that our life is multi-objective. Yes, we need to think not just in terms of energy, but in terms of, how are we going to develop more ethical AI systems that look at all these different objectives. So, let me highlight a super important underlying theme. Larry mentioned that as computer science, we like thinking about the computation issues. And what's beautiful, and that's the beauty of computer science and AI, is the power of reductions, how we can transfer methods from one area. And I will tell you about how models that we developed to predict bird distributions, joint species distributions, were so important in providing insights in terms of how to actually, predict properties of materials and solving various challenges and critical problems like crystal structure phase mapping. And so what I want to do today, more generally, I don't expect you to understand this very complex subway line. You know, subway lines are always very complicated, correct? So, but the key idea that I want to emphasize here is, again, the transferability of AI and computer science. And you see, we have different stations which correspond to different projects, and then you see the subway lines that are the underlying themes. And in particular, I will talk about, pattern demixing, which are, source separation or solving inverse problems. And I will show this transferability across very different problems. I will tell you how crystal structure phase mapping is essentially demixing Sudokus. Yes. So, and so that's the big message that I want to emphasize here. But another big message that has been really discussed before is that, AI is taking over the world. However, AI really has been, the focus now is really data-driven AI, and with incredible results in terms of imagery identification, face and speech recognition, and of course ChatGPT. But in fact, that's why I love AI for science, and I've been doing this for a long time, is AI ML as we know it is not really good enough and cannot really solve scientific discovery and decision making. And the previous speakers, Aditi also mentioned, Larry mentioned that, and Connor. We need really, there are many challenges in scientific discovery and decision making. We are mainly unsupervised or few shot learning, correct? And we want to do decision making, and our models need to obey physics, and therefore it becomes quite challenging. And of course, we have to deal with these super huge combinatorial spaces. We need to make decisions, and we deal with this curse of dimensionality. So basically, I really, my research has been really about how can we combine data and knowledge? How can we do, bring together data-driven AI with the knowledge-based and knowledge reasoning AI to really be able to reason from first principles, because we want to really predict outside the training data, correct? And we need to do self-supervision. We need to be able to generalize beyond the training data, and again, dealing with combinatorial choices. Also, and the example, the real Amazon problem or strategic planning really shows that we need to develop more ethical systems, AI systems that can reason across multiple dimensions. And I think actually the power of AI is really, we will be able to develop systems can reason in a very high dimensional space that we can't. So that's why AI for science is so exciting. So let me start with talking about AI to combat the rapid biodiversity decline. And as a computer science, I like distilling the questions. And the question is, how can we do multi-entity learning? And you will see that if you want to be loyal to the underlying domain, you really need to capture the scientific knowledge and adhere to their prior knowledge. So, and as you know, this is really a fundamental question in biodiversity research, is how different species are distributed across landscapes over time. And this is really important for us to know how to protect the species. And this is, as I mentioned before, the decline of biodiversity is really a key challenge, just like by climate change. So we collect all kinds of data with all kinds of sensors, and the best sensor, can you guess the best sensor? Us. We are still the best sensor. And how then Basically, Cornell, the Lab of Ornithology, or Lab of O, has this amazing eBirds project, citizen science project, with about, by now, a million volunteer birders that have contributed with lots and lots of observations, building 4 times the Empire State Building, and combining those data with environmental data, we can really develop very fine-grained models. What you see here, this is an animation. It's actually the output of a machine learning model. And these models have actually been formed the basis for the State of the Birds report and allow us to have a better understanding and lead to very novel ways of protecting species. So, for example, the TNC, the Nature Conservancy, has this project, the Birds Return Project, and the idea is to really, protect the water birds in California. And what you see here, you have the Pacific migration. Our models can predict the trajectories, and then what they do is they have these reverse auctions where they allow the farmers to submit bids, to keep the target rice fields flooded during the short periods while the birds are migrating. So this is a very novel way of doing conservation, much less expensive than buying the entire land, correct? And this is only possible, in fact, they've already generated a ton of acres of additional habitat because of these super accurate models. Just a little, underlying this, I will say that the traditional approach is to really consider one species at a time, but ecologists know that, species dependence are really key. So they know that it is very important to understand the preference of the species with respect to the environment, but also the interaction among the species. And they know that this is modeled by a multivariate Gaussian model, and therefore, in fact, it's called the multivariate probit model, but, the current limitations, it's very difficult to engineer these features, and training this model is really challenging because there's an underlying multivariate Gaussian model, and estimating the parameters of the covariance matrix is very hard. And in fact, for all the computer science, for example, we know about VAEs, and VAEs use an underlying Gaussian, but then, okay, we assume the matrix is a diagonal matrix, so independence. So that's not good enough. And I always tell my students that we are not doing this to publish papers. We need to be loyal to the domains. And because for ecologists it is very important to understand the interactions, we need to do that. And so I'm not going to go into details, but essentially we developed this end-to-end framework where essentially we have, and this was super inspirational, for us to really address the questions raised by the ecologists, we develop a model that has a latent space that is an interpretable latent space. The word interpretable is missing there. And there we can actually collect information about the preference of the birds, embeddings for the preference of the birds with respect of the environment, but also the information to reason and estimate the covariance matrix. And this is going then to feed to the multivariate probit model. Here you see the semantics of the latent space, where we have the embeddings, the environmental associations, and the species interactions for the covariance matrix. I'm not going to go into the technical details. We have a way. The problem about this is typically you can use iterative sampling or all kinds of models that are sequential, but we want to take advantage of GPUs and do it in parallel. And we do this by considering a residual variable, conditioning on it, and then we can solve this in parallel. And in fact, our models scale way better than ecologist models and way better than computer science models. And we can actually estimate the interactions. What you see here is really the output of the model. You see that for 41 species of warblers, they are here. You see that they arrive in around March and then go north. You see the color, the lighter, the more species. So this is really the output of our model. Well, here we see, the actually embeddings, the interactions with respect to the environment and the species interactions. And as computer science, I always tell my students, we cannot just come up with a little model for a particular thing. In general, this is should be generalizable. And in fact, the same paper actually it has results for other multi-objective detection, for computer vision, mapping the Amazon land cover, and others. And here we actually, Aditi mentioned that in general, models are classification models, and you are right. This is a classification model. We want to predict all the species, but whether or not species 1, 2, 3 are there. But we need to do also counts. How many? So we generalize this to regression, and for example, for fish abundance, we did that. And then, we realize, now we have a regression model that's very powerful. We can actually use this for density of states prediction. And that's what we did. So let me now go to the next topic that's related, and this is crystal structure phase mapping. This is a long-standing problem in material science, and it is an inverse problem. I was happy that Chris mentioned that, because, so basically you are given a collection of X-rays and you want to infer the crystal structures of materials from this collection. So the AI topic is inverse problems and unsupervised pattern demixing. No labels here, no label data. So how does this work? Basically, material science, have a way of synthesizing lots of materials. They use this co-sputtering, which like atomic spray painting, where here you have 3 materials, and you see there's the wafer and the guns, with the 3 metals, so they can produce these silicon wafers, and then they anneal them, etc. So they can produce lots of materials a day, and they, after this, you are trying to characterize them, so there are different ways of characterization, in particular X-ray diffraction. And this is the Cornell High Energy Synchrotron source. Actually, it's my student there. And basically, you can characterize rapidly thousands of materials, but then the key question is, how can I infer the crystal structure of these materials based on the XRD patterns? And this is really a very challenging task. In fact, they can do maybe 1 or 2 systems a day. No, not a day. Sometimes take, years to solve systems, and sometimes they can't even solve the system. So, I always like defining problems. I'm a computer science, so basically just for you to better understand, now I'm representing this in what it's called the composition space. So you have here 3 materials, aluminum, iron, and silicon, and now you are collecting X-rays. And basically, then you have a collection of X-rays, and based on this collection, you want to produce this phase map. You want to identify the different structures, and which correspond to pure materials or mixed regions. For example, here you have a pure a pure structure, and here you have a mixture of materials. But, you know, again, Aditi, I mean, this, you guys planned this amazing, you know. Yeah, so we, in fact, when we had a very challenging problem, we thought we had discovered 10 new materials. So my colleague, John Gregoire, said, well, Carlos, there's some problem there. So there are serious problems. So, because, you know, they have to be adhere to physics rules. There are thermodynamic rules that are important, and we have to satisfy them. And these are very important because they, you know, the problem actually mathematically is not invertible. So you need to condition better the problem so that you can invert it. So here again I show the problem. You see, you have a bunch of X-ray diffraction patterns, and then you have a mixed phase here, and this phase is a mixture of this and this. So you see, what you want to is you want to identify the phases, but then demix them. Okay, and you use thermodynamic rules and prior knowledge to really help you. But, you know, we are computer science, and if I write about this, you know, probably the paper, I send it to somewhere, they immediately say, oh, this should go to somewhere else. So, but also, you know, it's again this generality and the transferability of AI that is super important. And so, in order to actually make this understand, also my mom, who loves Sudoku, can understand the problem, we came up with a different problem where it is you are given two overlapping Sudokus, and what you want to do is you want to identify the letters and the digits and demix them. So this is crystal structure phase mapping in Sudoku language. But, you know, this problem is actually pervasive, this source separation of demixing, and we are solving many, many problems like this. And it's very exciting because, you know, we are monitoring species. So there's also, your signal now is audio, and you want to identify the elephant calls, the bird calls, etc. So this is also a demixing or source separation problem. Or you want to, you know, there's a music playing, you want to identify the instruments playing. So essentially, these problems are the same. You know, I'm Latin, Portuguese, so I like exaggerating a bit, but it's very close. Okay, so what's the catch here? The catch is this is essentially an unsupervised task. I'm given a bunch of X-rays, and I don't really have data label data to train on. And, you know, I need to deal with noise, incomplete data, uncertainty, etc. And so, and in fact, when my colleague and friend, John Gregoire, talked about this problem, you know, I would say a long time ago, this was music to my ears, because I knew that ML is not good enough. It's still not good enough if you just use the straightforward techniques. And in fact, you know, you need to really be able to capture the underlying physics of the phenomena. So you need to do symbolic AI. And as Jennifer and Chris know, I've done a lot of automated reasoning, even satisfiability. I'm not sure if you even know what it is, but yes, very fundamental reasoning tasks and approaches. So basically what we are doing is really integrating machine learning techniques with symbolic AI, with logical constraint and probabilistic reasoning. So let me now start by telling you how we solve Sudoku and basically how we combine learning and reasoning for discovery. And I'll start by showing this. Can you make sense of these symbols? Well, you see some numbers, you see some letters and some overlapping things, but it's not really easy to make sense of this, correct? But now if I tell you, well, I give you some prior knowledge and they come from two overlapping Sudokus, one using digits, one using letters. Now you see, for example, you say, oh, there's an A here, but you know that you cannot repeat a symbol in a row, column, and block. So then you see there's another A there. So yeah, maybe we know they cannot be two A's there. And by doing this, we actually can, demix, and using this approach, we can actually, by combining deep learning with reasoning about prior knowledge, the prior knowledge here, basically, I mean the Sudoku rules. We know the Sudoku rules, and basically, again, if you recall, this structure really was inspired by the model for DMVP for the birds, where we have an interpretable latent space, and this interpretable latent space actually captures the probabilities of the digits and the shape of the digits that are going to be reconstructed with a decoder. But super important is we have a reasoning module that can reason about the Sudoku rules, and there's a symbiosis. Then you have the deep learning, the encoder and the decoder working together with the reasoning. And in fact, for example, we compare this with, this is all unsupervised. But we compared even with supervised methods, and we outperform not just in digit accuracy, but okay, this is the type from after solving, this here is the real because you have about 300 fraction patterns. I see the position, and this problem has been solved before. And this is the copper vanadium oxide, and these are ideal noise the same. So this is like I will need 2 minutes. Okay. So this is like Sudoku matrix overlapping. These are like what I know about the digits and letters that I use to write that. So, using our deep reasoning techniques, we are able to identify the crystal structures underlying this and demix them. And in fact, here you see the phase regions. It's like the overlapping Sudokus, but here we didn't know a priori this region was explained by 3 phases. So all this was done by, combining the learning and reasoning. And, again, our colleagues, John Bakar, they were able to identify some exciting materials for solar fuels. The structure is, again, very similar. A key issue is these reasoning modules. And again, I make the parallel between the Sudoku and the crystal structure phase mapping. And, we are actually now really estimating the crystal structures embeddings. And as a final bigger picture, we are actually developing this SAR, which stands for Scientific Autonomous Reason Agent, integrating material theory, experiment, and AI. And really, the idea is Sarah is an AI robotic scientist that can, formulate hypotheses, plan, execute, and interpret experiments, and generate new knowledge. And here we actually, you see Sarah, controlling laser spike annealing to synthesize the experiments, collect and interpret the optical data and XRD data. So this is the team, obviously, and this is AI for Science is very hard because you really need to work with different, material science. So my colleagues make all this possible. And we also can solve, for example, medical image. I just want to go to the end. I had big plans. So again, I talked about a lot of topics, and a key issue is this underlying common computational themes. I talked a lot about this pattern demixing, in particular demixing Sudokus or crystal structure phase mapping, and also modeling medical images. And as a summary, I will say this is super exciting. I see this is a two-way street. On one, AI is taking over, so we can provide insights and methodologies to address scientific discovery and sustainability questions, but we get very challenging problems, new formulas and concepts, and we also work with cool people. So it's really awesome. So, and of course, hopefully the bigger picture, we are going to advance AI for humanity. Thank you. And sorry.
Thank you so much, Carla. We're going to go straight into the panel, so if all the speakers want to come up and join me.
Too late, I finished it.
It just started. So we're just going to give you a hint for the next session. Have a seat anywhere you want.
No,
Sorry, it was just her mic was having
so I'm going to, oh.
I'll sit over here.
Maybe, well, maybe. I'll sit over here.
So we have a lot of questions that we haven't answered from the audience on the speaker session. So I think we have some exciting things to take from the audience. I was just going to start out with expressing my admiration for the people that have been given talks this morning, because I think you're all going to Carla's talk, rare species, in the sense that you are willing to bridge different disciplines in your work. You are taking AI for science, talking to experimentalists, trying to make an inroad in domain sciences using a variety of whatever it takes, basically, to make an impact. And that is unusual, especially in our field, where we are typically not rewarded, speaking of merit functions, for being good at a lot of different things instead of really, really deep in one particular area. It's challenging. So I wanted to ask, from your perspective, your very varying perspectives in this arena, what's the biggest challenge and to bridge these different disciplines, and how to make an impact, and where do you see the where should we continue to grow as a community? And that could go anywhere from education to science to community. Who wants to start? Connor.
All right. I think education is a big part of it. So I think increasingly I at least observe students coming into, let's say graduate programs in the physical sciences are interested in understanding, right, how can they start to become fluent in AI techniques? How can they use that in their own research? And often they might lack the sort of understanding of where to get started. And likewise, you see a lot of interest from folks now in pure computer science backgrounds saying, well, maybe I don't want to sell advertisements and optimize that aspect of life, but I want to adapt to AI for science. And I think they equally sometimes have challenges identifying where to really have a foothold and start in this effort. So I think there's an abundance of interest and opportunity, but I think really making sure that you're convening the right people in the right places to identify the right opportunities has sometimes been a challenge.
Larry, you had something to...
Yeah, I think education... Wait, on? Yeah.
Yeah,
okay, good. Education is a big one. I totally agree with that. I think the other thing is, one of the big challenges is getting the right people in the room together. It's really hard, especially when you're starting out, getting involved in the spaces. A lot of times we have a tendency to silo in our different areas of expertise. And to have the opportunity to have, let's say, computational chemists to work really closely with machine learning experts is really awesome. And not only that, but when you have groups that come from different backgrounds working together, is a lot of times their students are involved in that, and suddenly we have students graduating which have expertise in both. And that, I think, has been really awesome for the community. And then to see, like, if we bring these people together and then they try to publish both in the chemistry journals and the machine learning conferences, is we see a better mixture there as well. So it's kind of a cold start problem, I think, initially, but I think we're making really good progress, thanks to everybody here, and seeing a greater cross-section, seeing more students interested in this space and kind of bringing people together.
It takes patience, though. Carla, do you want to?
Yeah, so, I mean, this is, I would say, super rewarding, but super challenging. And it's super challenging because what was mentioned before, it's a super, you really need highly interdisciplinary teams, correct? And essentially, the same way, researchers from other areas, are trying to learn AI, and there are many challenges about that. If us, computer science, if we really want to have an impact, we really need to learn about crystal structure phase mapping, about metabolites, about this, because essentially that was my point. You can't just use a data set and okay, I'm going to use diffusion models, transformers, and blah blah blah. It really doesn't work for AI for science, and that is exactly what attracted me to the field. This idea that you really need to understand the underlying phenomena so that you can reason about this. But that makes it super challenging at so many levels. Larry mentioned, students work for during their PhDs, and then, they take off. So then you need to, train another one from, and it's very challenging to do that. This learning curve, the learning curve for other domains, but it is also, I believe, very challenging for non-computer science because, off the shelf, as Aditi mentioned, they don't work. And therefore, you need to really have a good understanding. The same way, if I tell you, oh, I'm going to start doing nuclear physics, you are going to say, what? That's what I see other disciplines. Oh, I do AI. So it's just, there's a huge learning curve. And I think that's very, very challenging. Obviously, people talked about publication. That is, for example, as part of this computational sustainability, I created, we even have very different cultures, correct? For us, I have to convince my students that a science paper is more important than a NIPS paper, correct? Because, the cultures are very different. And and how do we do this, And then we have a pressure to publish like a thing.
Hold the mic, because the live stream can't hear you.
And I forgot to turn it on. Sorry. That's base, correct? Yeah. So, okay. So, publishing, and then, indeed, there's this tendency sometimes, for example, for us, again, we need to have a novel approach in computer science. So, I mean, maybe there are many, many challenges. Okay, is that better? Sorry.
This point about patience is a really big point, because when we see students come into college to study something, they're studying a specific field, whether it's physics, chemistry, engineering versus computer science, and which field you study often ends up shaping how you think about problems, how you approach new problems. And so to really work at the intersection of these two fields, often you need pretty strong training in both areas. And so I think that's one of the things that we're seeing now, more and more people getting that type of background, but it takes a while to develop, and I guess that's why a PhD is as long as it is in some ways.
May I just say one thing? But no matter what, you know, it is really key. If you are starting and you're excited about this area, you need to find the right collaborators. I mean, that is really like, I've worked, I was telling Christian this, with John Gregoire for a long time, and, you know, the right collaboration. Why do I do work with species distributions? Because we have the Cornell Lab of Ornithology is amazing, or even, you know, so finding the right collaborators and really be, you know, we need to be loyal to the science, not just, oh, I'm going to assume, you know, convexity or blah, blah, just to publish a paper. That's not, does not help your other science, you know, the other science, and it does not help you either, because, you know, for you to advance AI or your field, assuming, you know, like computer scientists, you really need to address the challenge, and there are many in AI for science, and that's why it's so exciting.
Great. Any questions from the community? Oh yes, we have one there, and then one there, and one there.
Hi, I have a question about over technical detail about the physical constraints and inductive biases. So I come from computational science, computational chemistry field, and I find it very hard to convince people to give up in energy conservation or any kind of physical laws. So apparently you have different viewpoints about how to implement those physical constraints. Can you all share a little bit experience about this?
So implementing things like energy conservation can be quite tricky. I think it's one of the things that's really interesting, because from getting a paper accepted perspective, we actually had a lot of issues originally because some of our initial models were not energy conserving, and they would be rejected from conferences because they didn't have that property. And the reviewers were very like, we can't use it, you know, it's not good for MD, reject. Not thinking that it could be useful for other applications like relaxations and that sort of thing, right? So I do think, I think there's a higher level question of how important is it for these models to be strictly energy conserving or strictly equivariant? Because I think there is an opportunity to build models which maybe aren't perfectly strictly having these properties, but maybe they become more accurate, et cetera, because they don't have these like hard constraints. Now, when we talk about actually encoding these constraints, that and making it like forcefully in there, I think that's when it gets interesting in the mathematics standpoint. And like, I'll just give you one example for the energy conserving, is to have higher accuracy, you want your model to be as deep as possible. The more layers you have, the more accurate it is, right? But the deeper it is, it means that when you do that backpropagation to compute the gradients with respect to the forces is a lot more computationally expensive, because you have to go all the way through the network and then all the way back, right? So ideally what you want is like narrow, like you know, shallow networks, is something that's just quite quick and efficient, so that way you can do that backpropagation much faster. So is there a way of making your networks either more shallow, or basically being able to shortcut that, so that way you're computing the gradients with respect to the atom positions higher up in the network. And that way you don't have to backpropagate through the entire thing. So I think it's that inherent trade-off between accuracy and the enforcement of this property, which I think which makes that problem like so interesting. And I think it's completely, I brought it up, I didn't give you any answers because I think it's totally open right now. Like, what is the best way to doing it?
Connor or Anita, did you want to add something to that? Or?
I think some of my priors have actually shifted in the last few years. I think initially it seems really nice to have a lot of these constraints, particularly things like rotation, equivariance, and you know that the neural network must obey this no matter what. This sounds really great from a domain point of view. I think what we've seen in other fields, and this shift that we're seeing really, is that neural networks are really, really good function approximators, and do you really need to build all of that into your network? Why not let the neural network have the flexibility to learn this? And I think this is also where downstream evaluations become super, super important, because you could say, I've trained 2 models, I've done it on this task, and this one was better, therefore constraints are better, or constraints are not better. But if you have, what if that downstream task was not useful at all, not something that people actually care about, which is sometimes what you actually see in these benchmark tables at ML conferences. And so I think that's where it becomes really important to think about, can we do more comprehensive downstream evaluations to actually do a really one-to-one comparison between these different approaches?
Really good point. Okay, let's take the next
May
question.
I?
Oh, yeah, sorry.
Because I really believe that we need to constrain the model. So there may be a little bit of a disagreement, because these models. I mean, yeah, can you learn Newton's law from the data, a ton of data? There are things that that's not how scientists work, correct? They have a priori knowledge and they build on that. And so we do really, in fact, the Sudoku is an example of, a baby example, how you encode constraints, and you are, it is a whole area of how do we encode constraints. And in fact, we actually started with the SAT encoding for Sudoku, but basically we can use entropy-based functions to encode constraints. We can also, worst case scenario, you really need to search, correct? And and in fact, think of AlphaGo. And the difference between, Google and Meta, maybe, was that, Facebook was really trying to solve this just with deep learning. And, Google was, no, we are going to use whatever it takes. And that is by doing search. And when you do search, you can actually force, like AlphaFold also, force constraints to be satisfied. But this is a whole new, a very challenging area, and there are many ways of doing this. I'm happy to talk more offline about it.
Hi, I'm Laura Batten from Cornell. I work with Carla. So my question is maybe the most basic one, which is funding. So there's an incredible amount of science and knowledge going on here, but it's only possible through government funding. Carla's gotten Expeditions Awards. I'm sure, here you are, these wonderful lead institutions, and have received good funding for it. Sadly, the government may look different in 2025. Federal government funding for all the work that you're doing may change. Obviously, I hope it doesn't. But so it's up to philanthropists like Schmidt Futures, who is funding AI for science. Cornell was a recipient of that, and industry. So I'll put Larry on the spot. So here you are up here, the odd man out, right? Not an academic, and funding, presumably Toronto and Carnegie Mellon. So how can Meta and your other companies, like the other Amazon that Carl referred to, and Google and all these places, how can we go to our industry partners and say, please, we need your incredible funding to make this happen?
There's several different types.
You have a lot of billions right here.
Yeah, I have it in my back pocket.
But these companies do have but they do have billions. Maybe you don't, but they do, and they're not funding academia the way that I hope that they would, and hope and make all this possible.
It's very interesting because there's actually many different types of funding. And for instance, one of the reasons why we started the Open Catalyst project and why Zach and I got super excited about it was we felt that there was no government lab or academic lab that could create a data set of that magnitude to study that problem. And that was a unique resource that we had at Meta that we could take advantage of. And Meta is unique in that we are allowed to open source everything that we're doing. So to be able to put that data out there with very liberal licenses, I look at that as a way of funding the community to allow them to do research, because they're doing it, they wouldn't be able to do this themselves. And that was one of the things that got us very passionate about it. Now, when you look at industry, I think one thing that's important to understand is different types of funding are easier to get than others. For instance, us being able to have the opportunity to generate really large data sets, train really big models, and to open source all of this, that funding is relatively easy for us to get. That's something we can take advantage of spare capacity. We are allowed to open source a lot of the data we do. I think it would be good for anybody else to mention to other companies how much you might appreciate open sourcing of data and compute, in case you might want to get data from other companies, etc. And we have the Open Catalyst surface to allow people to try out the models themselves if they don't want to run it locally as well. Okay, that being said, obviously a lot of times people would like to have more funding, just specifically literally the funding, giving universities money to explore these different problems. That is harder. It comes from different budgets, etc. Our team has a certain yearly budget that we utilize, and we obviously use that with our partners. Right now it's University of Toronto, it's CMU, and it was Georgia Tech as well, working on direct air capture. So we use that to fund the partners that we're working with directly, because a lot of the work we do is through academics and the students, because we don't know everything, obviously. I'm not a computational chemist, so it's really important for us to work with leaders in the field to make sure that this is viable. Unfortunately, like going beyond that and funding collaborators that we're not like working with on a day-to-day, I personally do not have that funding, and Microsoft, I think, did a bit more of this back in the day. I'm not sure what they're doing currently right now. Okay, I don't want to say anything.
It was much easier to get funding if you had some Microsoft researcher working with somebody. So
Yeah.
It was more and more restricted, sort of just.
Yeah, so basically it was, well, I'll let you say what it is about. I'm not going to say anything about Microsoft. Microsoft's a great place. I really loved working there. MSR was awesome. And I mean that sincerely. But I think the key thing here is, like the best way is to work with industry labs closely, to have those collaborations. I think it's a great way that we can take the knowledge that the academics have. Like, we hire a lot of the PhD students that we're working with because they learn the ML, they learn the chemistry, they know what we're working on. They're great, they're great hires. So it's great for us to be working with it. It's great to have that knowledge. And I think we should just be more open and collaborating and like talk to Amazon, talk to the other, like Google, other companies about having more open collaborations that we can publish and get that data out there. Because I think that is the key in the long term is actually these collaborations.
We had one question somewhere here. Oh, yes. And then over there. I don't think it's on.
Thank you for all the great talks today. One thing that I'm seeing in common a lot from many of you is these open databases that you've been involved with. Do you have any general advice about starting one of these? Of course, there's flexibility of your schema. How do you solicit contributions without getting spammed with really low quality things? But having done it so many times, like Materials Project, Open Catalyst Project, Open Reaction Database, eBird, these sorts of things, how do you reflect back on it and say what you might have done differently the first time around?
I've been talking a lot.
I think one thing from my perspective at least is trying to ensure that there's clarity on like what is the problem at hand and some focus and scope. I think there have been a few sort of diffuse efforts that I've sort of seen and sometimes been involved with where the value add is harder to articulate than for other initiatives. So I think like the Open Catalyst project is perfect because it's a very clear set of not just data, but the goals and the tasks and the evaluation metrics as well. And I think the sort of sustained support and maintenance is also a really important aspect. And I think we see a lot of open benchmarking and data generation efforts in the field, and then it's one person's passion project, and then that person graduates, let's say. So I think also the longer term commitment, which is harder to do, sort of see earlier conversation about funding, is definitely one of the things that is important to keep in mind for me.
When you create a data set, there's actually 3 things you need to do. One is you need to create a data set, which is the obvious thing, and that's what people think of. And a lot of times, unfortunately, that's what people do, and that's only the thing they do. But the other 2 things that are really important is you need to have really good metrics on that data set to direct people as to what problems they should solve. And that is something you should not underestimate how hard that is. It can take months. Like the COCO data set, 6 months of debating between 10 different academics about what the right metrics are. The OC20 data set, it was similar. We go out to, we talk to many different experts in the field before releasing the data set, and we told them about the metrics to make sure that they were consistent with what they thought would be meaningful. So that metrics is super important. And finally, once you have the data set and the metrics, you need to have good baselines. And this is something that also I think a lot of times gets neglected, which is you need to take the latest models, you need to be very thorough to make sure that you give people a sense for where the current state of the art is, and also give them the code, et cetera, to get started and like amped up on that. So when you make a data set paper, you need to really have all 3 of those things to be successful. And then you need to follow up, you need to do challenges, you need to do all these other things to get the community excited, do the outreach, et cetera. It's not something I would recommend doing this with a team of like 10 people. From all across, like you want these papers to have a lot of authors on them. This isn't, I wouldn't do it with like a 2-person effort, because it is really something you want the community to already be like, I'm so excited for this before you even release it.
Maybe I'll just add to that yes, the maintenance of the data set, also realizing that whatever you produce today may not be state-of-the-art 5 years from now, 10 years from now. You're going to have to update it. You have to inherently hire people that are very interdisciplinary, which speaks to all of the students that are being generated through this community, because they have to have an interest in software. They have to have a reasonable understanding of the domain that they are addressing, right? Otherwise, they cannot be effective. And then the funding, it typically isn't directed in that. So I'd love to have 10 people on my team.
Well, I mean, just collaboration, with other academics, like advising, that sort of thing.
Could I ask a question? Maybe, Kristen, could you tell us a little more about the Materials Project? Because it's an awesome resource. We use it a lot, correct? So I imagine that it's very challenging to keep it, to maintain it, but...
Yeah, no, I've strung together money from 15 different grants over the years, and it's only in the last 2 years that DOE stepped up and paid me $1 million more, so I can pay 4 staff inherently from 1 grant. But through the other 8-10 years since we started, it's been cobbling together and growing it with a lot of what I would call very soft money approaches. And typically, they don't like to pay basic energy grants for something that is very interdisciplinary. I have software engineers working on the Materials Project. It's very strange for BS to pay software engineers.
Yeah.
They're very uncomfortable with it.
But it's an amazing resource.
And I think that's the only reason they keep on paying us, because they see the impact.
And I would stress that indeed having good benchmarks, good data sets, and you outlined the real 3 key ingredients is really awesome. And that's how we build communities. And I keep talking about this SAT community because of Jennifer and Chris. But, so there's this community called Satisfiability that's, addressing foundational reasoning questions in AI. And, back in the 90s, we could solve problems with 50 variables. That was it, But really, the community really, is now huge because everything, all our data sets were public. The code, we had benchmarks, we had baselines, we had competitions, we had everything. And now, software, hardware verification, everybody, satisfiability. Now we can solve problems with millions of variables, and it's just incredible because of, this sharing and bringing together, physicists, computer scientists, you name it, really, mathematicians. It's having these platforms where you can share open source, it's really fabulous, and that's how you grow communities.
Awesome. Alessandra. Yes. Over there.
Thank you everyone for the great talk. I'm Alessandra Lanzara, and I'm an experimental physics and I work in materials. So my question is coming from an experimentalist. And so today, the way we are feeding data, or at least in your model, you are just feeding data, all existing data, published data. You have volunteers that go out and take pictures of birds and so on. And so these are all like passive data that are put into the system. And oftentimes these data are, success stories. We know that our brain will learn things by experiment, and a lot of it is actually through failure. And when we think about materials and material prediction, all the published work is always a story of success. So, there are all these beautiful predictions of new materials that are going to change the world. And oftentimes, I would say maybe the majority of the time, please correct me if I'm wrong, when you actually try to grow this material, ends up in not successful result. So the question is, how can we build a stronger synergy between experiment and AI and machine learning? We know that this works great when we think about the past, I would say 5 to 10 years, the impact that AI and machine learning is having on data you understand it better, and now we are seeing in the past 2 years actually real-time feedback during the experiment. So this is very successful. How can we build a stronger synergy, and how can we implement this very active closed loop between material prediction, material synthesis, and how can we provide more failure result to you guys to predict something that is closer to the reality of what we really need. Thank you.
Yep, no, those are, again, another domain that we need to connect closely with in order to actually make an impact. I think, Connor, you had some examples where you said, like, we need to talk to chemists every single time instead of just predicting.
Yeah, no, I think the sort of close interplay between the sort of design aspect and the experimental validation aspect is super important. I think there's a lot of psychology involved. So I've been part of a number of different collaborations with chemists over the years. And even if we're developing programs to try to recommend new molecules, new reactions, pathways, things like that, experimental chemists don't want to just be seen as service providers. They don't want to make the molecule you suggested. They want to put their own little spin on it. They want to feel ownership over the structure. There's routes for experimental validation that does rely on explicit, contract research organizations that are purely service providers. But I think in like a collaborative academic setting, we need to find sort of better ways of engaging with our colleagues that don't sort of reduce their role to hands in the lab. And I think when you can reduce it to hands in the lab, then you turn to robotics, as Omar mentioned yesterday. You try to think about robotic execution and validation, but I think there's so much human psychology wrapped up in this.
Making sure that we all listen to each other. I think it's very much a two-way street, right? Computational people don't only want to be, oh, please explain what I saw. Right? That's the other side of that coin. We're often, experimentalists come to me and say, oh, I found this, explain why. And I go, nice. So in the same way, experimentalists don't want to be, oh, I'm just your validating, person who's going to make whatever compound you told me to do. So we all, and it's the same thing with machine learning. Carla said that we need this to be challenging from a machine learning perspective, right? Otherwise, we can't engage that community. So it is a lot of psychology and a lot of okay, let's work together instead of just utilize each other. Let's build in those collaborations from the very beginning instead of coming to people at the very end. So yeah.
I really like your point about not having negative data. There's also a repeatability issue, et cetera. And from a machine learning perspective, it is really disappointing because you're like, I need the negatives as well as the positives, right? What am I going to train? And is it repeatable? I do think we are close to an inflection point, though. The experimental labs, et cetera, are getting better and better at doing things at high throughput. It's one of the things we're hoping to do with the University of Toronto, and we're working on that right now to release a large data set. From a machine learning perspective, still be fairly small, but from an experimental chemistry standpoint, it'd be quite large. And one of the things that we're trying to emphasize is the negatives and the positives, release all of that data, and we're kind of making it. And this is where it becomes interesting because we've been trying not to tell the experimentalists which ones we think will work well or not, because we didn't want there to be bias on that as well, but that goes completely counter to what you were mentioning before. So I think it is like getting everybody on the same page to create that initial kind of unbiased data set, if you want to call it that, and then working together after that to then do the exploration and try to find the materials that are truly going to be effective.
Well, I would also, mention that, often what you see is the result of several iterations, correct? For example, I talked about how we solved this amazing system, but, this has been a process. In fact, I've been working on this problem for over 10 years. And yeah, initially the results were very pathetic, I would say, compared. So, it's an incremental process. And, where you go forward and then back and forward, it's really baby steps. And it takes time. And indeed, often we don't publish the negative results because they are not publishable. But you can maybe find a spin. In fact, GANs started because they actually were quite counterintuitive. These generative adversarial networks, correct? It was a failure. They could not. They ended up generating models because they could not really. They realized it was failing. But they found a way of spinning it in a positive way, correct? So, and you know, that's a bit what science is about.
Do we have other questions? Oh, right, over, way back there. Orion.
Thank you all for the talks. So I'm curious in particular about the tension between optimization in the academic setting and actual commercialization. I think everybody talked about the importance of getting this research out into the world to have an impact on climate change. But often something created in a lab, for example, a new drug compound might have downstream toxicity, or an electrolyte additive might actually be too expensive to scale up or be toxic, or a new catalyst might be poisoned in practice. So how do you think about bridging this gap between the metrics that academics are optimizing for in the literature and the actual performance characteristics that become important when you want to put a new technology out into the world?
Yeah, great question. Who wants to? Aditi, do you want to start?
Yeah. I think there's a lot of considerations there, and I think Christine, you have work showing how the battery cycle is extremely, extremely long from when you started in academia versus when you actually get to the commercial level. I think some of that are things that I think get abstracted outside of academia. So if you have a full cycle, those initial kernels and starting something new, academia is a great place to do that. But to go and scale this up and go and build this into actual applications, this is where that full cycle of actually interest in commercial use comes in. And these two things kind of act with each other to form this full cycle. I think probably certain ways to bridge that could be more collaborations or more understanding between the two different areas. So going to the same conferences, going to the same locations. I think this has been fairly successful or starting to be successful in other types of fields. But I think ultimately, like many of the problems here, it also comes down to some level of patience, that this is going to be something that's going to take a pretty long cycle to actually see and actually be certain about when we actually go and use that out.
I would also say, hopefully it can be, apparently there's hard to hear online, so let me know if this is better. I think it's a really good point. It's let's say that we come up with whatever, 10 new materials, and they fit all kinds of good metrics, but they all fail on something that I didn't even consider in my whatever Pareto optimal or whatever merit optimization. So talking to engineers, actually in companies that are the ones that are maybe interested in commercializing that and finding out what is their biggest problem, instead of just being in our academic silos of what can I compute, what can I screen for, then what should I screen for. It could be that it's the property that you didn't suspect that's the killer of most of them, instead of the ones we sort of naively think on day one. So I do think we need closer collaboration. I mean, we keep saying this, closer collaborations between everybody, like engineers, the machine learning people, the software people. At some point, we need everybody in the room. I think that's why everybody keeps talking about Bell Labs, right? Because it was this amazing place where everybody worked together, and now we've separated out these people in different places, and it's not.
Doing that in BIDMaP.
Yeah, so we're trying. BIDMaP is definitely a shining star of like. You have 2 minutes, okay.
And it's an exciting time right now, too, because there's a lot of startup companies in this space right now that you can collaborate with, that they're eager for that collaboration. So that's something that we're looking into and we're currently doing as well to kind of get insight into what happens in that next step. When you do things experimentally, thinking about, is this an industrial relevant experimentation, setup, that sort of thing. I think those are all important, but it is a collaboration, with them that is probably the most important thing.
A good example of that, speaking of toxicity. So I was going to ask Connor if he knows how to screen for toxicity yet when it comes to salmon and people. I don't know. I came up with some new electrolyte molecule some years ago, and it was only by talking to a fellow chemist who took one look at one of them and go, oh, he's very close to sarin gas.
No, it is things like that, and I guess for the students who are in the audience who are listening, I think you'll be surprised how forthcoming company scientists are if you approach them and want to know, like, what are their real challenges and what are their real bottlenecks. People are willing to talk about it, and I think it's only by talking to people in these sort of maybe process chemistry roles for me that you actually learn what the challenges are.
All right. We are very close to, so if anyone wants to, last question, otherwise. Yes, last question.
I'm really glad. So I gave a keynote once at IEEE on brain-machine interface, and I stole something from Steve Jobs, and I said, do you want to be writing research papers your whole life, or do you want to utilize this technology to change the world? And I think you're going to utilize that technology to change the world. So thank you very much for a great presentation.
Great. I think that's a great ending note. Thanks to the speakers.
Hello. Before you all run out, so please be back at 1. And also, we again have the, so for those who were not here yesterday, if you are a graduate student or a postdoc who would like to continue the discussions which are started here, we are helping you to connect to each other. So there is a sign-up sheet outside during lunchtime where you can sign up, and then we'll connect you all to each other to maybe start reading groups or other ways of continuing this discussion.
Sorry, do you know where the laptop is?
On his laptop?
Yeah, I think it's fine. I'm just going to put this one up during the break. This is Carla's laptop. To give that to her. So put this on here. Put this to charge. Okay. Put this on. No worries. Let's turn off the light to get people off the stage.
Yeah, I think that's a good idea. Probably a good like to go for lunch. Right.
I'll start moving the chairs back.
Yes. So, yeah, you know, there's... Yeah. At 3, right? Yeah.
Hello. Hi, everyone.
Supposed to meet.
Can you hear me well? Perfect. Welcome back. Hope you have a nice lunch. We're going to start with the afternoon session. My name is Facundo Sapienza. I'm a PhD student at the Statistics Department, and I'm going to be moderator for the next keynote. So I'm very pleased to introduce our next speaker, Anima Anand Kumar. Anima is currently the Brem Professor at Caltech and works on AI algorithms and their applications to many, many different domains. She's a fellow of the ACM, IEEE, and IIII, and has received fellowship for the Guggenheim, Sloan, Schmidt-Sci, and AI 2050 foundations. She received her Bachelor in Technology from the Indian Institute of Technology at Madras, her PhD from Cornell, and her postdoctoral research at MIT. She has previously a principal scientist at Amazon Web Services and currently a senior director of AI research at NVIDIA. We're very excited to have you. I'm personally excited to hear about your talk. So without no more delays, please welcome Anima to stage.
Yeah. Thank you. Can you hear me well? Yeah. And also good online? I hope so. But yeah, I mean, this is a really, a unique event. The very first time an event of this kind is held at Berkeley. Thanks to Jennifer and Christian, Adrian, everybody here for making this happen. So I'm personally very excited for this session where you'll see the next set of talks about weather and climate modeling and being able to do this very large-scale modeling problems and what AI can bring about as a step change to the way we've been so far grappling with these very large-scale modeling issues. Okay, so my talk is here. I don't know if there is a presenter or do I just do the lab? I don't see. Okay, just the, yeah, got it. So, to me, the questions of bringing AI and science together, really the crux of it is in modeling all kinds of complex phenomena. What I like to think all the way from atomic and molecular scales to planetary scales. You have all kinds of different kinds of processes that occur, and you can, for a lot of them, you may not have extensive data. So we're never going to get internet scale data that we use for training language models in many of the scientific domains. Maybe a few that are large scale, but still nowhere the scale of data that's available for text. So since we don't have data, what else do we have? I mean, we have equations, So we can talk about molecular dynamics and whether in the Newtonian sense or even in the quantum sense, we have equations to model that. If we want to describe processes like clouds and ocean currents, we have Navier-Stokes equation. And so that's the aspect we have that is missing, If you think about standard text and image modeling, here we have domain knowledge, domain constraints like these mathematical equations, typically partial differential equations. But on the other hand, we don't have as much readily available data as in those domains. So that's a major difference, and that's what makes, I think, algorithmic research even more important. So it's not just the story of scale or the bitter lesson you may have been told about AI that anything you can do better, it's through scale and not necessarily through better algorithms. And I think that does not hold here, and that's why personally for me, as somebody who develops AI algorithms, this is a great challenge and a great place to show the impact of new algorithms. So that's one aspect. The other is, why do we need to develop new algorithms, right? So one aspect is data and math or modeling or physics coming together. The other aspect is also looking at phenomena like this. If you think about the planetary scale weather prediction, you cannot just look at it as a fixed set of pixels. I mean, you could because, you can look at what happens to the weather today, and you use it to predict the weather of tomorrow. So that's an image frame. You're predicting the next image frame. So why should it be more than that? That's because different phenomena happen at different scale. For instance, this is something I borrowed from my colleague Tapio Schneider, where, depending on the resolution you look at, you look at our planet, there's completely different kinds of phenomena. There's convection currents that happen at about 25-kilometer scale. So that's if you have grid points that are spaced 25 kilometer apart and cover the whole globe. But if you zoom into finer resolutions, that is, you have closer grid points, then you can model phenomena like storms. And ultimately, if you go to very close grid points, like 100-meter spaced apart grid points, that's when you capture these kind of cloud turbulence. How do these low-lying clouds that you may see outside, how do they form? How do they move, right? So, and that's, in fact, considered one of the biggest sources of uncertainty in climate modeling today, our ability to model this kind of fine-scale phenomena. And so if you were to apply standard deep learning, what does standard deep learning in computer vision require? It requires thinking about pixels of a fixed dimension. And so here the question is, if I take a grid at 25 kilometer and train my model on that grid, then at test time, when I'm doing inference, I'm limited to only that grid points. But that's not how the world works, right? The world doesn't just operate on fixed grid points. The world underneath is continuous. And that's what we want to model, that phenomena that are happening at these various scales, and take into account the effect of all that to ultimately predict weather and climate. So the main difference is weather is usually considered short-term, or what we call medium-range weather forecasts, like 1 to 2 weeks, where there is predictability, meaning we can say with some level of certainty whether it's going to be sunny, whether it's going to rain. But if you're asking about climate, and especially climate change, that's several decades, right? And there we are talking about overall statistics. And so that's the main difference, but it's still the same kind of processes we're modeling in both of them. But yeah, so given that we need to capture this multi-scale phenomena, there are indeed already methods to do it. They're called numerical solvers, right? So they take partial differential equations that model these different phenomena, right? And if you need to get to these phenomena like cloud turbulence, you need to go to very fine scales. And that's the challenge with the current numerical methods, that you're forced to pay this computational cost that just becomes untenable. In fact, these are numbers from Tapio's, really a very nice paper from 2017, where he calculates that if you were to accurately model this kind of cloud turbulence phenomena, that would take about 100 billion times more computing power than what we have today. Even with all the latest advances, if you went to NVIDIA GTC conference, if you listen to Blackwell and all the latest hardware advances, it's great. But we are nowhere close to solving many of the scientific modeling problems, and this is one of them, right? I mean, of course, the other examples are in quantum chemistry, which a number of folks here are looking at, and even there's an exponential growth in the computational requirements as you increase the size of the molecules. And so brute force is out of question, and traditionally the way it's been tackled is through various approximations that are somewhat hand-engineered. It requires a lot of ingenuity and the knowledge of the domain. And the question is, can we augment or find ways to replace that with machine learning, right? And would machine learning do a better job or help us get to a better speed up without paying too much price in terms of the approximation of these equations? And so that's the question. Can machine learning be another tool to help us get to these really fine-scale phenomena, but without paying this price of a very bad computational complexity we see with current numerical methods? And the intuition of why this is even possible is, as we know, deep learning methods, what they're good at is feature learning or feature transformation. So instead of numerical methods iterating on the native grid, meaning you could have a numerical method that just looks at space and time and comes up with grid points and iterates over that. You could learn all kinds of nonlinear transformations through deep learning and potentially come up with a coarser grid that requires far less computation than doing it in the native grid you started with. Right? And that's what we see has been successful with computer vision. Right? So instead of having hand-engineered features, something that was learned by machine was much better with accuracy, with representational power. And so question is, can we bring the same now to the scientific modeling? And that's where, to me, neural operators are that paradigm to answer that question. What I'm showing here is just the concept of what neural operators are able to do. For instance, they can simulate fluid flow like the one you see here with the heat map and any other partial differential equation. But the key is it's not just able to simulate it at one resolution. It can do that at any resolution. Because what it's learning now is not just learning to predict at fixed grid points, but it's learning to even find the interpolation between the grid points as it's doing the learning. And that, to me, is a fundamental difference with neural networks. Right? So neural networks learn mappings between fixed dimensions, whereas with neural operators, we are learning mappings between function spaces. And the other way to interpret this is looking at the energy at various frequencies, which is, wave numbers or frequencies. You can think of them as phenomena at different resolutions. So a higher wave number is a higher resolution or a finer scale phenomena. And during training time, if you only see data of a limited resolution, so I've only been using training data of 64 by 64 spatial resolution. And now at test time, if I ask it to predict what is the energy at finer frequencies or at a higher resolution, a standard deep learning model, like the one here in the red curve, if you try to directly ask it to predict, it cannot because it's limited to that resolution. You could add an interpolation on top, like bilinear interpolation. But the problem is that creates all kinds of distortion, so you can see it deviates quite a bit from the ground truth spectrum of how the energy drop-off happens in fluid flow. On the other hand, with neural operators, not only does it directly have the ability to predict, meaning you don't need to add any interpolation on top, You can directly query the model at any resolution and come up with answers. So you can come up with a prediction. And that prediction happens to be quite good. The blue curve is following the dotted line, which is the ground truth, meaning it's able to do quite a good job at extrapolating to higher resolutions. So what we can think of as a zero-shot super resolution framework and be able to do that quite well. And so that's where neural operators and neural networks are differing in the way they go about thinking of prediction not just at a fixed resolution, but at any resolution. And to me, the benefit of having neural operator operate at any resolution is not only to be able to predict zero shot, right? At test time, you can do a higher resolution prediction. You can further refine that prediction by adding physics. So for instance, with fluid flow, we know Navier-Stokes, we know the equation. So you can add that as a penalty. So in addition to fitting to data, you can also add the knowledge of physics to your learning, what we call physics-informed learning. And in fact, you can impose this physics at a finer scale than the data that is available. So if you now are forced to train only on coarse resolution data, which is typically the case, many times the data you collect is of coarse resolution. Now you can add physics at a much finer resolution through the knowledge of PDEs in this example. And you can do all this in one model, right? So while training, you can now impose loss functions, the data loss at a coarse resolution, and the PDE loss at a fine resolution, all into one model. You don't have to have separate layers for that. You don't have to worry about it, right? You can just input and output any different resolution data and loss functions without worrying about these issues of resolution. So it's both convenient as well as allows the model to distill knowledge of different scales seamlessly into one model and doesn't need retraining every time you change resolution. And with that, in fact, the green curve is on top of ground truth, so you no longer see the ground truth, meaning it's perfectly able to capture the information at all resolutions, right? So in this example, it was able to give you now a high fidelity surrogate for your numerical solver. So it's able to do perfectly fit the ground truth data even when it's trained on limited resolution, because it's able to add in the physics, fill that in to kind of correct the finer scales and give you the right answers. And to me, I think that's the paradigm of physics-informed learning that I mentioned earlier. You cannot just have data alone in lots of scientific modeling. You can add physics. And neural operators seamlessly allows you to do that at multiple scales and resolutions. So I'll get into a bit more detail about neural operators in a bit, but before that, I wanted to show the impact it's having on applications. So this is the weather forecasting model called ForecastNet. In fact, it was the first high-resolution AI-based weather model, meaning a weather model that was trained on to produce global weather forecasts at 25-kilometer resolution, which is considered like kind of with the available open data, that is the highest resolution available. And you can see here, it's able to predict these atmospheric rivers, which are very long-range phenomena, right? These are thousands of kilometers wide, and be able to do that quite well. And it's much faster than numerical weather models, so tens of thousands of times faster. And in fact, you can go to ECMWF and be able to run both ForecastNet and other AI-based weather models and get real-time forecasts for the next 2 weeks. So you can look at how these AI-based models are doing and how numerical weather models that are the de facto gold standard are doing. So you can compare them side by side, and it's running there since, I think, last August or September. So it's had many months of testing, and a lot of weather scientists, I should say, have been quite impressed and even surprised, if they were skeptical before, that not only that it did a good job or as good a job of numerical weather models, but in some cases even did better. There was an article of how Hurricane Lee was predicted like days earlier with these AI-based weather models compared to numerical ones. So, faster doesn't mean a less accurate model. And I think that's the aspect of contrasting and comparing numerical and AI-based weather models. Because with AI-based weather models, we're able to learn from data, right, and overcome modeling errors, whereas with numerical models, you could be forced to pay the price of those modeling errors. And so that's something a lot of people were surprised that it's not only faster, but it's also more accurate in some instances. And these are just some links. The model is fully open source, Apache license, so a lot of startups are building on this. It's available to the community, and I know a lot of people are developing that further. So there's a lot of resources available. And so one thing I wanted to also say is, in addition to neural operators, you can also add in other domain constraints. For instance, the fact that it's a sphere, right? So on the left, if I assumed a rectangle, so I put no spherical constraints, the model just learns from data, it still does a good job for, like, say, 1 or 2 week forecasts. So short range forecasting, it does well. But now if you roll it out, I think here we rolled it out to a year-long forecast. At some point, the small errors start building up and they can explode, and that's what happened on the left. If you assume the world is a rectangle, which it's not, and instead it is a sphere, so we are building in the spherical geometry into the layers of the model as well. And that helps when you want to extrapolate beyond just what it is trained to do, which is only short-range forecasting. And so the spherical geometry helped, and this is Antarctica, so it's a pole distortion is also a well-known issue with numerical methods. So, by the way, all this was with a deep collaboration with people in the domain, weather scientists, people in PDEs and numerical methods. So having that knowledge and bringing that in a way to incorporate issues like pole distortion could help us, not just design for a narrow goal as typically done with deep learning tools, but very broad goals, right? Having models that capture weather and climate in multiple ways. And these models being fast and accurate is also having implications not just for typical weather forecasts, but also extreme weather forecasts. For instance, hurricanes are what we call chaotic, meaning you can not expect to perfectly predict the trajectory of the hurricane, right, a week in advance or so, right, because it can change very fast. It's unpredictable. And in that case, what you can hope to do is not come up with a good deterministic prediction, but instead to come up with good risk assessment. Can I get the probability of it making a landfall in Florida, for instance? And with that, it's a direct implication of human lives, whether you should evacuate, all of these questions you can answer. And so looking at probabilistic calibration of these methods and being able to run a much larger ensemble because it's so much cheaper. In fact, the current weather stations use only about 50 ensemble members to come up with current risk assessment of these extreme weather events. Of course, if I asked you like statistical estimates with 50 numbers, it's not going to be good, right? There are big error bars if you only have 50 measurements, but so far the bottleneck has been the cost, because it takes a huge CPU-based supercomputer to run even one forecast. But now with our model being tens of thousands of times faster, you can just run it on a gaming GPU in your local desktop, right? So it just rapidly shrinks in terms of the hardware requirements, and because of that, now you can afford to run as large an ensemble as you like. Thousands or even tens of thousands of ensemble members you can keep, and so you can do much better risk assessment, and you can really hone in on the tail events and get those probabilities correct by expanding the ensemble that you use for them. So, I kind of like did a detail on weather, but there's so many other examples where neural operators having an impact. Nuclear fusion, we just had a paper in the Journal of Nuclear Fusion where we showed that you can predict disruption early before it happens. This is on the tokamak data, and this way you can prevent, the disruption usually happens in the middle column there, and it can have the ability to damage the reactors. So knowing that early and taking corrective action is important, and these methods are able to do that. They can capture the multi-scale nature of like material deformation. This is ultrasound reconstruction. Again, doing real-time ultrasound reconstruction could be very valuable in many imaging applications. And in all of these examples, they're very fast, right? From high, sometimes tens of thousands to hundreds of thousands, and even 1 million times faster when we look at equations for fusion, because magnetohydrodynamics requires very fine grid with traditional methods. And it's not just for forward simulation, but also for inverse design. So because once you learn this forward model of how a phenomena occurs and the ability to simulate, you can also ask the inverse problem of what is the best way to optimize for certain design parameters. So in this example, we designed a novel way to think about a catheter, which is a pipe which is used to draw fluids such as urine from the human body. But the bacterial contamination is in fact one of the biggest sources of healthcare-related risks in hospitals. And so what happens is, as the fluid is flowing, bacteria tend to swim upstream and infect the human body. And so what we did was a very simple kind of a cheap passive design where we decided to build these triangles or ridges inside the pipe. You can 3D print this, it's passive, right? It just stays in place, there's no movement, nothing. But what is important is to get the right design of those shapes. Of course, if you make it too big, then there's no fluid flow. You cannot stop the fluid flow, right? That still has to happen. But on the other hand, the idea is not to prevent the bacteria directly with that shapes, but instead use those shapes to create turbulences. So if you create these like whirlpools, then the bacteria cannot swim upstream and it's stopped. But how exactly is the angle and the right shape to do that is hard for humans. You know, if I asked you what should be the right kind of shape to do this, I mean, we cannot do this, right? It's a highly nonlinear phenomenon. And instead with now these neural operators, once we asked it to learn how the fluid flow can be simulated for any shape, right? Given any input geometry, what is the output in terms of the fluid flow as well as the bacteria being able to swim upstream. Once we model that, we could then go ahead and optimize directly through the model, because these models are differentiable. So you can ask directly the question of what is the optimal shape that reduces the bacterial contamination to the maximum extent. So we could just do gradient descent and find that optimal shape. And we just needed to 3D print it once in the lab and run these experiments. So the video I'm showing is the actual one in the lab. So it's seen under a microscope and you see these like particles that are pushed out. So it's not able to swim upstream, right? It's just kind of like pushed away. And so you see that only like there's one little thing here trying really hard to swim upstream, if you see. So a lot of it is reduced, and in fact, we could show in the lab that it resulted in 100 times reduction in bacterial contamination. And I think that's, to me, the real promise, this ability to build these digital twins that are much faster with AI, right? You can also design on these digital twins by directly differentiating through them, and hopefully do away with a lot of lab experiments, building prototypes that otherwise would be very expensive. I won't get into the other example, but you can similarly think of mask design and lithography for chip manufacturing also as an inverse design problem. And where do we go next? So far what I showed you were, we used neural operators, but instead of like training, right now we trained it on only one system of partial differential equations, right? Either only weather data or fluid flow data or nuclear fusion data. But what is the analog of a foundation model for physics, for science? I mean, to me, it's one that can not only simulate one phenomenon, but all kinds of different phenomena. Like you should be able to ask, simulate a system with diffusion equation or Helmholtz or different kinds of PDEs, right? And in fact, this was one of the first papers coming out of LBNL. So I was not involved in this paper, but many of our collaborators were, where they showed that neural operators can indeed learn now features that are shared and generalizable across multiple systems of PDEs. And that, to me, is really the future. Like, how do we get to a universal physical understanding by thinking about not just the ability to learn on one kind of scientific data, but data that could look very different across different domains. And to me, the common language that connects them together is math, right? If you can describe mathematical models across these very different looking systems, because the catheter in the pipe is Navier-Stokes, right? The cloud that is up there is also Navier-Stokes. So there's common relationship with data and phenomena that you may think as very different. And to me, bringing that together into one model that can be thought of as a system of partial differential equations and also incorporating that in a physics-informed manner could help us now create models that are broadly generalizable, that can do multiphysics. I'm not showing here, but one of our recent papers indeed was able to simulate even systems that are initially trained on only one system of equations like fluid dynamics, but then there are coupled equations like having an elastic band inside a fluid, right? So this requires both the equation for elasticity as well as for fluid. So you can kind of keep building up that complexity and thinking of now systems that can simulate multiphysics and build it in a form of curriculum learning. And I think a lot of these aspects from language models can be transferred, and at the same time there's so many new unique aspects to be worked on here. So yeah, I think I'm very excited about taking the next steps here from going from systems where we've already been able to simulate design to even more complex and systems and be able to solve problems that were not possible before. Thank you.
Thank you, Anima. That was a fantastic talk. Thank you very much. So now we are going to have some questions. I think we can put some. Yes, we can put the chairs here.
You can even sit on this. I don't know where.
No, that will be uncomfortable. Yeah. So we have one here.
Thank you.
There we go. That was great. I think.
Yeah, I know.
Oh,
this is the light is a bit.
I'm a little farther.
Yeah, that would be better. It's like a blind.
We may actually use it.
Yeah, that is better.
Well,
yeah, that is better.
Okay.
Yes, this
now we
is
can come
better.
back a little bit
Yes,
closer.
yes, exactly.
That was a great talk. Thank you very much.
Yeah, thank you.
I would like to start maybe with a simple general question. So, I love differential equations. I love their theory. I love to solve them analytically, numerically.
Yeah.
So I think I would like to ask you, like, looking at both the past and the future, like, what do you think now these algorithms, like Fourier neural operators, or neural networks for solving differential equations and solving complex inverse problems, what do you think is the reason why we're working on that now? And for example, when I was an undergrad student in physics, we just didn't have these tools.
Yeah.
And how do you think, like, science will look, or for example, like education in 5-10 years from now with these new tools that we're having, like combining differential equations, climate sciences, and machine learning?
Yeah, no, absolutely. I think it's a great time to be working on this from any dimension, right? Either as an AI person, a numerical methods person, a domain scientist. I think because it's really going to get a lot more interdisciplinary, and we're already seeing the beginning of that. And in fact, as we speak at Caltech, we're holding almost a week-long boot camp next week on, hopefully we'll put the lectures online where, it's kind of developing these tools of physics-informed learning, but also, getting everybody up to speed on the software libraries and code and AI frameworks. So you need to kind of now have that knowledge of all of this together. And the question of why now and why bring AI, I think to me the biggest reason is the computational complexity, right? I mean, in fact, since until recently I was at NVIDIA, right, this story is like the CUDA was really developed for science, because NVIDIA pursued graphics accelerators, and sure, right, once that is solved, what next? And then it was all of these scientific problems, and the reason to accelerate them could lead to all kinds of breakthroughs. But really, if you see what happened was hardly much GPU adoption happened in supercomputers. Even the supercomputers built, only the most recent ones have GPUs. And the reason is you don't get a lot of speed up, maybe like 2x, 5x, right? And so you need like technologies that have like these really big speed ups in order to change the way people think. And I think with AI, we are there because we are seeing these speed ups from tens of thousands to even 1 million times. And the reason these speed ups are possible now and weren't before is because with numerical methods, they're iterative, right? So anytime you have a sequential method, GPUs don't give you a big speed up. On the other hand, if you can parallelize it, that's when you get these really mind-boggling speed-ups. And with AI, if we're thinking of now layers that are 4 or 5 layers. So you can think of that just as solving something with 4 or 5 iterations, right, if you make that analogy. Whereas with traditional methods, it could be thousands, right, or even longer to do. And so once we have that speed up, I think we can solve much bigger problems. But the other important thing is the modeling errors that I mentioned. Like a lot of people were very skeptical that you can completely do away with all of the numerical weather forecasts, right? And of course, you still need that for the initial condition, but after that, to get the forecast, it's completely based on AI. And no, we have all this knowledge that is developed. And I think there's still a way to infuse that. But the important thing is the modeling errors. So with numerical methods, we don't have a good way of handling it, right? Sure, you can add like a residual term, but that's still you're making a choice that it's like additive. It's you're making so many choices of constraining what modeling error should look like. And with deep learning, we have complete freedom, depending on how we design these architectures. But these architectures are very expressive. They're universal approximators. So we can incorporate observational data that may be very different from the models. And we know in many cases, like you were saying, even glaciers, some of the details, we don't know what the models are. And so I think that's the aspect. So modeling errors and computational complexity, both AI is a winner.
That's a great answer. Thank you.
Yeah.
I have tons of questions, but I'm going to self-contain myself. So I'm going to invite the audience to make questions. I also encourage students and your researchers to jump in. So maybe we can have the mic here.
Hi. So Ron Cohen from, I work in atmospheric science across a bunch of different departments. I'm curious what you think about the pieces of the weather climate model that attract less attention. So the folks who work on weather are super focused on disasters.
Yeah.
And they don't care much when the winds are slow, which is when the worst air quality is. So I wonder what you see about a path to getting better models at those aspects that affect people's lives but are less dramatic.
Yeah, no, that's a great question. And aerosol modeling, right, it's something also some of my colleagues at Caltech look at. And from what I hear, I think the challenge is also getting measurements, right? You don't have like measurements at a global scale. You have very limited measurements and limited models. And to me, I think that's always the challenge. So, I don't know. First of all, my quick answer is I don't know enough about the domain. I'd love to learn to give a more intelligent response. But to me, I think the aspect is either you should know the model very well or you should have data, right? If you don't have both, it's a hard starting point for AI. Like somehow you need to kind of bring those together. So I don't know in your case if either box is ticked.
There's a huge amount of data.
Okay.
You might say that the absolute errors in wind speed are fixed at 1 meter per second.
Okay.
The relative error when the winds are 1 meter is really high.
Yeah. So if the data is there, maybe the next question is, can it be in a way that's completely curated and made accessible? And the, weather use case, again, I had no idea about weather, right? But it's the people in LBNL at NERSC who are like, oh, there's this data set available, it's open, it's an ECMWF, has the reanalysis data. And so we could consume and do it. I would suggest always the first step is to make the data easily consumable by AI researchers, and usually magic just happens after that.
Any other question from the audience? Maybe they're in the middle. Oh.
Yeah,
it's coming. There we go.
Hi, thank you for your talk. And many of the topics are past my training, but I just want to touch on something you said, where you make a good point that you get really dramatic changes in thinking and public engagement when you get really dramatic changes in capacity. So you said like 10,000 speed up or 1 million speed up.
Yeah.
And then you went on to say that parallelization in the GPU architecture is one of those sources of dramatic speed up. I completely agree. But I think you might have missed one, and that is that in the past when they did either AI logic or physics modeling, there was a great deal of attention on accuracy and accurate models. You wanted correct answers because your peers would not respect answers that were not correct answers. But it seems to me that the paradigm shift in modern AI momentum is that we now use probabilistic answers. And you're developing probabilistic models that give you possible statistically likely answers that comes from the language modeling. And it has spread like wildfire into all the different physical realms. You're getting probabilistic answers that include hallucinations, but the peers are accepting it because it's dramatically different than what has come before. Am I wrong?
This is different from language models. You know, language models have hallucinations because they're trained on all kinds of text, right? Both correct and incorrect, and indeed they give plausible answers. But in these kind of prediction tasks like weather modeling, your goal is still to be accurate. That's your loss function, and you train it to be accurate. So you can come up with now, you know, proof that it's accurate to whatever extent, right, on test data. And it's running now in the real world, and so far there have been no bad misses. In fact, it's the traditional models that have missed some of the hurricanes that these models have been able to predict. So, you know, both empirically as well as in terms of the formulation, I would say this is on solid ground compared to language models, which is a different story.
Nice. I would like to jump in with a question too. I think one of the really exciting venues in this research is like you talk about inverse modeling, and inverse modeling is typically like I really like doing the forward model is complicated. Doing inverse modeling to calibrate parameters or for data simulation is even more complicated. Yes. And something that I pay attention to your slides is like the number of epochs that you needed to converge to something like in the case of the cutter was very slow. Yes. Was very small. Yes. I was wondering if that's like a general pattern, like when you train these models, like doing an inverse pass is very expensive, but you just need a couple of inverse passes in order to converge to something meaningful?
Yeah, so that depends on the problem, right? How the optimization landscape is, so we can't say more generally. But it is true, like if these models have like a landscape in a way, moving through that parameter space is a good one, because, you know, like the way they've been trained, there's lots of nice regularizations, right? Like stochastic gradient descent already kind of gives you, even in the parameter space of the, you know, or the model weight space, nice ways to move about. And so I think that's something of a nice inductive bias that's already there. And the other aspect of like how many iterations it needs is also depends on the complexity. But I would say so, like that there is good inductive bias that does encourage these models to be better behaved, right? It's because with traditional models, first of all, it's not differentiable, so you have to do like MCMC, and that's slow, and each forward run is also slow, so you're kind of paying that double price. So I agree that inverse problems is where you get even further benefits in speed up.
More questions from the audience? Maybe microphone here in front.
Yeah, in the middle here.
Yeah, such a pleasure to be in your talk. I was so wowed by it. This is going to open a rabbit hole of reading, further reading for me. But I've been obsessively thinking about the scale problem, multi-scale problem. Yeah. And let's give me a second. I'm going to read it precisely what I was. Yeah, in the Navier-Stokes equation, for example, is actually, AI has gone beyond that actually. It is considered a millennium prize problem, you know, $1 million question. Mm-hmm. And if you follow closely what's happening with NVIDIA Earth 2 or Google's new model for environmental prediction, they're showing like, you know, prediction power beyond like limits of Navier-Stokes. And also the term all scales, on the one end of the spectrum, things cannot be predicted below 30 minutes or something like that because there's a limit to turbulence. Beyond that, it's all purely noise. Like wind, for example, is in all directions beyond a certain time limit. On the other end, there's something like 14 days, right? Beyond that, prediction is not possible. But arguably, AI is able to abstract things like shapes because Navier-Stokes is limited by the three-dimensional kind of, fluid dynamics, whereas AI can incorporate things like shapes of clouds and so on. So are you thinking about also collaborating with mathematicians to think about the Millennium Prize on the one end and also incorporating and going beyond the Navier-Stokes paradigm?
Right. Yeah, no, it's certainly interesting. So first of all, a few clarifications. The ForecastNet that I mentioned, there was collaboration with LBNL, right? NVIDIA, Caltech, that sparked Earth 2. That's what led Jensen Huang to create Earth 2. So, so I'm very, very thankful for Jensen to support this mission even further. The other aspect is the Millennium Prize. The main difference is we're talking about all this as typical behavior, right? So meaning you have random initial conditions, you come up with the predictions of the trajectory. But the Millennium Prize is about the zero measure set, like can you find one specific initial condition where things blow up? And so machine learning, at least in the standard way, is not good at that because this is like asking something that is so hard to find a needle in the haystack and doing something so unusual like this blow up property. So, but on the other hand, we are working with like Tom Howe, who's one of the professors at Caltech who's done the furthest work to get towards the answer of Millennium Prize. So he's done special cases of those. So there is potential to use this to try and learn different transformations of the problem, right? But I would say it's quite difficult to think of using machine. I don't think machine learning by itself will solve this specific Millennium problem. There could also be the symbolic paradigm of using like lean. There is theorem provers lean, which in a different line of work we've done theorem proving and use language models to be able to prove theorems without hallucination using lean. So you could use that kind of aspects to prove aspects in the Millennium Prize. But that's also, I think, very difficult. So, yeah, you can consider it a very far moonshot. That's where I would place that.
Do we maybe here and then here? Oh, you can go first, and we can go there after.
More efficient. Can you hear me?
Yeah.
Thank you for your talk. That was very interesting. I really was curious when you used the physics-informed neural operator versus just the regular. It did improve the results a lot. What I'm wondering is, what is the computational cost of that, and what is the change in the training regime look like to do that?
That's a great question. So during training, there's hardly any cost increase, right? Because you're just changing the loss function in addition to adding only the data loss, that is, you want to fit the data well. You're now adding an additional penalty term that has look at the PDE and look at how far is my solution with respect to solving, satisfying this PDE equation. But then the other refinement that I didn't get into the detail, it's in the paper, is at test time, now you're given a specific initial condition, so you know what the PDE is for this instance, right? You can plug in the initial condition, you can check for the equation. So you can further fine-tune the predictions given by the model for each instance. So what we call test time optimization. And this is similar to the PIN framework, like the physics-informed neural network, which has no data. But think of it as you're initializing with a really good guess compared to PIN, and then you're optimizing. And so there, depending on the number of iterations, there is some additional cost, but it's still usually much faster. In some of the new ultrasound and photoacoustic imaging work that we haven't yet published, we add this, because adding this test time tuning helps it refine the veins and all those imaging qualities even better. But it may increase the time by a few times, or at most 10 times, but you still have this big speed up before that, so it's a fine price to pay, but a good question. Yeah.
I said the same question.
Okay. Christian has.
So I have a question on your foundation models.
Yeah.
So do you believe that it's also will be universal beyond the equation and the dimension? So do you think you can do sort of a model which can do Navier-Stokes, which is probably in 3 dimensions, versus Schrödinger equation
Yeah.
400 atoms, which is
Right.
in 300 dimensions. Do you think that will be possible, or do you think we need to train really different models?
That's a good question. Conceptually, it's possible, but of course, practically, that's very difficult and probably not where we will start, right? Because the kind of, for the quantum domain, being able to learn good approximations and modifications may look very different from these Navier-Stokes and larger scales. So I think scales that look very different and are very separated, at least in the beginning, I would not try to bring all that together. It's just going to be computationally very expensive because with only limited data, it won't be able to learn enough of those connections.
Or even at the same dimension, if you did Schrödinger in 3 and Navier.
Yeah, I don't think it has...
Or even in the same dimension, you do just Schrödinger in 3 dimensions and Navier-Stokes in 3 dimensions.
Yeah. I think the worry is the common features may not be there, right? What approximates Schrödinger's may look quite different from Navier's. But like Navier and like Helmholtz and a few others, there may be more things in common because they're talking about spatial phenomena. And more importantly, you can do multiphysics there and you can couple them once you learn the same feature space. So there's more advantage to that. Because the reason to do like quantum chemistry and let's say, maybe I would start with molecular dynamics because that's the immediate or one of the immediate scales up, is to then be able to do better protein ligand binding as an example, right? So you don't just incorporate Newtonian physics, but can add some quantum chemistry if you had both in one model. So maybe start with scales that are immediately between each other and or next to each other and try to bring them together into one model.
Yeah, maybe to add something, like I think there is space there in the physics, like to learn like something that is shared, but also probably like in the methods, like when you're trying to solve like different differential equations and traditionally use numerical solvers, like many of the numerical solvers share like same subroutines or strategies that you might expect like something like a Fourier neural operator to learn also that kind of the kind of pattern, right?
Yes, and I think it's more likely that the classical continuum equations share more of it. But although there's been many attempts, and in fact successful attempts to use Fourier neural operators for approximating DFT, including some of the recent works. So who knows, maybe machine learning says there's a lot more in common, right? Because even with language, code looks quite different from jokes, but there is a common model. So I think it's hard for me to give an answer without experimenting this.
May have time for one more question, or maybe two, depending how much time we spend. We have a question there.
Hi, my name is Amit. I'm an investor in climate AI space. So I have actually two maybe practical questions. One is how, like when you're doing these spatial resolutions, you're presumably running a lot of simulations as part of generating your training data. So can you give just some quantification of how many simulations are you running to get enough data where you can actually train a model, and is that very domain specific? Yeah. And I guess the other question is, have you applied FNOs to any domain where it didn't work as well? I mean, we have seen a lot of good examples, but is there any limitation where it doesn't work for certain classes of problems?
Yeah, no, great question. So, of course, for the first, the quick answer is it depends on the domain, but so many of these problems, like of the physical domains, right, have the inductive bias of both. By the way, I mentioned Fourier neural operator, but there's a much more general zoo of architectures. You can add like local convolutions that are working across multiple resolutions, combine it with layers that are FNO. So there's multiple kind of, if I look at that overall family of neural operators, that's quite expressive and general, right? So, and they have good inductive bias. So we've seen like in the fluid flow example, it was only thousands of samples. The nuclear fusion was also, I think, 1,000 or 2,000 samples, both from the camera data as well as the MHD equation. So we did different experiments on that. And the weather data was about 50,000 samples. So all of this you're seeing is so much less than any of the language models that you come across, right? So this is not about the trillion token regime that we are talking. This is still thousands to tens of thousands. But of course, the thing is, each one could be quite expensive to generate depending on the domain. With the weather, as I said, the good catalyst was there was data available, right? And it was in a consumable form. And this is what I advise any domain scientist here to think about, creating data sets that can really challenge machine learning people. And on the second aspect, yes, if you look at specific architectures like FNO, they tend to capture global features well, but smooth out some of the local ones. And depending on the domain, maybe that's important, that's not, right? But if you expand this architectural realm to include parts of the model that can capture local features well, it goes away. So I would say, the main aspect is kind of coming up with the right architecture for different problems. And also more generally, yes, it may be more convenient to just take a standard unit or a transformer if you only care about predictions at one fixed resolution. But I always see that as a starting point, because if ultimately you want to capture the finest scale features for a certain application, you do want that ability to refine and add more information, right? And that's where these models are helpful.
Well, I think we're on time. I just want to thank you one more time. This was an excellent talk, an excellent panel.
Thank you. Thank you for moderating. Thank you.
Chat, or just should we try unmute it? Let's try this.
Yeah, it's fine. It's fine. Is she there?
Yeah.
She's not on video, but that's her.
But can I hear? I mean, without hearing her.
Let me see.
Can we hear her?
Oh, that's her video. Yeah, I think she's there.
Yep, she's there.
Can you hear us? Hi. What should we do?
So he said if you unblank the screen, you just have to hit the blank button and it'll project.
Okay.
So is that what? It's a 2:15 start.
Okay, we can wait.
I would say we need to start crowd herding. I said that to Andre. I was like, oh, I might have to run out and try and herd people back in because that's a really
and
quick.
I think one way is to just
this
start.
is not mine.
Yeah, that makes
That's
sense.
not this one is yours, maybe. Is this the one?
Yeah, that looks nice. See all the bold.
you know it's pronounced as Saukanya? No idea, to be honest. I'll do my best. Because the Indian version is Sukanya, right? But it's muted, so she can't hear us, I think. He asked me to mute this one. Okay, so she can still hear us. Okay. Yeah. Hi, everyone. Guess it's good to settle back in for a great set of next talks. Again, right, dealing with AI for weather and climate, so an area that's very near and dear to me. So we're very happy to have here Saukanya Mautadit. I hope I didn't butcher the name too much. If you can hear me, Saukanya. Oh yeah, I hear that. So she's Schmidt AI in Science postdoctoral fellow at the Department of Computer Science at Toronto. So research interests lie in the intersection, of course, on machine learning and climate modeling, combining statistics, numerical simulations to improve the accuracy of subseasonal weather forecasts, and developing machine learning for parameterizations for subgrid processes in global circulation models. And she earned her PhD in computer science also from University of Toronto. And before that, she got her master's from McGill. And she's organized, or rather co-organized, the Climate Informatics Workshop in 2018 and 2019, bringing people from diverse communities together. She's also won a number of awards for her work on temperature and precipitation forecasting for subseasonal modeling. So yeah, Saukanya, the floor is all yours.
Auditorium.
Can you hear me now?
Yes, we hear you. Thank you.
Perfect. Okay, so hi everyone. Thank you for having me today. I'm going to be talking today about machine learning for improved subseasonal forecasting. And this is work that I've done with many great collaborators over the last 4 years. So first, a general outline for the talk. What I want to communicate today is that Earth system models have demonstrated scale in prediction, and they are continuing to improve their representation of the climate. but there are many issues that remain. For example, the inclusion of important Earth system processes and their interactions. And these issues can result in poor forecasting skill in certain cases. So the point I'm making in today's talk is that machine learning can efficiently improve the forecasting skill of weather and climate predictions. And why does this matter? So what we know so far with certainty is that there has been warming, but there's a lot of uncertainty when it comes to extreme events, especially if we look at regional scales. Global warming can lead to a warmer atmosphere, which can hold more water vapor, which could lead to heavier precipitation and storms. Or global warming may increase surface evaporation in other cases, which could lead to heat waves, droughts, and so on. In addition, there are these underlying modes of variability in the climate system, like ENSO, the El Niño Southern Oscillation. But now climate change could also change these modes, which means that we expect different regions to be affected in different ways. And so if you want to study extreme events, just by looking at the historical record, that's going to be limited because extreme events are rare by definition. And climate change is also changing the distribution of these events. So past statistics alone may not be sufficient for future prediction, but this is an extremely unique field, as we saw in previous talks, where we have access to what is known as climate model simulations, meaning we're evolving millions of variables about the atmosphere and the climate system over time. And this brings us to a really massive data problem, which is exactly where machine learning comes in. And the work I've been doing with my collaborators explores problems at this intersection between machine learning and climate science, including bias correction, downscaling, parameterization, and so on. But for today's talk, I want to focus on 3 problems. In particular, I will be talking about climate simulators, subseasonal forecasting, and bias correction. Now, before we move forward, I want to emphasize another piece of research where we looked at different emerging machine learning-enabled research fields, like bioinformatics, for example, and we identified factors that can accelerate discovery in a nascent field like climate informatics. And the main conclusion of this work was that for any AI or machine learning solution to be truly useful and to be adopted by the climate community, it has to display 4 properties. It must be scalable, considering the volumes of data that we deal with in this field. We want it to be interpretable to enable scientific understanding and scientific discovery, adaptive, so that it's able to respond to the current and future climate change, and finally open source. So our goal is to develop solutions while keeping these 4 properties in mind. All right, so for the first part of this talk, we want to address the following question. Can machine learning improve and speed up numerical weather predictions? So traditionally, weather forecasts are obtained using numerical weather prediction models, or NWP for short, where essentially you gather observations or measurements of weather variables, and you use those to initialize your model. And then the model is run forward. And when I say a model here, the model is not obtained by fitting data, but it's a mathematical model that simulates the interactions between the ocean, the atmosphere, the ice, the land, etc. So each submodel here is a set of PDEs that's discretized and solved using supercomputers. And the current operational NWP, as we saw in Anima's talk, is actually highly successful in generating skillful forecasts, but they're also very expensive computationally. So this is problematic if we want to create ensemble forecasts. If you want to study extreme events like floods and hurricanes, you need large ensemble runs to better estimate the probability of these events. And these large ensemble runs are expensive to generate. And in the last 5 or 6 years, people have started wondering if data-driven models can learn a more efficient representation of these underlying dynamical and physical equations. And eventually, can they provide cheaper forecasts? And we call these data-driven models climate emulators. So here I'm focusing on purely data-driven emulators for medium-range weather prediction. Specifically, we're going to target the range of 3 to 5 days, where the atmosphere shows complex nonlinear behavior, but it's still reasonably deterministic. And we define 2 types of forecasts. The first one is shown here. It's a direct weather prediction, meaning the input to the model is a field or multiple fields on a latitude-longitude grid, and the goal is to predict the same field sometime ahead. The second type is to produce an iterative forecast that's created from data-driven models that were trained on a shorter lead time, for example 6 hours, and which are then iteratively called up to the target lead time, in our case 5 days. So in one of our early efforts, we actually proposed a benchmark dataset to evaluate these deep learning climate emulators for global medium-range weather forecasting. So for that initial release, we used a subset of the ERA5 reanalysis dataset. We used 4 years of data, which we regraded to 3 different lower resolutions. And for the 3-dimensional fields, we selected 13 vertical levels from 1 to 1,000 hectopascal. We agreed on a common problem setup and a simple evaluation metric. We just used the RMSE. And we came up with 2 simple baselines. The first one is a persistence forecast and the climatology forecast. The numerical weather prediction baseline we used was the operational IFS model from the European ECMWF Center. This model was at the time, still is considered the gold standard of medium range NWP. We looked at a simple linear regression and the convolutional neural network with periodic convolutions in the longitude direction. Here I'm showing the root mean squared error for these different models. And you can see here that the NWP model leads with the lowest error, that's the dark blue line here, which was not very surprising considering how simple the other models are. When it comes to the CNN, that's the dots in red, so these are the direct forecasts. You can see that it beats the linear regression forecast for both 3 to 5 days, but when we get to 5 days, using a CNN really is just marginally better than just using a climatology. And then if you use the CNN for iterative forecasts, it performs well up to a day and a half, and then after that, the network's errors start to grow in a nonlinear way. So clearly very poor results from the CNN, but it was a simple network. It was more meant to be a starting point for more complex models. Here I'm showing example forecasts of temperature, and what I want to bring your attention to here is that in the ERA5 ground truth, in this panel on the left, you can see that there's less or there's smaller temporal variability in the tropics compared to the extratropics, whereas the CNN prediction is just an unrealistically smooth field all over. And we suspected that this might be due to one of 2 reasons. The first one could be that the input fields that we used for the CNN baseline model contained insufficient information to create a skillful forecast that would include all the small-scale details. And that the other reason we had in mind is that maybe our lead time of 5 days, the atmosphere is slightly chaotic. And so in face of such uncertainty, the mean squared error loss that we were using just pushed the network to predict the mean of the distribution rather than a realistic realization. Now, since these results came out, the field has progressed very rapidly. So here I'm showing the scale of different climate emulators as a function of their publication time. Here's the scale of weather bench, and this is the scale relative to the physics-based ECMWF baseline. So all the models below this line did worse than the physics-based model. And it's really only in the last year or 2 that we started seeing deep learning emulators outperforming the NWP baseline, which is quite exciting. Quite exciting, but with one remark I want to make here. So all the emulators I showed so far are focused on weather forecasts. So these are the very short-term forecasts that go from 0 to 10 days. And the reason why they typically stop around 10 days is because after that, the scale of the forecast goes down due to the chaotic nature of the atmosphere. Meanwhile, on the other extreme, you have seasonal forecasts. So these are predictions over seasons or years or longer. Sometimes they're just called climate forecasts. And you see a bump in accuracy for these forecasts simply because the thing you're predicting is being averaged over more time. So it's a less noisy quantity. Now, in between, you have what's been called the desert of predictability, where the weather forecasts are no longer skillful, and the climate forecasts aren't good either because you're not averaging over enough time. And these are called subseasonal forecasts. So here you have predictions that depend both on local weather today and on global factors like teleconnections. And our ability to predict for this time scale is just very poor. So next we're going to address this question. Can machine learning provide an accurate and scalable solution to improve the skill of these subseasonal forecasts? So the problem here is that subseasonal forecasts have poor skill. They are practically unusable. And when we started this work, the concern from the climate scientist in our group, Jutta Cohen, was that the community was not making the best use of historical data in weather and climate forecasting. Instead, the predominant paradigm is numerical weather prediction. And just to be precise, when we talk about subseasonal weather predictions, we're talking about predicting the weather 2 to 6 weeks ahead. And why does this matter? Well, it's a time scale that gives us just enough time to prepare and plan for extreme weather events and for anticipated impacts on agriculture and water resources. It also has implications for crop planting, irrigation scheduling, energy pricing, and so on. Now, if all of this is not motivation enough, then there's also this. This is a poster for a subseasonal forecasting competition that was organized by the US National Oceanic and Atmospheric Administration, NOAA, as well as other partners, and that promised 800,000 in prizes. So what is this competition about? It's a year-long real-time competition where we look at 4 separate forecasting tasks: predicting the average temperature and the accumulated precipitation 3 to 4 weeks ahead and 5 to 6 weeks ahead. And the geographical region we consider is the Western US on a 1 by 1 degree grid. Now, the funny thing about this competition was that there was no data provided. Of course, the organizers did identify what ground truth they will be using to evaluate the submitted forecast. But other than this, they didn't provide any data sets. They just said, do whatever you want, somehow forecast the weather, and if you can beat our baseline, then we'll give you some prizes. So the first thing we needed to do was to build a data set. And so we downloaded, we scrapped, we pulled from a lot of different government websites, and we eventually collected a data set that we cleaned up and we released publicly. We call it the Subseasonal Climate USA data set. And it has data on temperature, precipitation, but also on pressure, relative humidity, on some larger scale phenomena like the state of El Nino and the Madden-Julian oscillation. We even have some fine-grained dynamical forecasts included. And so we standardized all these different data sources that had different data formats, many of which we weren't even familiar with before starting the competition. We converted everything into HDF5 files and Panda data frames so that machine learning people could easily use it. And you can access the data set to our subseasonal data Python package. Now, for evaluation, we used the scale. We define it here as the uncentered anomaly correlation between the observed anomalies and the forecast anomalies. And we covered the test period from 2019 to 2020. And what you need to remember here is that with this skill metric, the higher the value, the better. The competition came, of course, with a set of baseline models that included the climatology calculated over 1981 to 2010. We had the Climate Forecast System 2, or CFSV2, which is the main operational US model that's able to predict at the subseasonal scale. And we had the persistence baseline, which is equivalent to predicting the most recent realization of the target variable. We also compared ourselves against state-of-the-art learning models from the literature that were previously used for weather prediction and are based on deep learning, boosting, additive regression models. And now we proposed a toolkit that consists of 3 novel forecasting models. So the first one we call Climatology++. And what it does is it predicts the mean or the geometric median observation in a window that's adaptively selected around the target date. We have what we also call CFSV2++, which is a learned correction for that operational CFSV2 model that I just mentioned. And then Persistence++, where the idea with this model was to learn a combination of physics-based forecasts lacked measurements, and climatology. So this is what we do. Now, what do the results look like? Here I'm showing the percentage improvement over de-biased CFSV2, the NWP baseline. And in this table, each column represents a task and each row represents a model. And we have 4 groups of models: baselines, contestants, learning models from the literature, and our toolkit models. And the numbers in green here show the best performer within each task. And so what we found is that the simple models we introduced did actually very well in all 4 tasks, but especially here where they outperformed the top contest competitors. So we were very happy with these results, but we found that the context of the competition was limited in a sense because it focused on the Western US only. So once the contest was over, we decided to extend the forecasting region to the contiguous US, and we started evaluating over a 10-year period as opposed to only 2 years. We also integrated more granular dynamical forecasts, and we started using an additional metric. So whereas before we used cosine similarity scale, we now consider both scale and RMSE. And finally, if you remember, we want our solutions to be scalable. So it was important for us to focus on the simpler forecasting models that proved to be more accurate. And our suspicion that simpler models would perform best on these new tasks was confirmed by results. So here I'm showing the scale by season for each of the 4 tasks. And the solid lines here represent our toolkit models. And you can see that these models outperform both the baselines and the learning models. And what does this improvement look like? So for precipitation, improvement is especially concentrated over the West Coast. For temperature, it's more uniformly distributed. But in all cases, these models showed better skill than some of the deep learning models like Prophet, this is a transformer model, or Salient 2.0, which is an ensemble of neural networks. In fact, when we compared all models on the newly defined tasks, what we found is that the best performing models are still these 3 toolkit models. So from there, we thought about combining these models together so that you can use these methods to debias not just CFSV2, but any NWP model in the same adaptive way. And so this brings us to our third question: can we enhance the scale of dynamical models to adaptive bias correction? So in this adaptive bias correction method, under the hood, you would have these 3 toolkit models, which individually outperform their respective baselines. And for starters, let's just ensemble these models using a uniform average. And we will refer to this model as ABC for adaptive bias correction. So the idea behind ABC is that it would take as input forecasts from a dynamical model, run these 3 localized statistical corrections, ensemble them, and then output the corrected forecasts. Now, what do the results look like? This is a precipitation scale for CFSV2 without any debiasing applied. This is debiased CFSV2 using the debiasing protocol that's used by NCEP, which is the climate center behind this model. And this is our adaptive bias correction method applied to CFSV2. And you can see here that ABC improves the forecast scale for all 3 horizons. These are the temperature results. Again, the improvement is noticeable, especially as we progress ahead in further horizons like the weeks 5-6 horizon. So we were pretty happy with these results. And when I started presenting this work, people would get excited, but then they would ask, well, how do you compare to ECMWF? Now, if you recall, ECMWF, like I said earlier, is a European dynamical numerical weather prediction model that's considered within the community to be the gold standard. So we applied our adaptive debiasing to ECMWF, and just to have a more comprehensive picture, we also applied it to all the models that are part of the SABEX experiment. And what the SABEX experiment is, it's a climate testbed project that's focused on subseasonal predictions, and it brings together 7 participating global models. So here I'm showing the mean scale of an evaluation period from 2018 to 2021 for ECMWF and for the SABEX models. And you can see that ABC consistently improves over each individual model. In fact, when we applied our correction to the least skillful sub-X model, CCSM4, it became comparable to the world's best model. So we were pretty satisfied with these results, but I want to make a remark here. So the results I've been presenting so far have been assessing the overall model skill that is averaged across all forecast dates in our evaluation period. But there's actually a growing appreciation within the community that for subseasonal forecast in particular, we can also benefit from selective deployment during what we call windows of opportunity. And what I mean by this is that there are periods in time that are defined by observable climate conditions where specific forecasters or specific models are likely to have higher skill than average. And so this brings us to our final question: can we use machine learning to identify these windows of forecasting opportunity? So what we want is a practical workflow to identify windows in time where ABC is likely to improve upon the operational baseline. And the way we proceed is by taking as input the dynamical forecast and the ABC corrected forecast, looking at the skill difference or the skill improvement that we achieve, and analyzing how different explanatory variables are going to impact this skill difference, so that eventually we can answer the question, does the target date we're interested in fall into a window of opportunity or not? But first, the question is, how do we identify these explanatory variables? So ideally, we want to consider the most useful variables or the most important variables. And to identify these, we use the cohort Shapley algorithm. So we compute these Shapley effects where, given the skill difference between the ABC corrected forecast and the operationally debiased forecast, and given a set of candidates' explanatory variables, these Shapley effects are going to quantify how much of the variance in the skill difference is explained by each candidate's explanatory variable. So we applied this to our data, and what we found is that the variables that are most important in our case are the geopotential height, the Madden-Julian oscillation, and ice concentration. And so next, we want to use this information to understand when ABC is likely to outperform standard debiasing. So for example, here we can take a closer look at our most important explanatory variable, HET 500. That's the geopotential height at the 500 hectopascal level. And in order to summarize the impact of this variable on skill improvement, we're going to divide our evaluation period forecast into 10 bins that are just determined by the D size of HET 500. And again, we're going to use cohort Shapley to compute forecast-specific impact values, explaining the skill difference. And within each of these bins, we're going to compute the fraction of forecasts with the positive impact values. And we report this fraction as an estimate of the probability of positive impact. And what we found here is that HET 500 is most likely to have a positive impact on skill improvement in decile 1. And we can take a look at this decile and actually interpret it to feature a positive Arctic oscillation pattern. And it's least likely in decile 9, which features an Arctic oscillation in the opposite phase. We can then take a look at the forecast that was most impacted by HET 500 in decile 1. That's the dates for which HET 500 had the largest impact, and see what the forecast looked like on that date and interpret it. So here, green in these maps, green shows more wet than the mean, than average, and brown is drier than the mean. And what we found is that the forecast that was most impacted was also preceded by a positive Arctic oscillation. And when it comes to anomalies, we found that the ABC forecast replaces the wet numerical weather prediction forecast with a more skillful dry pattern here in the west. And so we go through the same process for all our explanatory variables. Now our next step is to use these identified high-scale deciles to define windows of opportunity for operational deployment. And the idea here is that since all these explanatory variables are observable on the forecast issuance date, one can selectively apply ABC when multiple variables are likely to have a positive impact on skill. and otherwise just issue a default standard forecast. And we call this selective forecasting model opportunistic ABC. But the question now is, how many high-impact variables should we require when we try to define these windows of opportunity? And what we found is that when more explanatory variables fall into high-impact bins, the mean scale of ABCD biased model improves, but the percentage of forecast using ABC declines. So in other words, requiring a large number of high-impact variables will tend to increase the skill gains of ABC, but simultaneously it will reduce the number of dates on which ABC is deployed. So here I'm showing this trade-off, and I'm showing here this opportunistic ABC model as this green line, and you can see that the overall skill of the opportunistic ABC model is maximized when ABC is deployed for target dates with 2 or more high-impact variables, and the operational baseline model is deployed otherwise. So if we make this choice, we're going to be using ABC for approximately 80% of forecast, and the operational baseline for the remaining 20%. So now I can complete the workflow by updating my final question. So whereas before I was asking, does the target date fall into a window of opportunity? Now I can ask, does the target date fall into a high impact bin for at least 2 explanatory variables? So here I'm summarizing the complete opportunistic ABC workflow with all steps involved. And the hope here is that this is going to be a first step in actually opening the black box and explaining how these skill gains that were achieved, how were they achieved, and when are they more likely to happen. And more generally, we just want to make these solutions we're proposing more interpretable to climate scientists. Now, before I finish, I want to go back one more time to this slide, showing the scale of different emulators in recent years. So the scale that's reported here is achieved for short-term weather forecasts that don't go past 10 days. But we still wanted to know how these models would perform if we were to run them on subseasonal timescales. In particular, how would they compare to a very cheap solution like ABC? So we evaluated this DeepMind model here called GraphCast that achieved state-of-the-art scale for 1 to 2 weeks ahead. And we ran it iteratively in a continuous way to generate forecasts for the horizon relevant to us, meaning 3 to 4 weeks ahead. And here's what we found. So GraphCast did worse than the physics-based baseline in terms of RMSE, but it outperforms it in terms of scale. But in all cases, it strongly underperforms ABC ensemble models in both metrics for both temperature and precipitation. So here I'm showing the spatial distribution of the improvements, and dark green here means higher improvement. And it becomes clear for these maps that GraphCast, which showed amazing results for short-term forecasts, actually struggles here to achieve any improvement for subseasonal timescales. And so because of these findings, and just considering how great scale on a certain task or a certain horizon doesn't necessarily translate to a longer lead time, and just more generally considering that these studies, although they showed great promise, they all use slightly different evaluation protocols or different ground truths. So you can already sense here how these differences highlight the importance of really having a common benchmark to compare prediction scale and to make the different algorithms intercomparable.
So can you hear
so,
us? I think we're running out of time, so if we have to finish this. So I don't know if you had just a few seconds or two.
Yes, I just have 30 seconds left. Okay, so to wrap up, I just want to mention that this is where our work is heading next. We are currently early in the process of developing a global open source benchmarking platform for subseasonal forecasting models, and we are welcoming collaborations. So these are other general research directions that we're exploring right now. But if this is something that's interesting to you, you want to learn more, you want to join in, collaborate, I'm leaving this slide here with all the relevant links. And that's all I wanted to share with you today. Thank you for your time, and I'll end this talk here.
Thank you. And so, unfortunately, we don't have time for questions, so we can follow up offline. Very happy to have our next speaker here, Bill Collins. He's the lab director of the Earth and Environmental Sciences at here nearby LBNL, the Lawrence Berkeley National Lab, and also professor in residence at the Department of Earth and Planetary Sciences here at Berkeley. He's an internationally recognized expert in climate modeling, climate change, working on aerosols, greenhouse gases, coupled climate systems. He's a fellow of the American Association for the Advancement of Science, the American Physical Society, American Geophysical Union, American Meteorological Society, a number of accolades, including the AGU's Tyndall History of Global Environmental Change Lectureship. He was the lead author on the 4th assessment of the IPCC for climate change, and that was awarded the 2007 Nobel Peace Prize. And his role as chief scientist in launching the DOE's Accelerated Climate Energy Model for Energy was awarded the US DOE Secretary's Achievement Award in 2015. So yeah, it goes on and on. So before joining the Berkeley lab, he was a senior scientist at NCAR, which is the Center for Atmospheric Research. And he has an amazing career, and look forward to hearing from you, Bill.
Thank you. Thanks so much for the opportunity to speak with you. I'm actually going to be covering some of the same topics, but from a slightly different perspective. And I'm going to give you a slightly less technically oriented talk to put the work that we're doing on climate extremes in a climate relevant context. This is work that I'm doing with a graduate student, Anka Mahesh, who's here with us today, along with colleagues from NERSC, and also critically a team at NVIDIA. And I do want to stress how different climate science is now from when I started my career. I'll come back to this point a little bit later. We are running these calculations at the National Energy Research Supercomputing Center right up the hill. In fact, we did some very important calculations on the problem I'm going to show you that finished this morning. So this is very much hot off the presses. So we are focused in a project that I lead for the Department of Energy on looking at low likelihood, high impact extremes. And I'll come back and describe what those are to you and why you should care about them in just a moment. And we just heard, why the field has taken a long time to evolve to the point where we can begin to study these. I'm going to make the case that we really need to switch to data-driven forecasting in order to tackle this problem. I'll talk about the work that we're doing with NVIDIA, and this is actually work that also involved Anima on using the ForecastNet model as a tool for studying these extremes, and then tell you where we're going next. So as you may know, there's an international assessment process called IPCC that stands for the Intergovernmental Panel on Climate Change. It's basically commissioned by the UN General Assembly through the World Meteorological Organization and the United Nations Environmental Program. And scientists are basically unpaid, we're unpaid consultants who generate these massive reports. And in the most recent report that we issued in August of 2021, we concluded these extremes that occur relatively rarely, but when they do occur, they really can damage infrastructure, are something to worry about, especially if the climate warms appreciably above 4 degrees Celsius. And the list of things we need to be worried about are shown here. Heat waves, certainly more severe atmospheric rivers, the possibility that tropical cyclones and hurricanes might get more extreme, etc. So the question, the challenge for us as a community is that term low likelihood. Why? Because it means that we're looking at things where there's very limited samples in the observational record. There may be one, there may be none. So if we expect that these events are going to become more of a prevalent part of our existence going forward, how do we get a handle on their mechanistic behavior, their drivers, in the absence of being able to look at them actually in the observational climate record. And I'm going to make the case that data-driven climate emulation is essentially must-have, not nice-to-have in this context. To give you a couple of examples, and I'm actually going to be speaking about this in a couple of weeks to the chairperson of NVIDIA when he donates a supercomputer to Oregon State because he's an alumnus there. So this is a heat wave that occurred in 2021. It saw temperatures approaching 50 degrees Celsius over large portions of the Pacific Northwest. It's the most severe heat wave in our recorded records that go back to the late 19th century for this part of the United States. And Anke and I were looking at what else was happening the same day, and it turns out the highest temperature recorded on Earth occurred in Death Valley the same week. So we've just finished running a simulation of this 2-week period, and we're going to go in and dig in and see what we can find about it. But this is one such event that was so severe we could not calibrate statistical models against the observational record to study this particular heat wave. In other words, it broke generalized extreme value theory for all events that had preceded this in the observational record. That shows you how unique and rare these events are. So I'm sorry for the string of acronyms up here. Low likelihood, high impact extremes. This is the Intergovernmental Panel on Climate Change. AR6 is the 6th assessment report. Working Group 1 is the group that studies physics. That was the part that I was concerned with. SPM is a summary for policymakers. What they basically say is that these events can't be ruled out. They're likely to become more frequent when the climate gets warmer. And we have very little confidence in what's going to happen. So that's not good. Something that's bad, and we can't predict with confidence what it's going to do to us. So how do we fix this problem? Well, the way this has been approached in the past, as we just heard, is through numerical weather prediction and climate modeling. So numerical weather prediction field has been around since Lewis Richardson in the UK anticipated creating models with human computers back in the 1920s. And he imagined that he had one person whose responsibility it was for effectively one part of the UK, and he would point at them with a light pointer, and they would sit down with paper and pen and compute the changes in the wind and the pressure and the temperature for that grid point, and then report it back to this massed ensemble of people who were acting as a human computer. John von Neumann anticipated creating the first numerical models of the weather back in the 1950s. And we now have a very large cottage industry devoted to this precise problem. This is, as we heard, the European Centre for Medium Range Forecasting, which is the world's leading NWP center. And the problem they're asked to solve is shown on the left. So we start with essentially an estimate for the state of the climate currently. There's an oval drawn around that because we're not exactly sure what the current state of the climate system is. And then we allow that we run a number of realizations of that climate forward with the idea that if there's some black swan event that's going to occur, one of those ensemble members may hit it. And typically these ensembles that are represented by these white lines going from left to right are typically about 50 or so ensemble members. And then because of the fact that the climate system is chaotic and the model equations are sensitive to the uncertainty in the initial conditions, you get an even larger oval, that gray oval shown on the right, that represents the forecast uncertainty. And this is being run continuously every day. That's what shows up on your phone in the weather app, which is correctly predicted that it's raining, by the way. It was being rained on when I walked over here. This has been a hard slog over many years. Apologies for the quality of this diagram. This is now, of course, dated. But the community has been at this problem for decades, so essentially 4.5 decades up to now. And the skill of the 3-day forecast is approaching 100%, which is really a remarkable technical accomplishment on the part of hundreds of people in person and millennia worth of effort going into these numerical weather prediction models. So this is very nice. And is useful, and we will be using these to calibrate our models. I'm about to tell you why it's not suitable for the problem of looking at low likelihood and high impact extremes, but I did want to give a shout out to the Numerical Weather Prediction Committee and their accomplishments. So let me lead into why this is not adequate. And it's shown with these diagrams, what these diagrams are meant to convey to you is the fact that our ability to spatially discretize the climate system and to resolve finer and finer scale phenomena has been improving with time, so that's good. What's shown here is effectively a factor of 10 improvement from the first assessment report, which was issued back in 1990, up to the sixth assessment report, which was issued in 2021. So that's 30 years and a factor of 10. And second assessment report, third assessment report, I always tell a pun here, which is that the climate scientists weren't smart enough to predict that they were going to need to switch to new nomenclature because first and four both start with the letter F. So they switched from FAR to then putting a numeral after AR, and we're now AR5, AR6. So that's what's going to be a factor of 10 over 30 years. So is that adequate? And the answer is no. So the phenomena that we're interested in studying are shown on the left inside of this diagram. Time runs on the vertical axis, space on the horizontal axis. This is a log-log plot. All the juicy, really concerning phenomena, things like tornadoes, thunderstorms, these low likelihood high impact, well, in these cases these recur fairly frequently, but we're worried about particularly severe instances of these storms. They all lie in the lower left-hand side of this diagram, and then slow variations in the climate system are on the upper right-hand side. So the problem that we face is that we're looking at this single unified climate system, which has energy running both in downscale from large to small scale, but there's also now, and we know for a fact that there's upscale cascades that run from the small scale to the large scale. We're treating this single unified system with a zoo, which is shown on the right-hand side. It's a zoo of models. Climate models, the kinds that I built, are that pink oval on the upper right-hand side, GCM's, Global Climate Models. Again, sorry for the acronym STEW here, but things like CRM, which is that blue oval, that's Cloud Resolving Model. LES is Large Eddy Simulation that's suitable for looking at turbulence in the boundary layer. DNS is Direct Numerical Simulation. So we have a unified climate system and then a non-unified way of looking at that problem. And we need the models that are able to do long-range climate forecasting are sitting, as you can see, a long way away from the phenomena that we need to treat. So that's the problem that we need to crack, and we need to crack it in a hurry. And this, despite the fact that we made remarkable progress, I shouldn't say we really, but the computer industry has made truly phenomenal progress in providing computing resources to the numerical weather prediction community. I think, again, this is a shout out to the progress that's been made. So this is all the way back to sort of the dawn of numerical weather prediction, as I mentioned with John von Neumann, machines that he was asked not to build at the Institute for Advanced Study. The pure mathematicians at the Institute for Advanced Study were extremely skeptical of computing and basically forced him to build this thing in a shed so that nobody had to look at it. But so start with that history all the way up to the present day. Again, this diagram is dated. The compute that landed one Nobel Prize for Suki Minabe in 2021 was a machine that you wouldn't even put into to control a microwave oven these days. And fast forward to today, we've increased computing power by a factor of 1 trillion. That has only bought us 4 orders of magnitude in spatial scale for reasons that have to do with the numerical stability of these models. So we've gone from being global at 30,000 kilometers, decreased that by a factor of 10 to the 4, so 10,000, so we're down to 30 kilometers. That's still not where we need to be. Because Suki Minabe was running models that were effectively a single column representing the entire climate system, which is 30,000 kilometers in extent. So how do we speed up the solution to this problem? Enter data-driven weather prediction and climate prediction. So as we just heard, you can mine the data to train data-driven models that are highly skillful. We have a very long record, 15,000 days against which to train them. What's remarkable is that these can be stood up by small teams of people. So this was done as a collaboration between NVIDIA, Caltech, where Anima was when a lot of this work was done, and other collaborators. This model was constructed by roughly, on the order of about 30 person-years worth of effort. It takes a person millennium to create a climate model. So you're already looking at 1.5 orders of magnitude gain in just the amount of effort required to build one of these things, which is remarkable. As I'm going to show you, the gain in skill has been phenomenal. We saw diagrams that indicated that in the last talk that ForecastNet is inferior to ECWF. That's no longer true. ForecastNet has now broken through that barrier, by the way. So the gain in skill is truly astonishing. Let's start with the issue of spatial resolution, because I just raised that elephant in the room a moment ago. So starting back in 2018, a mere 5 years ago, these models are running with roughly 2,000 grid points covering the planet, when everyone's now running with 1 million. This is trained off the European Center. ForecastNet was one of the first models to get there. That was in 2022. It's just in 5 years, that's a gain of 500 in over 500 in the number of grid points covering the planet. Take the square root of that, you've got on the order of about 25. Over the same time period, numerical weather prediction gained a factor of just 4. So you're already looking at an order of magnitude speed up in the rate at which we're able to acquire spatial resolution with data-driven models relative to traditional numerical weather prediction models. And in fact, the problem we're running into now is that we need data at such a high resolution that we can't acquire it from NWP centers. So we can come back to that during Q&A about what we're going to do about that. So ForecastNet, it's a Fourier neural operator model. The Fourier is really key here. We gain speed up from the fact that fast Fourier transforms are in log n, so effectively linear in the number of grid points over which you're fitting the data. The fact that the model is also based on Fourier transforms of the spatial grid also gives you a modest amount of resolution invariance, which is very nice. The model runs somewhere between 10 to 100,000 times faster than NWP. That's a game changer, as I'll come back to in a moment. It's also greener. It runs at 1/10,000th the power consumption to produce the same amount of prediction. And now is stable rollout to years to decades, and it's open source. So anyone in this room can walk outside after we're done with this model and begin using it. And it's really quite an astounding tool. The reason we adopted it, one of the reasons is that the NVIDIA team, along with colleagues, took this model and torture tested it against the world's leading numerical weather prediction experts at ECWF. And that was the point where I said, okay, they've taken it to the people who are the hardest nosed people in the business. That's the hardest standard you can hold yourself against. I will trust them. And it's turned out that trust was well placed. Like I said, these tools are available online right now, open source. They consist of the training harness and the model itself, this modulus Makani toolkit, and methods for also diagnosing the model and evaluating it against the observational record. I am not going to show you very many technical results in this talk in the interest of making sure that I keep this high enough level so that you can see why we're doing what we're doing. But I'm happy to come back in questions if you want more detail. I'm literally going to show you just one piece of eye candy to sort of motivate the fact that the model is working well. And this would, eye candy tests like this, climate models do this all the time. Guilty is charged. The pictures look pretty, and if you compare these things by eye, they look the same. In the climate community, we call this Chi by eye. But it's not a terribly rigorous test. But what's being shown here is the European Center for Medium Range Forecasting on the lowest row of this diagram, 3 different tropical storms, and then ForecastNet right above it that pretty much nailed the position of the storms with a lead time of 4 days, 96 hours. What we have done, what Ankur and I did, actually motivated by the collaboration with NVIDIA, was we went out and got the diagnostics that the NWP centers use to test the extremes of their own models. We've constructed instantiations of those here, given them back to NVIDIA, so that they're now part of the GitHub repo that NVIDIA maintains. And we now essentially meet almost precisely the same levels of fidelity that the integrated forecast system meets for extremes. And again, I didn't get the slides out of this talk in the interest of keeping it high level, but we can talk about that more offline. So that's great. So we have a model that seems to be fit for purpose of looking at these extreme phenomena. What about it is game-changing? And this is a diagram, thanks to Anima, which sort of shows what would happen if you could sort of start to inflate on an ensemble and then ask, if I just give you one prediction, you might be wrong, right? And what you really want to be able to predict is where might a hurricane go, because you want to warn, might want to warn an appreciable part of the coastline around the Gulf that it needs to be ready and able to deploy resources. And again, this is a figure thanks to Anima, showing the importance of being able to construct larger ensembles. Well, in our case, what we're faced with is a situation where we need to look at phenomena where we literally can't resort to the observational record. We need something else. We need a model that's very faithful to the observational record, but can create essentially events that might have been that we nearly missed. And so imagine, and what I'm going to argue here, and there's some mathematics behind this, is that if the climate system, the atmosphere are truly ergodic, then what ergodicity means is that the climate system will explore the phase space available to it if you give it enough time. What that means is that rather than taking one climate simulation and running it forever, which takes a very long time even in the largest supercomputers that we have, you can chop that time record up and run it in parallel and look at each individual sample, and they're all running in parallel. And mathematically, those two things are equivalent. So the only way we're going to do this is producing a large number of realizations via simulation. And we need to do this orders of magnitude faster than a climate model. So this is why data-driven weather prediction is valuable, and I would almost say indispensable, for studying extremely rare climate extremes. So we want to generate statistics on these things, understand their mechanistic drivers. And there's a whole cottage community in climate that creates these things called LENS for large ensembles. I'm trying to think of a play on hens, so I came up with HENS, which is a huge ensemble. And I went out and then asked several machine learning-based artistic systems to generate pictures of hens sitting on top of a mountain, literally an Everest of eggs. They weren't very good. That's why I'm not showing them to you. But we literally want ensembles that are approaching 10,000 members. We have just run two dates, one for this past summer, one for the heat wave in 2021 with 7,000 climate members. They took 45 minutes on the supercomputer up at NERSC to do that. Truly, astonishing. So we are now running ensembles of 2-week-long hindcasts, and again explaining the fact that we can trade ensemble size for time. This is an example that David Hall and his colleagues at NVIDIA showed at a meeting in Berlin last year. It's for a heat wave that occurred in Algeria, where the heat wave was 51 degrees Celsius. For those of you who don't do that conversion very quickly in your head, that's around 124 degrees Fahrenheit, very toasty. And it exceeded the 99th percentile, and if you run what amounts to a traditional sort of limited number, 50-member ensemble climate prediction for that time period, you might miss this event. But what if you could run 1,000 members, and sure enough, 12 of those ensemble members meet or exceeded the 99th percentile, and actually some of them hit the same heat wave that we saw in Algeria. This gives you, this is a proof of principle that running large ensembles will allow you to look at exceptionally rare events. And we've now started to do that with the 2 huge ensembles that we've run literally in the last week. Our goal, by the way, is to simulate long time periods which were exceptionally hot, and where we just got permission from, I was just reading email that we just got permission from the Supercomputing Center to do this thing. So we're ready to push the big green go button on generating huge ensembles. We're going to have to bend the rules at the Supercomputer Center, but they're going to allow us to bend the rules. Our target is to study the summer of 2023. It's the hottest summer on record, and by on record I mean certainly in the US climate records, which go back to the late 19th century. It may also be the hottest summer since the last interglacial 100,000 years ago, which means it's truly exceptional. We're going to run a huge ensemble for 90 days over this summer. It'll take 3 days to run on a supercomputer, and in that time period it'll generate 2 petabytes worth of output. And that's if we don't save everything. So we are gearing up to run this calculation. I'm really stoked. What this took was, again, teamwork with NVIDIA, with our colleagues in the university system, to effectively copy what took the Numerical Weather Prediction Centers 40 years to develop, which is a means of creating large ensembles. And the way they do this is because the initial conditions, as I described to you, are uncertain. We perturb the initial conditions. We don't know the climate physics exactly, so we have essentially perturbed parameter ensemble for the climate models. And then the third thing that we're going to do, haven't yet, is inject noise during the model integration. This is something that Tim Palmer, who was at the European Center and is actually the first professor ever appointed to both Cambridge and Oxford simultaneously, is a big advocate of, and we now have figured out how to do that. I'm coming to the close of my talk here in case those of you who are keeping time on me are nervous. One of the other things that we are not doing, but colleagues who are at Chris Brotherton and his team in Seattle are doing is now doing long rollouts with ForecastNet for decades. They've trained ForecastNet against an idealized simulation where the boundary conditions are time invariant. And they've been able to show that you can do rollouts with ForecastNet that are decades in length. So what's important here? I've really been focused on looking at these near misses effectively in a numerical weather prediction mode, but on climate relevant timescales. What this allows you to do is to now start thinking about, as we heard, the transition from weather to climate. When I first started talking to NVIDIA, they were parked over, they couldn't go past 4 days. That was, just to give you some sense of the rapidity of the progress, that was 2 summers ago at an Aspen Global Change Institute that I ran with Veronica Eyring, who was the chair of CMIP 6. So from 4 days, 2 years ago, we're now out to 10 years. So that's a gain of a factor of 1,000 in just 2 years. Again, giving you some sense of the rapidity of change. Now broken into the climate regime, and once you've done that, you can now study a whole range of phenomena that are relevant for doing emergency management, making sure that we are safeguarding both the society and the surrounding environment. And this is the team, Chris Brotherton, who literally resigned a plum faculty post at the University of Washington and said, forget it. The future is with machine learning, and has done a deep dive with his colleagues at OpenAI. And similarly, Mike Pritchard, another colleague from UC Irvine, has switched to NVIDIA 80% time because they see where the future is heading. And this is leading now into the climate future, which we can come back to during questions. I think this is a really exciting time for us. We're watching a literal revolution occurring. I'd like to thank all my collaborators, and with that, close and see if we have any time for questions. So thank you. Thanks. I think I left exactly 3 minutes, if I'm keeping time on myself. So, yes, I see a question here. We're gonna mic you.
Sorry. I really enjoyed your talk. There was one slide where you showed the various scales and applications. I think it's the fourth slide from the last.
Yeah.
I just wanted to take a quick picture for the reference. Sorry.
Yeah, sorry. I'm getting, as usual, Microsoft and I are not companionable.
Yeah, this one. Yeah,
this one, yes. So what was your question? So I now repeat it? Okay. So the question was, could I take a picture of this slide? And the answer is yes. So and its sourcing is down here for anyone who's interested. And again, what the graph is showing as a function of both time and decision, sort of your forecast lead time and your decision time, and this gets across the point that we can only beat these phenomena a little bit before they happen to us, right? So we've got a little bit of lead time, but not by much. And so you want this curve to be up and to the right, so it's convex downward and up above the one-to-one line. It's just barely above the one-to-one line. It gives us enough time to kind of get prepared. I see a question toward the...
I already stole the mic, sorry.
Okay, so I'll come to your two questions in just a moment.
Thank you for your talk, Bill. I wanted to ask the question you proposed, which was, what do you do when the resolution at which you'd like to get predictions is stretching the resolution of the observations that you have?
I've already sort of broached the topic, and this is easy to say, but much harder to do. Cut out the middleman. And the middleman is the numerical weather prediction model, because numerical weather prediction, I mean, it's prediction, but it's tightly constrained with observations, right? And so the model is adjusted to look like reality, and the reality is coming from a huge trove of data coming mostly from satellite these days. About 99.9% of the model data using to constrain numerical weather prediction. More than that, actually, 99.99% is coming from satellites. In situ observations are a trivial component into those systems. So the model is tightly constrained, and then it essentially does a physics-driven interpolation on that data, and then we take that physics-driven interpolation and use it to train these models. Why not take out but the underlying data itself, the satellite data, is at 1 kilometer resolution. So just take out the numerical weather prediction model and assimilate the data directly into an emulator. And people are starting experiments with that. There were two questions in the back. Yes, sir.
The research that I'd really like to see is how long do we have to wait until we are capable or we can actually change the outcome with initial conditions? So we can, this is still probably a decade away or so, but we can prevent a hurricane from happening or something using initial conditions, and it's a great calculation. That's something I would work on. And, yeah.
I think you may be waiting longer than a decade on that one. Yeah, there's every time there's a hurricane, someone calls up the president and suggests that they nuke it, and that's a real thing. There are efforts to control weather through that are coming back into fore. They were very popular during the 50s. They're coming back into vogue now, mostly having to do with moving rainfall around. But severe storms are a different animal altogether. The amount of energy in them far exceeds the 17 terawatts that we produce to drive all of human civilization. The storm clobbers that power output. So we're kind of, we're David versus Goliath. There was a question over here. Okay. David versus Goliath, yeah.
Bill, you talked about 2-week simulations.
Yeah.
If you think about seasonal drought and other sorts of flooding that depend on longer accumulation of either dry or wet, where do you see the prospects for being able to do predictions at those scales?
We can do the difference between so there's a subtlety here, which is the difference between a prediction and a projection. Prediction, I would argue, still remembers its initial conditions, right? So it has memory of where it started from. A projection essentially has lost memory. All it knows is that how warm is the climate. It sort of knows about the boundary conditions, but not the initial conditions. We can definitely do projections out to seasonal. The reason why we focused on these shorter range things is that I actually wanted to make the argument that what we're doing was a near miss, right? So it's not, haven't let the model essentially go into a mode of generating its own climate yet. So the reason why we've been focused on there are two reasons. We can show that the model is faithful to reality on these shorter time scales, and we've remembered where we came from. And I don't want to be looking essentially at a climate. When I look at the summer of 2021 in Corvallis, if I go longer than 2 weeks, I'm essentially looking at a climatology for Corvallis, not that summer. So that's the reason why we're hewing to these shorter predictions. But yeah, we can definitely go seasonal and beyond. Great question. I think there was one more question over here. And then
hey, Bill, thanks for a
very
great...
last question.
Oh, last question?
Yeah.
Thanks for a great talk. My question is about, you're training these models on Era 5, right? And that data is generated from a distribution where these low likelihood events are, that distribution is going to change, right, as climate change?
Yes.
So I'm wondering, how are you thinking about dealing with that issue in your approach?
Yeah, so there's I'm going to rephrase your question. The question is, how do you deal with no analog climates, right? Because we've trained against the past. We're very concerned about projecting the future, and the physics in the future is going to look a little different than it did in the past. I mean, the physics is the same. The way it's responding to greenhouse gases is, we sort of have to fold that in. This is a very active area of research, and there are now some techniques that are coming to the fore which try to use physical principles to make the model training data set invariant to climate change, to be continued. So thank you for that question. Thanks. All right, now I'll be back.
So you can save your questions for the panel when we do, after the last speaker, and we'll resume for the last talk at 3:45. Thank you. Great. Yeah, welcome back, everyone. And can we all settle in? Great. Well, last but not the least, we have a very exciting talk by Aditya Grover, again in the theme of foundation models and for a sustainable planet. So he's an assistant professor of computer science at UCLA, and his interests are in generative modeling with applications for large-scale atmospheric sciences. So he has a Best Paper Award at NeurIPS, several graduate fellowships and faculty awards, such as from Google, Meta, Microsoft, Schmidt Sciences, the Forbes 30 Under 30 list, AI Researcher of the Award by Samsung, the Kavli Fellowship by the U.S. National Academy of Sciences, and the ACM Doctoral Dissertation Award. And yeah, so here's to Aditya now.
Thanks, Anima, for that introduction. And thank you all for having me here. Am I audible in the back? Okay, great. So today, being the last, I guess I also get the benefit of being a little bit contrarian. So in a way that I might suggest a push for foundation models with more of computer science than a domain science, but that's just me trying to extend our imagination in one way. So to motivate this talk, well, we have seen from the previous lineup of speakers that atmospheric sciences is really at a pivotal moment. There are headlines which used to be sensational at some point, but now they are almost every day. Some part of the globe is having some extreme weather event. And these extreme weather events have really spanned even locations where you wouldn't imagine. So just 3 weeks back at UCLA, we had the highest ever rainfall ever experienced, to the extent that LA was being compared to Seattle. And that was very offensive to everybody in Southern California. So that's where we are at right now. And naturally, this means we need to do something about it and figure out how we can better handle things related to weather and climate in the long term. Last year was also, and this year as well now, was also a pivotal moment for AI. The headlines were much more optimistic. AI will solve all our problems. AI will reshape how our world is, and so on and forth. And all of this was largely driven by a lot of hype, but also some substance around thinking about a lot of foundation models that came about, beginning with language, now to multimodal scenarios, as well as now thinking about how they'll help us make decisions for a lot of applications. And in all of this, there has also been fantastic achievements in science. AlphaFold is the one North Star that all of us have now started looking forward to in this community for AI for science, how to achieve breakthroughs, and as well as many of the amazing talks today that we have seen are really stretching the capabilities of AI plus science. So with this talk and a lot of my group's research has now been thinking about how can AI bring about a pivotal change to how we think about atmospheric sciences. So my lab, the Machine Intelligence Lab, we think about research at the intersection of foundation models and atmospheric sciences. And for foundation models, my background has been largely with generative models, and now we've been thinking about their intersection with decision making. And when it comes to atmospheric sciences, thinking about forecasting as that one big challenge has been quite a good way to ground a lot of progress in AI, as we also saw from the previous two talks. So this talk will be at the intersection of the two, and we'll start thinking about as what it means to build even an atmospheric foundation model. But even before we can go to the exciting parts, there is this pressing question that gets the two communities in a debate, which is, what is a model? So if you are a computer scientist, and especially in AI, we had some notion of a model from traditional machine learning, where you collect a bunch of labeled data, train any machine learning model, SVM, neural network, to solve a certain kind of a task. And we would do this process again and again for a lot of different tasks, and that's how we would get different machine learning models. It has changed now in some ways. We are now used to this paradigm of foundation models where we would collect a lot of data and use unsupervised approaches to learn a single model that can then be adapted to a variety of different domains and tasks. And this is the paradigm behind the successes that I listed before. Moving over to the atmospheric sciences, where we have model meaning something somewhat different, which is a physical model. And here we are really thinking about systems of differential equations that are governing the flow of matter and energy through the atmosphere. And as the shout out in the last talk was very well placed, this has been an amazing technology. This is what has guided us to make everything from travel plans to having insurance schemes for farmers, and a lot of wealth of applications that are enabled by having very good physical models provide us good forecasts about the weather. And as this plot was also there in the last slide, we can see that over the years, this technology has been improving. But what we have gotten in many decades is skill that lasts up to 3 to 5 days ahead. So anytime you're trying to make a forecast beyond 5 days, it's not going to be as accurate as what we would like to have it in what would be known as this regime of high skill. So let's try to understand why that happens. Well, first, of course, physical knowledge is incomplete at the planetary scales we are interested in. There's also a computational side to it. Running these physical models requires supercomputer level computation to go to finer and finer resolutions. And lastly, there is a little bit of limitation into the scope of these models in the sense of they are designed specifically for doing weather forecasting and climate. And it's a bit, even though a lot of these internal mechanisms that are built into these models could have implications elsewhere. Now with these three limitations, we start thinking the contrast with how computer scientists have begun to think of foundation models. So foundation model performance scales very well with both data and compute. So it's not just more computation will give you better performance, but the more we can collect data, the better we can hope. And there are precise ways that will also come later in the talk of predicting how that performance will change as we build in more data and compute. In terms of how expensive all of this is, it's expensive indeed. There is a GPU rich versus GPU poor distinction being made more and more now. But once you have trained these foundation models, your predictions are very fast and cheap. And lastly, which is why this talk is not just about atmospheric sciences, but thinking about sustainability at large, is once you train these foundation models, you can think about very fast ways to adapt them to a wealth of different applications. So today's talk is going to try to identify what are some very basic primitives that we can come up with and test. We have tested in previous works to build a foundation model for atmospheric sciences. So we will look at aspects relating to data engineering, model pre-training, and finally adaptation as well, which will allow us to build these very generalizable models. To make it a bit more concrete to what we mean by generalization for atmospheric foundation models, we would look at starting with weather forecasting at different time scales. So short range is 3 to 5 days. We'll extend it all the way to 1 to 2 weeks. And then we'll also think about going deeper in space. So weather and climate are inherently space and time problems. So we'll think about how we can improve the resolution of these models if we have some coarse predictions. And finally, we'll think about very long-term periods where we are thinking about trying to project climate under different kinds of interventions. Okay, so with this, there are roughly 3 parts to the talk, and these are just a very biased selection of rethinking the ingredient for what a foundation model would look like. The first part will be on the objectives that we'll use for pre-training an atmospheric foundation model. The second part will think about the scaling we could do, both on the data side as well as thinking about the model design. And the last part will be about fine-tuning. So weather forecasting, if you think about it formally, it's in a sense a time series prediction problem. You have weather at time t, and you want to predict the state of the weather at some h time ahead. And the simplest thing you could do is just predict the current weather as your future. And that's the persistence baseline, which is really good if you care about predictions from minutes to hours ahead. If you want to go in the other extreme, where you want to predict really far ahead, the best thing you could do is to look at historical averages, and that's the climatology baseline. In between is where a lot of magic happens, and that's where you have the numerical weather prediction models doing really well and giving us very non-trivial predictions of the weather, which are better than both persistence and climatology. So when we're thinking about pre-training, we'll use weather forecasting as the pre-training task. This is a first attempt. In the future years, we might think of better pre-training tasks, but this is our best guess for next token prediction. So, and in doing so, we'll hope that at least if you're able to do this well, if nothing, we will be able to extend the frontier of predictability that numerical weather prediction has in this time scale of between hours to 1 to 2 weeks ahead. So, turns out even for weather forecasting, the objectives actually have a spectrum. So if you have the weather at time t and you want to make a prediction at t plus h, you could do a direct approach where you directly map the weather at the future time step ahead. And this is great. It's doing exactly the task you care about. It's very fast to do inference. But it's not super nice if you think about how much of the information it is skipping through. Our data has a lot of information about the path from the current to the target time step, which is being lost in these direct prediction models. So the other challenge is, of course, if h changes, you need a different model every single time. So it's also not super parameter efficient and generalizable in that sense. The other approach, which is more common, is the iterative approach, where you essentially try to break down this path into smaller steps. So these steps could have some size delta. And then you try to predict the weather at t plus delta, 2 delta, and so on forth until you reach your target lead time. So this is more like the autoregressive formulation that has become very common for, let's say, language. This is how also physical models are often rolled out. And it uses the intermediate supervision, but it has some concerns that relate to how errors can compound as and when you are simulating for longer and longer time steps. That is related to also this question of what should that delta really be. So what we did, and one of the very key ingredients which allowed us to really build a generalizable model across time scales, was this procedure of doing randomized forecasting. So the idea here is twofold. The first one is quite simple and intuitive. Instead of fixing your delta, think about delta being a random variable which can take anything from 6, 12, 24 hours. So delta 1, delta 2, delta 3, all of these would look different both during training and testing. And the other thing is, we have to think about the mismatch between training and testing to be minimized. So if we know that at test time we're going to be simulating this system for a lot of different time steps, even during training the model should be made aware of that fact, and that essentially implies that we would want to learn the joint prediction for multiple time steps during training as well. So this is just, if k equals 2, we're not just predicting for the random delta ahead, but we also think about 2 times delta as well. Now with these kinds of changes, we are actually also going towards the regime where the model is becoming more of not a single task, but a multitask model. And from a domain side perspective, it also means that we are going to be learning very different features. So for whether using delta from 6 to 12 hours will correspond to learning day-night cycle features. But when you have deltas on the order of days, then you're learning synoptic scale features which are very different. And presumably, both of these are important when you're trying to make predictions for different time scales. The fact about joint multi-step prediction, which is the second component of this approach, is then trying to reduce the train test mismatch, which in turn will also help us reduce the compounding errors. Now, so this simple primitive, this is the first primitive that we found really useful. So we had this model called Stormer in red, and we first did some ablation studies looking at the impact of both randomization and predicting multiple time steps ahead. And we found that if you look at the RMSC and plot it against the lead time, which is how much into the future we are making a prediction, these changes have a very nice effect on reducing our forecasting errors. Now, going back to the question for the first part of the talk, what happens when you put it in the challenge arena of trying to extend the frontier of predictability? So this is where we looked at the state-of-the-art methods, so Pangu Weather, which was in Nature last year, GraphCast in Science, and we looked at the WeatherBench 2, and here is where the results look like. So again, Stormer here is a method in green, and we are also comparing, besides the data-driven methods, we're comparing with climatology, persistence, and the IFS predictions, which are the ones in deployment right now. And we really see the benefits of these kinds of simple but effective changes. So we see that across the lead times, in the early lead times, as well as the later lead times, we are having a lower prediction error. And more importantly, up to 2 weeks, which is the point at which climatology will end up doing better than most data-driven baselines, we are able to achieve that level of stability up to 2 weeks. Okay, so this was the first part of thinking about what is that pre-training objective for our foundation model, and this is our initial attempt at designing such a pre-training objective. Now thinking about how do we scale these kinds of systems. So here, now if you think about scaling, scaling is a key component of foundation models. So scaling both with respect to data and compute leads to big advances. Here I'm showing you the power law relationship of our language models as we add more data, how performance improves. But scaling also should be with tokens which are diverse. So the plot on the right shows that if you have repeated data sets being shown to your model, there's diminishing returns with more and more data. It's not adding more information. So what does data volume look like for foundation models? And what is data quality as well? Now, this is where there's a big challenge for the field because atmospheric observations are less diverse. In a way, you can think of them as subsets of videos. So it's a movie playing, but this is just a very tiny fraction of all possible movies that could be on YouTube. This other challenge, which is atmospheric science data is highly multimodal. So you have lots and lots of variables and lots of pressure levels, which makes it different from visual data where you might have only 3 or 4 channels for red, green, blue, or the time index. So this necessarily means we have to also then think about new ways of scaling our data, as well as techniques for on the modeling side to embed these kinds of data sources. So what do we have so far? So we have heard this ERA5 data set in the previous talks as well. This is hourly data, historical records from 1979 to present. This is very limited. It's constrained by our ability to sense the atmosphere, so there's some physical constraints to it. And if we do some off-the-shelf, off-the-envelope calculations, we find that ERA5, if I look at all the variables and look at all the time steps, this is about 90 million frames. YouTube, on the other hand, is 13 billion videos. So that's the magnitude of difference we have in terms of the data available for atmospheric sciences versus what you have for, let's say, training a video foundation model. And of course, this ER data is also highly correlated into cross frames, so there's a lot of redundancy as well available here. If you go to an atmospheric scientist, they'll tell you two more limitations. We have a lot of actually predictions before 1979 through historical paleoclimatic technology now. We also have a lot of predictions about the future which are not being incorporated by ERA5. So one of the things we did to improve this data diversity was to combine it with the fantastic simulation models that the climate community has built over the years. So CMIP6 is one of those climate simulation data sets which contains data all the way from 1850 to 2100. So it's more expansive both in the past as well as the future. And it contains a lot of different scenarios of how the climate could change in the future. So there's a lot of diversity that's present in CMIP6, which is not present in ERA5. Now this is good in some sense. It will expand our data set size, but there's also the signal to noise ratio. The simulation data set is based on physics, so we don't really know if it's going to capture the right kind of signal to improve a model which we are designing for weather. We did these experiments and we actually find it to be good news in some sense. It does help. So here we first did some simulation experiments on nonlinear functions. So this is another work, but in the interest of time, I'll just skip to the results that exist for the atmospheric cases. So here I'm showing on the x-axis the size of the data, especially the size of the data as a function of how many simulation data sets you add, right? So, and on the y-axis, we're looking at the same RMSE, the lower the better. And for different weather variables, we see the same story. The more simulation data you add, the performance on the real test set, which is grounded in the real weather observations, is improving. This also occurs for different model sizes. So the different shades of blue are showing the different model sizes. And this performance has been improving with including the simulation data. Okay, so this is good, somewhat good news on how we can use a lot of the weather data that we hear about for the climate community and think about incorporating it for making better weather predictions. The second challenge, and in the interest of time, I'll just talk about what the challenge is and less about the solution, is we have to think about the geometry of the problem as well. So atmospheric data is very complex in the different dimensions where this data could be looked at. So there's a latitude and longitudinal aspect of it, but then we also have dozens of variables for which we are trying to model a joint distribution. Add in time, that's another dimension. Add in the different pressure levels or heights at which we are measuring, and that's another dimension. And suddenly you find there's a big disconnect between the language and vision data sets we are used to versus what atmospheric data set looks like. So we also have come up with a new way of embedding weather data, which is scalable. And in really brief terms, how it works is it first thinks of coalescing all these data sets as independent channels, and then trying to break this down into patches for every channel. So you do actually think about more like a VIT embedding, but you don't collapse the channel dimension. So that's the key difference in the first step. The only collapsing you do later on to permit scalability happens after you have done some cross-attention layers. So this provides to us a right balance of preserving the differences across different weather variables while still permitting scalability in real data sets. And this is just one of these ablations which shows how these weather embeddings are much better substrate than the VIT embeddings. Okay, so the last part, thinking about how do we go beyond just atmospheric sciences to climate and sustainability at large. And this is where we think about generalization, and that's where foundation model has had a big impact. So in an intro to machine learning course, I teach this as train set not equal to test set, but that's really a lie, because now we are thinking about generalization as train and test tasks being very different, and what it actually should be for us to even think of different modalities. So just thinking about the number of different things weather affects in our everyday life, presumably these models should be applicable to those kinds of domains. Think about agriculture, think about insurance, think about all these other places where weather information could be useful in making these forecasts. So we designed a new approach, and here we tested it for emulating climate. And this is the general challenge here, is that we have to make sure we do it in a way that's parameter efficient, not just because it's fast, but it's also going to prevent overfitting. And one of our previous works found that this is actually very much possible within these transformers by just looking at components which are excluding the attention and feed-forward layers. So that's just 0.1% of the parameters, which if we then fine-tune, we found it works really well to essentially generalize across different modalities. So we applied the same idea for climate, and we find that across the different variables that we care about for making climate projections, we find that these approaches, which are parameter efficient, also end up being better than the previous approaches proposed for this kind of benchmark. I will not go into all the other tasks that this foundation model was used for, but just a brief mention, we also forecasting both at a regional, where you have finer resolutions, as well as the sub-seasonal to seasonal timescales that was also talked about. And in the community, now this model has been used for, the model ClimaX has been used for many different kinds of applications. And we ourselves are collaborating with the Institute for the Amazon to better predict land use patterns, as well as with Argonne National Labs for seasonal extremes. So the final technical slide I have is making a pitch for how we should really think about the intersection of AI and atmospheric science as a new form of engineering science. So it is a science in itself to think about these primitives which permit scalability, and these in turn will enable a lot of interesting domain science downstream. And this needs high quality software. So we have an open source library developed and maintained by my students, which is enabling fair benchmarking and rigorous reproduction across a wealth of different tasks in AI and atmospheric sciences. So the bitter lesson is where I guess there's a lot of opinions around this conference, and hopefully it will also come up in the panel. My personal take on this is that I feel we have the chance as a community to go for a bittersweet lesson, where we really think about scale being really important, and that's the driving force for a lot of work that I presented today. But then we might have to rethink the primitives. So it's not going to be maybe the same primitives that have worked for language and vision, which will be the final answer to what scale implies. We might have to redesign those, and we are still in very early days of defining those primitives. So that I'd like to thank my students, especially Tung and Jason, who did most of this work, as well as a lot of funding agencies for supporting it. Thank you.
A couple of questions. I think there.
Hey, hi. Thank you for your talk. So a quick question about a foundation model. So you say basically it's an encoder and decoder, and is this right? And the encoder, you're going to take a different, mostly numerical measurements, and chunk, and you end up with the embeddings, and then the embeddings are read by a decoder, and you said something about fine-tuning. Just really quick, in this work that you're showing here, can you say more in terms of encoder, encodings, decoder, fine-tuning? Can you say about that?
Yes, so we used mostly transformer-based models. So the closest analog you can think of as would be vision transformers based on the nature of data we are operating. And the key differences is to think about whether a linear embedding or a CNN embedding would suffice, because weather is very multimodal. So the encoder needs a little bit of changes that I talked about, but a lot of the self-attention blocks and the decoding could be transferred over directly from what exists out there for transformers.
Maybe just one more and we can soon do the panel. Any other question? Oh, if not, yeah. Yeah, thank you. Yeah. Would you? Or should I like, I think, yeah, maybe this. Okay, yes. Yeah, so I guess the final event for the day, and I think it'll be a great way to, get first of all more questions from the audience, but also many of the, I guess, contrarian views or different views. We can kind of see how to bring that together. So maybe to start off with, maybe Bill, we can, first, talk about what you mentioned about removing the middleman. Let's, I think diving into that a bit more, and how, would that kind of also relate to what Aditya is saying about the bittersweet lesson? Do we just throw away a lot of the hard work that's done in numerical methods, atmospheric sciences, or when you say remove the middleman, is it more like incorporating it in some meaningful ways? So I'm curious what you think, and maybe Aditya can follow up after that.
Can you
hear everyone?
Yeah. I'm deeply torn about this question as a physicist, so it's making me nervous. Let me start with your second question first, right? So we saw a number of talks that looked at the bridge between weather and climate, which is about 2 weeks, and it turns out that nature, for some reason, conspired that the onset of chaos, the butterfly effect, from Lorenz's work on the equations of motion, is 14 days. 14 days is also the time scale on which the global precipitation cycle comes into equilibrium with the transfer of light and heat in the atmosphere. That's known as radiative convective equilibrium. That equilibration is essential to the global hydrological cycle. Everything that you saw today is completely ignorant of it. And so how these models are being skillful in the absence of knowing sort of climate process 101 physics is a problem that I plan to dive into, because the models have learned it pretty indirectly. And so this is, I think, a problem that we need to ultimately confront. It's going to be equally essential, that same physics is equally essential to looking at climate change. So we're going to, it both begs the question of how these numerical data-driven models are skillful on short time scales, but also gets back to climate. This sort of off-the-cuff remark I made about getting rid of the middleman, it's easier said than done. We're seeing early steps here. So the European Center for Medium Range Forecasting is now publishing climate emulators alongside of their operational numerical weather prediction forecasts. And that's remarkable, because you can sort of see how skillful the emulators are relative to a model that, like I said, represents person millennia worth of time investment. I think what we're going to see next, my prediction for the near term, is not getting rid of the middleman, but the numerical weather prediction centers will begin to run two models. One of them is their traditional model, and another is an emulator. And the emulator will be used to inflate the size of the ensemble. And the reason you want to do that is to avoid, there's a sort of egg in your face that happened when all the numerical weather prediction centers missed the hurricane that caused $1 billion of damage to Acapulco last October. So how do you dodge that? You use emulators to look for black swans. So I think there's a mystery in my answer, and there's also sort of some baby steps. Getting rid of numerical weather prediction models altogether is a bigger leap.
Yeah, no, I agree. I mean, because the question of you could just go directly from satellite observations to predictions, right?
Yep.
Do you think we'll have a future where there's absolutely no middleman? And I mean, whether you incorporate physics in a certain way is a question, but end to end, there is one AI model that goes from satellites to predictions. Do you see that happening soon?
Yes, I've experienced it. So when I was working at the National Center for Atmospheric Research, we were using a model that's used very widely, called the Weather and Research Forecast Model, and it makes very skillful weather predictions. It completely botched all the physics about the heat transfer of light and heat. I know because I looked. It was doing wonderfully, making 2-week predictions, but you couldn't use it to do climate to save your life. That's an example of being able to sort of ignore that piece of physics and still be skillful on short-range timescales. So I think there's hope.
But you think for kind of climate change and dealing with climate models, is the middleman there essential, or you think there are ways to kind of overcome that too?
Not sure.
Yeah.
The problem is to sort of translate what we're discussing is this issue of when you are training for a climate with no analog in your training data set. So you're essentially doing an extrapolation.
Yes.
Why do you trust the extrapolation to work?
Right.
That's, I'd say, the sort of the central mystery. Now, there are people working very hard on climate invariant methods for training climate models. And there's been a lot of progress on that. You can re-express the climate system in ways that should be largely invariant. But we're at the infancy of that work. Yeah. So I have to admit, again, as a physicist, I'm kind of at the edge of my comfort level.
Again, we're not asking about loyalty.
David Rolnick, who was at the Aspen Global Change meeting, watched me evolve from being a climate skeptic to at least moderately, emulator adjacent. That took that experience took all of 4 days, and David watched it happen. But I'm still not trying to completely lose my grounding.
I want to turn your question back to you, Arima.
Yeah.
So why are you thinking that if you take your physics-informed, equation-based AI, ML training, you wouldn't be able to sort of go directly from the atmospheric data to a forecast?
I think we should be able to.
Right, because it's not giving up on the NWP. It's just replacing all that brilliance that's embedded in that model with the opportunity for the physics to pull directly on the data in a different way.
Yeah, you have more direct control on embedding whatever physics constraint is needed, right? And to do that in a way that like there's always this trade-off between constraints, like which ones to impose, like you mentioned, and the prediction power, right? Like how do you want to only worry about forecasting well on your training data and validation data, or do you want to also respect the laws of physics? And sometimes that may be in opposition. But yes, we can, and not only in principle. In fact, one of the works that Karthik and others did at NVIDIA was to just directly take observational data and do the predictions, and you can do pretty well on that. So I think there is a future where we will see that.
If I may just add one other comment. Yeah. I mean, I've described this, this is a little bit like being a physicist and worrying and realizing, waking up one morning and realizing that only 5% of the mass in the universe is nucleonic and you can see it, and the rest of it's dark matter and dark energy. You know, I've been talking a lot about the equations of motion, but those equations of motion are driven by things for which we do not have first principles theory. So clouds, aerosols are notoriously hard. The carbon cycle, notoriously hard. All of those things are influencing climate. And we've struggled for decades to figure out how to represent them parametrically, statistically in models. If we sort of, again, skip that whole step and learn how the climate flow acts in the presence of that real world physics, without having to figure out a whole bunch of Rube Goldberg mechanisms that sort of approximate how it's working, maybe that's also a means of cutting to the chase. So that's, getting back to Ron's question, that might also be an advantage. We skip the things that we've been working on laboriously for decades, and there's no promise that we're ever going to reach the right answer anytime soon, and just cut straight to the answer.
At least you have some shortcuts you can explore.
Yeah.
So Aditya, do you think, I know you're kind of like taking the other end of the spectrum where it's fully data-driven, right? No physics constraints. Do you see like kind of, again, of course it depends on the realm of whether it's like short-term weather or climate, or especially climate change, right? There's a number of problems, but do you see the value of adding some kind of physics constraints and other knowledge, and where would that be?
Yeah, I think indeed it would help. So there's two distinctions. One is, of course, like you mentioned, weather versus climate. For weather, I believe you could go directly from satellite observations to the direct forecasts. Climate is where it gets interesting. I think that's where physical constraints will help us define whether we are getting nonsensical predictions from our emulator or whether it's actually going to have some real-world impact and it's reliable. The other main aspect, I think, is I'm not saying that physics is not useful. I think we should think about how it's incorporated within the models. Like, is it the architecture or is it the data? So if you're training on a lot of physical simulation data, you are actually making your model physics informed. It's just through a different route. And I think that's where maybe we can have a community which explores different directions, loss function, architecture, or data, and find whatever works best.
I agree on that last point because, I think, because, a lot of us, we also call it data-driven models, right? But really, we're training on reanalysis data, which means the physics is indirectly incorporated because the data has gone through these physics-based models, and so it's incorporating that. I mean, to me, one of the biggest surprises when we did ForecastNet was that it wasn't just doing well on average weather, but on extreme weather like hurricanes, right? It was able to pick up those signature without seeing a lot of data, but somehow I think, and it would be an interesting question to ask, would that show up in an observational based model versus a data simulated one and a reanalysis one? And so I think that may be a good ablation to do and check how much of the value the middleman is adding, and if there is a way to kind of, still remove the middleman, but train on some more physics-based information that is present in this. So I had one more question, and maybe after that we can take the audience. So I don't know if Bill and Aditya, if you saw like a recent commentary, I think it was Tapio Schneider was one of the authors, where the question of there is one part of the climate community working on getting to the finest resolution, right? Like Bjorn Stevens and the Eve community, where it's like, can we get to kilometer scale, and can we get to really being able to model this cloud turbulence and other phenomena at fine scales? And then there are others who are arguing, instead of spending all our computational engineering efforts to get to the finest scale, why not take the coarser resolution models but focus on larger ensembles? And if you were to pick only one of them, which one do you think is an approach? And of course, with machine learning, maybe there is a way to get best of both worlds. So it's curious what your thoughts are. And
why don't you go? You can take this one first.
Or Aditya, go ahead. Anyway.
Yeah, I think, and here is where if I had to make projections with no bets at all, I would say there's going to be a difference in what would work well in the short term, and I think that would more likely be an approach which is a hybrid, where you get to whatever course or the best finest resolution you can get to in a one shot, and then think of a totally different approach to go to your target resolution via downscaling. So some mix of forecasting and downscaling is likely to work in the short run. But thanks to everything that's happening with compute getting cheaper, with it getting faster, there is a possibility that the route of going towards the finer scales will in some sense maybe automatic, just borrowing a lot of the advancements that's happening in the high performance computing community.
So there's sort of a scientific and a practical argument for going to high resolution.
Mm-hmm.
Let's start with the practical one. People don't live, they live in little tiny zip codes, and you really want to have, presumably you would like to have fidelity at the highest possible resolution in order for that information to be actionable. And as the models I discussed earlier, 30 kilometers, that's 3 times the edge size of San Francisco. So you're not, if you're just in things like the microclimate inside the San Francisco Bay, the best we can do with reanalysis or with climate models is not resolve that, frankly. You might be able to resolve the gradient between us and UC Davis. So that's a practical argument for it. And then the scientific argument is that there is action from the smallest scales to the largest scales. And it imprints on the largest scales, and currently that imprint is absent. The challenge, and this is, I've been around long enough to be in a community that decides to build just the most expensive possible model it could barely run on the biggest supercomputer it could run, and then you find that you're torn between being able to do hypothesis-driven research. And only be able to test one hypothesis because the model is so hideously expensive, or running at lower resolution, and that's also a trade-off. The other, so I'm on longer time scales. I'm actually worried that the ultra-high, we've shown, the climate community has shown that one realization will not capture will do disservice to capturing signal to noise. Because currently the noise is actually big enough. Remember, I told you the system is not completely predictable. The noise will swamp. Whatever that 1 kilometer model does, if you run it long enough, it'll produce beautiful, gorgeous eye candy. It'll be utterly wrong, right? So that's the problem. We have shown that climate predictions on timescales, decadal length climate predictions, can exhibit enormous variability one to the next across a multi-member ensemble that's big enough to encompass the entire Western United States. Some of those predictions actually said that the Western United States should be cooling. And so if you have only one model, and that's the model that you've put all your eggs in that one basket, I'm worried that basket is going to be a limiting factor. So I'm torn. I think this is, to your point, a situation where complementarity is the name.
Ensembles, right?
Complementarity is the name of the game. Yeah. We need to be looking at climate change using every tool we can get our hand on, not one tool to rule them all. To quote the Fellowship of the Ring. So,
right. It's always a challenge with limited resources and which path to take.
And to add to that, I think there is one other point about there could be a natural middle ground if you're thinking about more generative prediction systems. Because I think so in my talk I was saying that model is that contentious word that gets domain scientists and machine learning scientists split. The second word is ensembles. So we have in machine learning community has developed some notions of measuring uncertainty, which to what I can see are actually very complementary but with different names in the climate science community. So whatever we call as model uncertainty becomes structural uncertainty in other community, and then initial conditions becomes data uncertainty, and there's like these mappings which I think as a community now we need to like start resolving and then building methods which are inherently stochastic in nature. And with everything that's happened in generative models, I think that outlook looks quite bright.
Yeah.
I agree. Great. I think we have time for a few more questions. Yeah, go ahead.
Thank you so much. This is a fantastic conversation. I wanted to raise the question of sort of boundaries, especially with some of the branding that goes on sort of implicitly with the idea of, we're going to have digital twins of the Earth. And I think a lot of people outside of the climate science domain don't necessarily know the limits of what a digital twin means. They think of digital twins as something that we can control, we can see fully into all the interstices, right? So I guess, what do you see as the bounds for what should be captured within, your dream foundation models here, recognizing that, for example, if the Amazon is going to become a savanna, then we, don't have a very good idea of how the tipping points there work, what, in general governs land use change, and that there are human decisions, of course, there as well. And some of that is captured in official scenarios, and some of that isn't. And there are just so many data streams coming in, some of them coming from machine learning processing and remote sensing, some of them not. Where do you see being the limit for this single thing that is a digital twin?
David, I thought your question might go in a different direction. One
yeah, answer that one as well.
I mean, I think there's one thing I want to point out, that one other tension we haven't discussed here, that did come up earlier when we talked about who has access to this sort of compute power. Running digital twins is something that's a very much, it's somewhat a matter of privilege. Like who can afford, so Europe just purchased 300 petaflop per second supercomputers. This is not, the US spent, the machine up here is cheap compared to what Oak Ridge and Argonne spent. They spent $500 million apiece in their systems. That's very much a non-democratic proposition when you turn the idea into that we were going to have a digital twin and there's not necessarily gatekeepers to it, but you can't even move that data around the planet to share it, right?
But climate models are already.
I know. The point I was going to say is that the emulators have the advantage that they completely break that. So the laptop that I'm using in the back of the room has 40 GPUs on it. I could be running forecasting on it right as I speak. We haven't figured out how to port it yet or did this yet. But the idea that you can now buy as a commodity laptop a supercomputer that was the number one on the top 500 list 25 years ago is inside a Faraday cage at Indian National Laboratory, guarded by people with machine guns. That's democracy. That's computational democracy in action, and we should be pushing. I would like to see that pushed, so that people can be running these emulators in their home institutions. The data is completely landlocked in the Northern Hemisphere. I know because I've tried to move it. Rather than focusing on digital twins, I'd like to see us get to a place where worldwide people can run these emulators, see what's going to happen to their local communities, share the data with their local communities, torture test what they're being told from the first world. I think that to me is a much brighter future than a future in which we have one master model running on some gigantic supercomputer, in the Swiss Alps. That's not a vision I regard as particularly helpful.
I think it's like AI-enabled
Yes.
digital twins.
Sorry for
right?
that rant, but I just, yeah.
Yeah.
Yeah, okay.
Yeah, I think the digital twin, it's a great example of how, I guess, maybe even in an interdisciplinary world, we are in early stages, so we don't see it, but there might come a time where the hype needs to be separated out from the reality.
Yes. Yeah.
And indeed, like the sounding of it also makes it seem it will solve all problems. Of course, it's not going to do that. This interesting point that you brought up, Bill, about how maybe machine learning is more democratic than what climate modeling used to be.
Yeah.
Anybody could train a neural network. And It's interesting also because I think it was true, but it's becoming less and less true because of the standards of what is a good result or not. So today, if somebody trains a generative model on MNIST, or if you train a weather model on, say, let's say 5-degree resolution, it's very hard to save these results with scale. And I think that's opening up new challenges for the scientific community, that how do universities have that access where they can test their ideas at scales which allows them to also be a part. Because as we go to finer and finer resolution, we might just go back into the realm of some gatekeepers of, earlier it was like these climate models, now it might be some big tech companies which are like gatekeepers of data-driven weather and climate models. So that, I feel like that's a topic of discussion which should also be part of the discussions we're having as a community and with the funding agencies.
So I'm not sure if this is a question for Bill or Anima, but today if I wanted to look at my neighborhood, I would nest a 1 kilometer model in a global model.
Yes.
And I'm wondering what you think about the ability of the global scale models to learn from nesting about processes that scale back and forth at 1 kilometer or even higher resolution than that with a few nests that then allow you to get the whole globe right and to get, without having to run a 1 kilometer model for the whole globe.
I think this is where we're seeing a lot of good benefits, right? Because if you train a global model now at 25 kilometer or so, you can further now train on limited regional data and refine it. But also you could do that for different regions that may not be very well aligned and bring that into one model, right? And we have done the first step, like there are now regional models, for instance, Taiwan, Switzerland, a few of those on top of ForecastNet and other models, you can do it. But like kind of ultimately the goal is if you can bring all those disparate data into a model that could ultimately be fully global and higher resolution. And in a way, neural operators as an architectural framework enables that, right? Because you can distill all that into one model. And of course, it makes extrapolations when it predicts at higher resolution. But you can correct that more natively directly into the architecture. And so I think there'll be interesting ways to explore now further distilling these disparate data sets, limited data sets available at higher resolution into a global model.
So I think we're already seeing what are known as hybrid models. So these are models where that mystery meat I was mentioning on the right-hand side of the equations of motion, portions of that mystery meat are being replaced by machine learning algorithms that have been trained against process models that can actually simulate that physics at the relevant length scale. So for example, boundary layer turbulence, we can afford to simulate that directly in a global climate model, because the physics is occurring at length scales of meters. But we can run LAS models, till we're exhausted, and train a machine learning algorithm on how the boundary layer operates and how it exchanges, mass and energy and greenhouse gases between the boundary layer and the free troposphere, and then incorporate that into a global climate model. One prediction I'm very reluctant to make is when we will start to see this show up in the IPCC assessments. So we had David may remember there were some fairly drunken predictions made at the Aspen workshop by colleagues at another company I won't name about when this would show up. There were some predictions that it might be the next IPCC assessment, but it is coming. And sooner, I think, than the legacy climate modeling community might be comfortable with, but it's coming. And your former colleague, Tapir Schneider at Caltech, has been doing some brilliant work using very surgical applications of machine learning in a really clever way to get at the same question you were asking. How to learn, how to be able to work across scales, but train, actually in this case, machine learning algorithm to predict a parametric representation of the physics we don't understand. So that's an extremely elegant work, and he makes the analogy to Newton's laws of gravity. I won't get into that now.
It's a more local model, and,
Yeah.
and just to clarify, my current colleague.
Yes. Right. Yes.
Yeah.
Sorry.
No.
Yeah. I've been sort of having trouble keeping track of where you're currently. You seem to be.
I'm like a quantum.
Yes. Well, your wave function is hard to localize. Are there other questions for us?
Yeah.
I had a question that it's a bit less technical, but it has to do with kind of the interdisciplinary nature of the field, in that entering the field, one must have knowledge about not only, for example, like building a graph neural network or foundational AI knowledge, in addition to knowledge on either like molecular structures for like a chemistry application or a atmospheric science like background. So given that you kind of must have to be knowledgeable about both of those fields, how do you recommend that someone who is still pursuing like an undergraduate study, like get involved? We were discussing this earlier, but are there like any few like key YouTubers or something that would teach you all the theoretical concepts that would be useful?
Yeah, I think that's a great question. And to say something again controversial, I feel, or maybe not so much, but I think competitions is a very big tool of advancement. And we have seen a lot of examples. So Carla mentioned about the SAT competitions. Larry has been running Open Catalyst, and that has a NeurIPS competition for many years. And in all these competitions, you could think of the problem as some input, some output, and just maybe learn a mapping. That's not the best way in the long run to make impact, but as a starting point, I feel that simplification is actually a good way to start from somewhere and explore the field and learn some tools. And often that has been the basis for, even in my group and some of the applications we have looked at, that has been the basis for then future collaborations with domain experts. YouTubers, I am not very familiar with.
Take the courses here.
Somebody with a mic.
Yeah, so the data science courses here in Berkeley and the new data science college. So, yeah, thank you, everyone. Sorry,
I just wanted to. Do we have time for one last word here? Because I think that's a great question.
Let's.
So I did want to respond to your question, and it's I have learned the hard way that it's not what you know, it's how you approach a problem, right? So it's pivoting from what you know, because that's basically a bottomless sink, right? I'm never going to know enough. It's a large part of being successful is how you approach a problem. So to just leave this thought with you, there's essentially, think about, there being a sphere of knowledge, and where you want to be is at the perimeter between that sphere, the known and the unknown, and then ask, why is that boundary not moving faster? And then ask what you do to move that boundary faster. Mm-hmm. So if that's the way that you sort of encode, an attack on the problem, then actually it turns out that you can do a lot with actually on the basis of just being able to ask the right questions. Mm-hmm. Is about I found about 95% of the battle. To be honest with you, it's not knowing something; it's knowing what to ask.
Mm-hmm. Yes.
Okay.
Yes.
Yep.
Really wise words. Yeah. Thank you, Bill. Thank you, Aditya. Thank you. Thank you. And I don't know if you want to say the last words.
Okay, so with that we go to our social part, but before that I want first to thank sort of our current panel, obviously, you for being the panel leader, and our speakers, the speakers of all today's, the panel leaders. But I think we would really go amiss if we didn't thank everybody who has been working in the background. You want to start with the organizing committee? No?
No, go ahead.
Okay, well, I will not start with the organizing committee. So I want to thank sort of all our helpers in the back. I think the people who probably, the person who did really most of the work and probably had the most stress that this might not work and is probably the happiest that it has worked is Adrian. Adrian, could you stand up? So a big applause for... Okay, so this wouldn't work, would never have happened without Adrian. Adrian got help from Danielle. Where's Danielle? Okay, Danielle, you have seen...
You can still hear us.
So, and then we have a gazillion helpers. So from, I will not do all the last names, but people could stand up. Kevin?
Stand up, stand up.
Stand up. I don't know whether Shoshi is here today. No? Okay. Anika, is she here today? Nakul is here. And so is Theo. Samul, where's Samul? Sumil, sorry. And Xing Shao. And then is Philip here? No? Okay, Greg, who has been helping in the background, is Greg here? He's outside. And finally, Olivia.
Who is over in CCI virtual land. So thank you very much, Liv.
Okay, and then we have the organizing committee, which I let, maybe you take over now.
Sure. Is this microphone working? Oh, it is, great. So huge thanks to Jennifer and Christian for all of your work in this. And then to Maria Joao Sosa and Priya Donti at CCAI for helping conceive all of this together. It's been the work of many months iterating on this and putting together a speaker list, crafting the organizational structure, and there has just been a lot for all of us. So really, thank you to everybody for.
Well, I want to actually chime in to thank Olivia, both of them, Maria and Priya, who really started this very early with Adrian, I don't know, probably a year ago almost. And I think probably before we had anybody else of the organizing committee, when we had maybe Jennifer and Adrian had the idea, and sort of but we started working with, I think first with Priya, Maria, one of the two of them,
first with Priya.
early on. So they have been, unfortunately not here, but helping a lot getting this going. So thank you so much. Oh, David, and David, of course.
I was looped in later.
Good. And with this, I think we...
I want to say one thing, may I? Okay, I want to thank all of you for being here. I am really excited about this community, okay? This is giving me great hope because we're bringing together people from very different backgrounds who a few years ago were skeptical of each other and of each other's methods, and I just think it's really exciting. I'm thrilled to see AI for the physical sciences really blooming here at Berkeley and much more broadly. And we have to find out ways to stay in touch, to keep working together, to have ways to bring our undergraduates and graduate students and postdocs together so that they will become the new leaders of this field, and they will not struggle as we did with only knowing this or only knowing that, but knowing how to ask the right questions, which you all still must learn, and many of you are doing very well at that. So thank you. Let's try to find a way to keep meeting in some random fashion, and let's work with each other.
It's always stochastic. Thank you.
Check, like, I'll close all the presentations. Right. I'll close all the presentations.